For 3 centuries, astronomers chased a wobble so small it could not be seen, a tiny shift in starlight that would prove, at last, how far away the heavens truly lay. This is a story of patience measured not in months but in lifetimes, of instruments refined to impossible precision, of failures that stretched across generations before a single success emerged in the cold observatories of the 1830s. From Tycho Brahe's careful doubts to Friedrich Bessel's triumphant measurement of 61 Cygni, the quest for stellar parallax asked one quiet question over and over again: how vast is the darkness between us and the nearest points of light? If these slow journeys through history help bring rest, there is always more to come for those who subscribe and return. Now, let the centuries unfold gently, beginning in 1573, when a young Danish nobleman first turned his instruments toward a new star burning in Cassiopeia, and so the telling begins. On the 11th day of November in the year 1572, a young Danish nobleman named Tycho Brahe was walking home through the evening air, having spent some hours at the chemical laboratory he kept at Hereward Abbey, which belonged to his uncle, and where he pursued his studies of alchemy and the natural world. The abbey lay in the southern region of what was then Danish territory, in the province of Skane, and the evening was clear and cold, as November evenings tend to be in that part of the world. Tycho was 25 years old, already possessed of a reputation for intellectual seriousness that sat somewhat uneasily with his noble birth, and he had cultivated from his student days a particular fascination with the movements of the heavens, a fascination that his family considered peculiar and perhaps beneath his station. As he walked that evening, he happened to glance upward at the familiar constellation of Cassiopeia, that distinctive W-shaped pattern of stars that traces itself across the northern sky, and there, quite unmistakably, he saw something that should not have been there at all, a star of remarkable brilliance shining where no star had shone before, a star so bright that it rivaled Venus in its luminosity and could not possibly have escaped notice on any previous clear night. Tycho stopped and looked again, because a man of scientific temperament does not simply accept what his eyes tell him when what his eyes tell him contradicts everything he has been taught about the nature of the universe. The heavens, according to the Aristotelian philosophy that formed the foundation of natural science throughout Europe, were perfect and unchanging, composed of a fifth element called the quintessence, and the sphere of the fixed stars, which lay beyond the moon and the planets, had remained exactly as it was since the moment of creation. New stars did not simply appear in that eternal realm, any more than new continents might suddenly rise from the sea. And yet there it was, shining with a steady light, not twinkling as the planets do not twinkle, positioned clearly among the fixed stars of Cassiopeia rather than wandering as a planet wanders. And Tycho, being a careful observer even in that first moment of astonishment, noted its position relative to the other stars in the constellation before he did anything else, because he understood instinctively that this observation might matter very much indeed. In the days and weeks that followed, Tycho devoted himself to the systematic study of this unexpected visitor with an intensity that would come to define his entire approach to astronomy. He constructed, with the help of skilled craftsmen, a large sextant of a design intended to achieve unprecedented accuracy in the measurement of angular positions in the sky. This instrument, which he would later describe in considerable detail in his published writings, consisted of a substantial wooden frame reinforced with carefully fitted brass components, and its arms extended to a considerable length so as to allow very fine divisions to be marked upon its graduated scale. The sextant operated on a simple principle that had been understood since antiquity, allowing the observer to measure the angle between any two celestial objects by aligning sighting devices along the two arms of the instrument and reading the angle from the scale where the arms met. But Tycho brought to this ancient technique a concern for precision that was quite unusual for his time. He calibrated his instruments repeatedly. He checked for sources of systematic error. He made multiple observations on multiple nights and compared the results. And he recorded everything with meticulous care, because he understood that an observation is only as valuable as the reliability of the methods used to obtain it. The question that Tycho sought to answer with these measurements was the question of parallax, which is to say, the apparent shift in the position of a nearby object when viewed from different locations. And this question goes to the very heart of how we understand distances in the universe. When you hold your finger at arm's length and close first one eye and then the other, you observe that your finger appears to shift against the background of more distant objects, and this shift is called parallax. The amount of the shift depends on the distance to your finger and on the separation between your two eyes, which is called the baseline of the observation. An object that is very close shows a large parallactic shift, while an object that is farther away shows a smaller shift, and an object that is extremely far away shows a shift so small that it cannot be measured at all with the instruments available. The Earth itself, as it rotates on its axis, carries the observer from one location to another over the course of a single night, providing a baseline of several thousand miles. And this diurnal parallax, as it is called, should cause any nearby celestial object to appear to shift against the background of more distant stars as the Earth turns. Tycho reasoned, as others had reasoned before him, that if the new star were located in the sublunar realm, in that region below the sphere of the Moon where change and corruption were permitted according to Aristotelian philosophy, then it should display a measurable parallax over the course of a night's observation. The Moon itself shows such a parallax, which is why the Moon appears in slightly different positions against the background stars when observed from different points on the Earth's surface, and comets, which were generally thought to be atmospheric phenomena occurring within the sublunar realm, should show an even larger parallax owing to their presumed proximity to the Earth. If the new star were a comet, or some other form of atmospheric exhalation as some scholars suggested, its parallax should be readily detectable with a well-made instrument. But if the new star showed no parallax at all, or a parallax too small to measure, then it must lie far beyond the Moon, out among the fixed stars themselves, and this would mean that change had occurred in the supposedly unchangeable heavens, which would require a fundamental reconsideration of everything that natural philosophers believed about the structure of the cosmos. Night after night, Tycho measured the position of the new star relative to the other stars in Cassiopeia, particularly the star we now call Skida and the star we call Kaf, and he found that its position remained absolutely constant. He measured its distance from these reference stars when Cassiopeia stood high in the sky and again when the constellation had moved to a different position, and the measurements agreed to within the limits of his instrumental accuracy. He could detect no parallax whatsoever. His instruments were capable of measuring angles to a precision of roughly 1 arcminute, which is 1/60th of a degree, a very fine measurement by the standards of his time, and yet the new star showed no shift greater than this limit. This meant that the star must be located at a distance so great that its parallax, if it had any, was smaller than 1 arcminute, which placed it well beyond the Moon, well beyond the planets, out among the fixed stars at distances that staggered the imagination. This work occupied Tycho through the winter of 1572 and into the spring of 1573, and as he labored over his measurements, He found himself in a somewhat awkward social position that tells us something important about the culture of learning in 16th century Europe. Tycho was a nobleman, born into the highest ranks of Danish aristocracy, and noblemen in that era did not generally engage in activities that required manual skill or technical craftsmanship. The making and using of precision instruments, the careful recording of numerical observations, the long hours of patient measurement in the cold night air, these were activities associated with craftsmen and mechanics, not with men of gentle birth, and Tycho's relatives and peers sometimes expressed dismay at his willingness to engage in such work. There was a social hierarchy of knowledge in Renaissance Europe, and while a nobleman might properly study philosophy or compose verses or discuss the movements of the heavens in general terms, the actual business of measuring and calculating was thought to be beneath his dignity. Tycho disregarded these social conventions entirely, because he understood that the progress of astronomy depended upon precise observation, and precise observation depended upon instruments built and used with care, and if he wanted such observations to be made, he would have to make them himself, regardless of what his fellow nobles might think. The results of Tycho's investigation were published in 1573 in a small book bearing the title De Nova Stella, which means simply on the new star, and this publication marks a turning point in the history of astronomy that cannot be overstated. In clear and methodical prose, Tycho described his observations, explained his methods, presented his measurements, and drew the inescapable conclusion that the new star was located among the fixed stars and not in the sublunar realm. He included detailed diagrams showing the position of the nova within Cassiopeia. He provided tables of his measurements, and he discussed the implications of his findings for the prevailing understanding of celestial physics. The book was not long, but it was thorough, and it demonstrated a commitment to empirical evidence and careful reasoning that would become the hallmark of Tycho's entire scientific career. He had shown, as conclusively as the instruments of his time would allow, that something had changed in the supposedly unchangeable heavens, and this fact demanded explanation. The theological implications of Tycho's discovery were significant and were debated earnestly by scholars throughout Europe in the months and years that followed. The Aristotelian cosmology of perfect and immutable heavens had been woven deeply into Christian theology over the preceding centuries, and many scholars, both Lutheran and Catholic, had come to regard the perfection of the celestial realm as a reflection of divine perfection itself. If the heavens could change, if new stars could appear and presumably old stars could disappear, then what did this say about the constancy of God's creation? And what did it mean for the elaborate theological systems that had been built upon the assumption of celestial immutability? Lutheran scholars, following the tradition established by Martin Luther and Philip Melanchthon, tended to interpret the new star as a sign or portent, a message from God to humanity, without necessarily questioning the underlying cosmological framework, though some did begin to wonder whether Aristotle had been entirely correct about the nature of the heavens. Catholic scholars faced a more difficult challenge, because the Church had invested heavily in the Aristotelian Ptolemaic system as a framework for understanding both the physical and the spiritual cosmos, and any challenge to that system was potentially a challenge to the authority of the Church itself, though the full implications of this tension would not become apparent until the controversies surrounding Galileo in the following century. Tycho was not the only observer to study the new star, and his measurements were confirmed and extended by other astronomers working independently in different parts of Europe. In England, the mathematician and astronomer Thomas Digges made his own observations of the nova and reached conclusions similar to those of Tycho, finding no detectable parallax and therefore concluding that the star lay among the fixed stars rather than in the sublunar realm. Digges was a follower of Copernicus and believed that the Earth moved around the Sun, a position that Tycho himself did not accept. But on the question of the nova's distance, the two observers were in complete agreement. In Germany, a young scholar named Michael Maskelyne, who would later become the teacher of Johannes Kepler, also observed the new star and published his own analysis, which again confirmed the absence of measurable parallax and the celestial nature of the phenomenon. The convergence of these independent observations, made with different instruments by different observers in different countries, lent considerable weight to the conclusion that the nova was genuinely located among the fixed stars, and this convergence was itself an early example of the kind of collaborative verification that would become essential to the progress of modern science. The star that Tycho observed in 1572 is now known to have been a supernova, the catastrophic explosion of a dying star, though of course Tycho had no way of knowing this. What he saw was the light of a stellar explosion that had occurred many thousands of years earlier, finally reaching the Earth after its long journey across the vast distances of interstellar space, and this light shone brilliantly for about 18 months before fading below the threshold of naked eye visibility. Modern astronomers have identified the remnants of this explosion, a shell of expanding gas that can still be observed with radio telescopes and X-ray telescopes, and they have estimated that the supernova occurred at a distance of approximately 7,500 light-years from Earth, which means that the light Tycho saw in 1572 had been traveling through space since about 5,500 years before the Common Era, before the construction of the pyramids, before the invention of writing, before the dawn of recorded history. Tycho could not have known any of this, but he did understand that the star was very far away indeed, and that its appearance in the heavens demonstrated that the celestial realm was not so perfect and unchanging as the philosophers had taught. The absence of measurable parallax in Tycho's observations of the nova was, in one sense, a negative result, a failure to detect something that he was looking for, and yet this negative result carried profound implications for the understanding of the universe. By establishing an upper limit on the parallax of the nova, Tycho had established a lower limit on its distance, and this lower limit placed the nova well beyond the sphere of the Moon, in a region where no change was supposed to occur. The argument from absence is always a delicate one in science, because the failure to detect something might mean that the thing does not exist, or it might simply mean that the instruments used were not sensitive enough to detect it. But in this case, the instruments were sensitive enough to have detected a parallax if the nova had been located within the sublunar realm, and so the absence of detectable parallax really did prove something important about the location of the star. Tycho understood this logic clearly, and he presented it carefully in De Nova Stella, demonstrating that the precision of his measurements was sufficient to rule out any distance closer than the Moon, and therefore establishing beyond reasonable doubt that the nova was a genuine celestial phenomenon. The publication of De Nova Stella brought Tycho a measure of fame that transformed his career and made possible the remarkable astronomical enterprise that would occupy the rest of his life. The King of Denmark, Friedrich II, took notice of this brilliant young nobleman who had demonstrated such skill in the observation of the heavens, and in the years that followed, the king would provide Tycho with the island of Hven, located in the Sound between Denmark and Sweden, along with substantial funding to build there the most advanced astronomical observatory the world had ever seen. At Uraniborg, the castle of the heavens, Tycho would spend more than 20 years making observations of unprecedented accuracy, tracking the positions of the planets and the stars with instruments that he designed himself and that achieved a precision roughly 5 times greater than anything that had come before. These observations, particularly his observations of the planet Mars, would eventually provide the raw material for Johannes Kepler's discovery of the laws of planetary motion, and would thus contribute directly to the scientific revolution that transformed our understanding of the cosmos. But all of this lay in the future on that November evening in 1572, when Tycho first looked up at Cassiopeia and saw a star that was not supposed to be there, a star that changed everything. The nova of 1572 was not, strictly speaking, a contribution to the measurement of stellar parallax in the sense of successfully determining the distance to a star, because Tycho did not detect a parallax and therefore could not calculate a distance. What he could do, and what he did with great skill and care, was establish that no parallax existed within the limits of his measurement accuracy, and this negative result, this demonstrated absence, was itself a finding of enormous importance. It showed that the fixed stars were genuinely far away, farther than the Moon, farther than the planets, farther than any distance that could be measured with the instruments of the time, and it showed that the techniques of careful measurement and precise instrumentation could yield meaningful knowledge about the heavens even when the quantities being measured were too small to detect directly. The quest to measure the true distances to the stars would continue for more than 2.5 centuries after Tycho's observations of the nova, and it would require instruments of ever-increasing precision and baselines of ever-increasing length. But the fundamental approach, the careful measurement of tiny angles and the patient accumulation of observational data, was established in those cold November nights at Hereward Abbey, when a young Danish nobleman turned his sextant toward a new star in Cassiopeia and began the long process of measuring what had never been measured before. In the year 1576, something rather remarkable happened on a small island in the narrow strait between Denmark and Sweden, an island called Hven, which sat low and green in the waters of the Øresund, home to perhaps 40 farming families and their livestock, a quiet place of windswept fields and modest cottages where very little of consequence had ever occurred. King Friedrich II of Denmark, who had become quite fascinated by the work of a young nobleman named Tycho Brahe, decided to grant this entire island to the astronomer, along with all its rents and revenues, so that he might build there whatever facilities he required to continue his observations of the heavens. This was an act of patronage on a scale that had never before been extended to astronomical science, a recognition that the careful measurement of the stars was worthy of royal investment, and it would transform not only the life of one man but the entire future of precision astronomy. Friedrich had been impressed by Tycho's observations of the new star that had appeared in Cassiopeia in 1572. And he had come to understand that Denmark possessed in this unusual nobleman a resource of genuine value, someone whose meticulous approach to celestial observation surpassed anything being done elsewhere in Europe. The king was also motivated by a certain national pride, for he did not wish to see Tycho accept the generous offers that had come from other courts, particularly from the Landgrave William of Hesse-Kassel, who was himself an enthusiastic practitioner of astronomy and who would very much have liked to attract Tycho to his own domain. And so the island of Hven was offered, along with additional funds for construction and a promise of ongoing financial support, creating circumstances that allowed Tycho to dream on a scale that would have seemed fantastical to any astronomer of previous generations. The construction that began on Hven in 1576 and continued through 1580 was nothing less than the creation of the first true research institution dedicated to astronomical observation, a place designed from its very foundations to facilitate the precise measurement of celestial positions with an accuracy that had never before been achieved. Tycho named his new creation Uraniborg, which means the castle of Urania, after the muse of astronomy, and the building that rose on the highest point of the island was a remarkable fusion of Renaissance architectural ideals with the practical requirements of scientific work, a structure that was simultaneously a nobleman's residence, a workshop for instrument makers, and an observatory equipped with the most sophisticated measuring devices that human ingenuity could devise. The main building of Uraniborg was constructed in a style that drew upon the architectural theories then fashionable in Northern Europe, incorporating elements of both Gothic and classical design into a symmetrical whole that pleased the eye while serving very specific functional purposes. The structure was built around a central axis, with matching wings extending to the north and south, and the entire composition was oriented precisely with respect to the cardinal directions, so that the walls themselves could serve as references for certain types of observation. The building materials were carefully chosen, with brick forming the primary structure and sandstone used for decorative elements, and the construction was carried out with considerable attention to durability, for Tycho intended this to be a place where observations would continue for many decades. At the heart of Uraniborg's design were the observing rooms, positioned at the corners of the building where large windows and removable roof sections could provide unobstructed views of the sky in multiple directions. These were not simply rooms with windows, but carefully planned spaces where massive instruments could be permanently mounted and precisely aligned, where an observer could work in reasonable comfort during the long cold nights of the Danish winter, protected from wind and weather while still having access to whatever portion of the heavens required examination. The integration of observing facilities into the fabric of a substantial building represented a significant departure from earlier practice, when astronomers had typically made their observations from open rooftops or temporary structures, exposed to the elements and working with portable instruments that had to be set up afresh for each session of observation. One of the most impressive instruments installed at Uraniborg was the Great Mural Quadrant, an enormous measuring device that was built into the very fabric of a south-facing wall, its graduated arc spanning nearly 6 feet in radius. A mural quadrant is essentially a quarter circle mounted vertically against a wall that has been aligned precisely with the local meridian, the imaginary line running from north to south through the point directly overhead. And such an instrument allows the observer to measure the altitude of a star at the exact moment when it crosses this meridian, which is the moment when the star reaches its highest point in the sky. By combining this altitude measurement with an accurate determination of the time, an astronomer can calculate the star's position with considerable precision, and the larger the quadrant, the more finely its arc can be graduated, allowing smaller fractions of a degree to be read directly from the scale. Tycho's Great Mural Quadrant was decorated with a painted mural depicting Tycho himself seated at work within a representation of Uraniborg, surrounded by images of his instruments and assistants, with a faithful dog resting at his feet. And this painting has survived in engravings that give us a vivid picture of how the observatory appeared during its years of active use. But the artistic embellishment should not obscure the fact that this was fundamentally a scientific instrument of unprecedented precision, its brass arc carefully divided and subdivided to allow readings that approached 1 arc-minute in accuracy, a level of measurement that was perhaps 10 times more precise than anything that had been achieved before. To understand what this level of precision meant in practical terms, it is helpful to consider the apparent size of celestial objects. The full moon, as seen from Earth, subtends an angle of approximately half a degree, or 30 arc-minutes, in the sky, which means that 1 arc-minute is roughly 1/30th of the lunar diameter. Previous astronomical measurements had typically been accurate to perhaps 10 or 15 arc-minutes at best, which is to say that the position of a star might be uncertain by a quantity equal to 1/3 or 1/2 the diameter of the Moon, a margin of error that would completely obscure the tiny parallax shift that even nearby stars exhibit. Tycho's goal was to reduce this uncertainty to 1 arc-minute or less, pushing into a realm where parallax might finally become detectable if stars were close enough and if the Copernican theory was correct. The achievement of this precision required not only large instruments but also innovative techniques for reading the scales that were engraved upon them. Tycho developed and refined a system of transversal lines, a geometric method that allowed fractions of the smallest marked divisions to be estimated with considerable reliability. The principle behind transversal lines involves the use of diagonal lines that cross the main scale at a slight angle, creating a pattern of intersections that can be interpolated by eye, somewhat like the vernier scales that would later become common on precision instruments. By counting how many transversal lines a pointer crosses before reaching a main division mark, an observer can estimate tenths or even smaller fractions of that division, extending the effective resolution of the scale well beyond what could be achieved by direct estimation alone. This technique was not entirely original to Tycho, having been used in various forms by earlier instrument makers, but he applied it with systematic rigor across all of his major instruments, developing consistent methods that his assistants could learn and apply, reducing the variation that might arise from different observers using different approaches. The combination of large size, careful construction, and refined reading techniques allowed the instruments of Uraniborg to achieve a level of accuracy that would not be substantially surpassed until the invention of the telescope transformed the entire practice of astronomical observation. Among the other instruments that Tycho installed at Uraniborg were several large armillary spheres, which are frameworks of graduated rings that can be rotated to measure positions anywhere in the sky, not just along the meridian. These instruments allowed observations to be made at any hour of the night, without waiting for a star to cross the meridian, which increased the efficiency of the observing program and allowed more data to be gathered during each clear night. There were also smaller quadrants and sextants of various designs, each suited to particular types of measurement, and the collection grew over the years as Tycho and his instrument makers refined their techniques and identified opportunities for improvement. The main building of Uraniborg also featured a revolving wooden dome, one of the earliest examples of such a structure, which allowed a large instrument to be pointed in any direction while remaining protected from the weather. This dome could be rotated by means of a mechanism that Tycho designed, enabling the observer to track objects across the sky without having to move the entire instrument, a considerable advantage when working with devices that were too heavy to be easily repositioned. The concept of the rotating dome would eventually become standard in observatory design, reaching its fullest expression in the great observatories of the 19th and 20th centuries. But it was at Uraniborg that this idea was first implemented on a practical scale. Despite the sophistication of the facilities in the main building, Tycho came to recognize that there were limitations inherent in observing from an elevated structure, for even the most solidly built tower will sway slightly in the wind, and the warmth of a heated building creates currents in the air that can cause the images of stars to shimmer and dance, degrading the precision of measurements. To address these concerns, Tycho began construction in 1584 of a second observatory, which he named Stjernborg, meaning star castle, and which was built almost entirely underground, with only small cupolas projecting above the surface to shelter the upper portions of the instruments. The subterranean design of Stjernborg provided several important advantages. The instruments were mounted on foundations that extended deep into the Earth, isolating them from vibrations and movements that might affect structures built above ground. The temperature underground remains relatively constant throughout the year, reducing the thermal expansion and contraction of metal components that can introduce errors into precise measurements. And the low profile of the buildings meant that wind had little purchase, eliminating the swaying that could plague observations made from towers or elevated platforms. Each instrument at Stjernborg was housed in its own small chamber, with a domed roof that could be opened to the sky, and the arrangement allowed multiple observers to work simultaneously on different measurements without interfering with one another. The combination of Uraniborg and Stjernborg gave Tycho a range of facilities that exceeded anything available elsewhere in the world, and he used these resources to mount a sustained program of observation that continued for more than 2 decades, gathering data on the positions of stars, planets, the Sun, and the Moon with a consistency and precision that had never before been attempted. This was not occasional observation undertaken when circumstances permitted, but a systematic campaign of measurement that sought to record the heavens night after night, season after season, building up a body of data that would eventually allow patterns and regularities to be discerned with unprecedented confidence. But Uraniborg was much more than an observatory. Tycho understood that the reduction of astronomical observations into useful catalogues and tables required extensive computation, and that the dissemination of results required the ability to produce printed books and illustrations, and so he equipped his island establishment with facilities that supported the entire process of scientific work, from raw observation to published result. A paper mill was constructed on the island, using local materials to produce the paper needed for Tycho's publishing activities, and a printing press was installed at Uraniborg itself, staffed by workers who could set type and produce the carefully illustrated volumes that Tycho wished to share with the learned world. The printing press was particularly important because Tycho had very specific ideas about how astronomical data and instrument designs should be presented, with detailed engravings that showed the construction and use of his various devices, and he found that working with commercial printers elsewhere introduced delays and compromises that he preferred to avoid. By bringing the entire production process onto the island, he could supervise every stage of publication, ensuring that the finished works met his exacting standards. The books that emerged from the Uraniborg press were notable for their quality and their comprehensive treatment of both observational results and the methods by which those results had been obtained, setting a standard for scientific publication that influenced later generations. Tycho also maintained a chemical laboratory at Uraniborg, reflecting the broader interests that were common among natural philosophers of his era, when the boundaries between what we now call chemistry, medicine, and alchemy were not clearly drawn. He prepared medicines and conducted experiments with various substances, pursuing questions about the nature of matter alongside his astronomical investigations, and this diversity of activity was seen not as a distraction but as a natural expression of a comprehensive curiosity about the workings of the natural world. The laboratory was equipped with furnaces, distillation apparatus, and the various vessels and implements required for chemical work, and Tycho devoted considerable time to these pursuits, though it is his astronomical legacy for which he is now primarily remembered. The operation of such an extensive establishment required a substantial workforce, and Tycho gathered around him a community of assistants, students, and craftsmen who lived and worked on the island, forming what might be considered an early example of a scientific research group. Among these assistants were skilled instrument makers who could fabricate the metal components required for Tycho's devices, observers who could help gather data during the long nights of systematic measurement, and scholars who could assist with the mathematical computations needed to reduce raw observations into useful results. At its peak, the Uraniborg establishment employed perhaps 24 people in various capacities, creating a concentration of astronomical expertise that had no parallel elsewhere. One of the most notable of Tycho's assistants was his younger sister Sophie Bray, who was herself a capable astronomer and who participated in the observational work at Uraniborg during the 1580s. Sophie had received an education unusual for a woman of her time, learning Latin, history, and natural philosophy, and she developed a particular interest in astronomy that her brother encouraged and supported. She assisted with observations and calculations, demonstrating competence in technical work that was typically reserved for men, and her involvement illustrates the somewhat unusual intellectual atmosphere that prevailed at Uraniborg, where practical ability could be valued alongside social convention. The cost of maintaining all these facilities and personnel was considerable, and the financial records that survive indicate that Friedrich II and his successors provided Tycho with annual support amounting to approximately 1% of the entire Danish state revenue, an extraordinary allocation of resources to a single scientific enterprise. This figure included not only the direct grants from the Crown, but also the revenues from various estates and church properties that had been assigned to Tycho's support, creating an income stream that allowed him to pursue his work without the financial anxieties that constrained most scholars of his era. Such lavish patronage reflected the high value that Friedrich placed upon Tycho's work, but it also created dependencies and obligations that would eventually contribute to difficulties when royal favor shifted. The systematic nature of Tycho's observational program represented a fundamental change in how the search for stellar parallax could be conducted. Previous astronomers who had attempted to detect parallax had made occasional observations, comparing positions measured months or years apart, working with instruments of limited precision, and accepting whatever data they happened to gather as sufficient basis for their conclusions. Tycho transformed this sporadic approach into a sustained scientific program, observing the same stars repeatedly throughout the year, comparing measurements made with different instruments, checking results against multiple reference points, and building up a body of data that could reveal systematic patterns while averaging out random errors. This approach required patience and persistence on a scale that had never before been applied to astronomical observation. It meant observing not just when conditions seemed favorable for detecting parallax, but continuously, so that any real effect could be distinguished from spurious variations caused by atmospheric conditions, instrumental errors, or other factors. It meant developing standardized procedures that different observers could follow consistently, so that data gathered over many years by various assistants could be combined into a coherent whole. And it meant maintaining careful records of every observation, every instrument setting, every circumstance that might affect the reliability of a measurement, creating archives that could be consulted years or decades later when questions arose about the meaning of particular results. On the island of Hven, in the buildings of Uraniborg and the underground chambers of Stjernborg, with instruments of unprecedented size and precision, supported by a staff of capable assistants and funded by royal patronage of remarkable generosity, Tycho Brahe created the conditions under which the question of stellar parallax could finally be addressed with the rigor it deserved. The instruments were ready, the methods were developed, the workforce was assembled, and the observations could begin in earnest, night after night, season after season, the great quadrant tracing arcs across its scale, the assistants recording numbers in their ledgers, the data accumulating slowly but steadily like sediment laid down in ancient seas. And so we come now to a question that hung in the air for many decades, a question that astronomers could not escape once the idea of a moving Earth had been placed before them. And that question concerned the apparent positions of the stars and whether those positions might shift ever so slightly over the course of a year, as the Earth, if indeed it moved, carried us around the Sun and offered us different vantage points from which to observe the heavens. And this subtle shift, this gentle wobble in stellar positions, is what astronomers would come to call stellar parallax, and its presence or absence would become one of the most important tests of whether the Sun truly stood at the center of the cosmos, or whether our Earth remained, as tradition had long held, motionless at the center of all things, with the heavens wheeling about us in their ancient courses. The story of this challenge begins properly with Nicolaus Copernicus, the Polish astronomer and church administrator who spent much of his life in the small town of Frombork, on the Baltic coast, where he served as a canon of the cathedral and pursued his astronomical studies in the quiet hours that his duties allowed. And it was there, working patiently over many years, that Copernicus developed his revolutionary proposal that the Sun, not the Earth, occupied the center of the planetary system, with the Earth becoming merely one of the planets, circling the Sun just as Mercury and Venus and Mars and Jupiter and Saturn did. And this idea, which Copernicus hesitated to publish for fear of ridicule and opposition, finally appeared in print in the year 1543, in a substantial volume titled De Revolutionibus Orbium Celestium, which we might translate as On the Revolutions of the Heavenly Spheres. And this book, dedicated to Pope Paul III, presented not merely a philosophical speculation but a detailed mathematical system, complete with tables and calculations, that allowed astronomers to predict the positions of the planets using the assumption of a sun-centered cosmos. Now Copernicus was a careful thinker, and he understood very well that his proposal carried certain implications that could be tested against observation, and one of the most important of these implications concerned the stars, those distant points of light that had always seemed fixed and unchanging against the black velvet of the night sky. And the geometric argument was straightforward enough that any person familiar with basic principles of vision and perspective could grasp it. For if the Earth truly moved around the Sun, then over the course of a year we would be carried from one side of that great orbit to the other, a journey of immense proportions, and from these different positions we would be looking out at the stars from slightly different angles. And just as a nearby tree appears to shift against the distant hills when you walk from one side of a meadow to the other, so too should a nearby star appear to shift against the more distant stars when the Earth carries us from one side of its orbit to the other. And this shifting, this annual wobble in stellar positions, is precisely what astronomers mean when they speak of stellar parallax. The geometry of the situation can be understood in this way, and you may find it helpful to imagine it gently as you listen, for it is not a difficult concept, merely one that requires a moment of quiet thought. And so consider that you are standing at one point on the Earth in the month of January, looking out at a particular star, and then 6 months later, in July, the Earth has carried you to the opposite side of its orbit around the Sun, so that you are now looking at that same star from a position that is separated from your January position by the full diameter of the Earth's orbit, which astronomers would eventually determine to be roughly 300 million kilometers. Though of course this precise figure was not known in the time of Copernicus, and from this new vantage point, if the star is not infinitely far away, it should appear to have shifted slightly against the background of more distant stars, and the amount of this shift, measured as an angle, would depend on the star's distance, with closer stars showing a larger shift and more distant stars showing a smaller shift. And if you could measure this angle with sufficient precision, you could then use simple principles of geometry to calculate the actual distance to the star, which was something that had never been achieved and which represented one of the great unanswered questions of astronomy. Copernicus himself addressed this matter directly in the first book of De Revolutionibus, for he was well aware that any thoughtful reader would immediately raise the objection that if the Earth moved, then surely this stellar parallax should be observable, and yet careful observers over many centuries had never detected any such shift in the positions of the stars, and Copernicus acknowledged this problem honestly, for he was not one to shy away from difficulties, and his solution was both simple and rather breathtaking in its implications, for he proposed that the stars were so enormously distant that their parallax, though it must certainly exist, was far too small to be detected by the instruments then available, and when you pause to consider what this meant, you begin to appreciate the vastness that Copernicus was asking his readers to accept. For the absence of detectable parallax implied that the stars were not merely far away in any ordinary sense, but that they were removed to distances so immense as to dwarf the entire orbit of the Earth, reducing that great circle, some 300 million kilometers in diameter, to a mere point when viewed against the backdrop of the stellar sphere. And so Copernicus, in defending his heliocentric system, was forced to expand the universe to a size that many of his contemporaries found difficult to accept, for the traditional cosmos, with the Earth at its center, had been a relatively cozy affair, with the sphere of the fixed stars lying just beyond the orbit of Saturn, completing a neat and orderly arrangement in which everything had its proper place and in which the universe, though certainly large by human standards, was not incomprehensibly vast. And now Copernicus was asking people to believe that the stars were so distant that the Earth's orbit, enormous though it might be, was utterly negligible by comparison, and this required a fundamental shift in how one thought about the scale of creation, a shift that many were unwilling or unable to make, and the absence of detectable stellar parallax became, for the opponents of Copernicus, one of the strongest arguments against the heliocentric system, a point to which they would return again and again in the decades that followed. Among the most formidable of these opponents was the Danish astronomer Tycho Brahe, who was born just 3 years after the publication of De Revolutionibus and who would become, in the latter half of the 16th century, the greatest observational astronomer since the ancient Greeks, and Tycho, working from his magnificent observatory on the island of Hven, which the King of Denmark had granted him for his astronomical work, made measurements of the positions of stars and planets with a precision that had never before been achieved, using large and carefully constructed instruments made of brass and steel. And Tycho understood very well the implications of stellar parallax for the Copernican system, and he searched for this parallax with all the skill and determination that his instruments and his abilities allowed, and yet he could not find it, and the limit of his measurements, which was approximately 1 arcminute, or 1/60th of a degree, meant that if the stars had any parallax at all, it must be smaller than this amount. And when Tycho worked through the geometric calculations to determine what this implied about stellar distances, the numbers that emerged were deeply troubling to him. To understand Tycho's reasoning, consider that the parallax angle, the distance from the Earth to the Sun, and the distance from the Sun to the star form a simple geometric relationship. And if the parallax angle is very small, then the distance to the star must be very large in proportion to the distance from the Earth to the Sun, And Tycho calculated that a parallax of 1 arc-minute would imply that the nearest stars were at least 3,400 astronomical units away, where 1 astronomical unit is the distance from the Earth to the Sun. And this was already an almost inconceivable distance. But since Tycho could not detect any parallax even at this level, the stars must be even more distant still. And this created a problem that went beyond mere distance. For in the Copernican system, the stars were generally assumed to be suns like our own. And if they were as distant as the absence of parallax implied, then they must also be enormous in size, far larger than our own sun, in order to appear as bright as they did. And Tycho found this arrangement to be implausible. For what sense did it make for God to create such monstrous suns at such absurd distances, visible only as tiny points of light, when a more economical arrangement would have served just as well? And so Tycho, finding himself unable to accept the Copernican system due to the absence of stellar parallax and other concerns, but also recognizing that the Copernican mathematics had certain advantages for predicting planetary positions, developed his own compromise system, which he published in 1588. And in this Tychonic system, as it came to be called, the Earth remained stationary at the center of the cosmos, with the Moon and Sun orbiting around it. But the other planets, Mercury and Venus and Mars and Jupiter and Saturn, orbited around the Sun, so that the Sun carried its family of planets with it as it circled the Earth. And this arrangement preserved the mathematical advantages of the Copernican system, which had the planets orbiting the Sun, while avoiding the physical and observational difficulties, including the absence of stellar parallax, that arose from giving motion to the Earth. And for many astronomers of the late 16th and early 17th centuries, the Tychonic system offered an attractive middle path, accepting the useful parts of Copernicus while rejecting those aspects that seemed to conflict with observation and with Scripture. The question of stellar parallax also carried theological weight, for in the traditional Christian understanding of the cosmos, everything had been created with purpose and meaning, and the Earth occupied its central position not by accident but by design, as the stage upon which the drama of human salvation was unfolding, and the stars and planets existed to serve human needs, whether for navigation or for keeping track of the seasons or for signs of divine providence. And in this understanding, it made sense that the cosmos should be of a manageable size, with the Earth at its heart and the heavenly bodies arranged in an orderly fashion around it. But if Copernicus was right, and if the stars were at such enormous distances that their parallax could not be detected, then what purpose did all that empty space serve? And why would God create such a wasteful and seemingly pointless expanse of nothingness between the orbit of Saturn and the sphere of the fixed stars? For in traditional cosmology there had been no such gulf, with the stars lying just beyond the outermost planet. But now Copernicus was asking people to believe in a cosmos where the overwhelmingly greater part of creation was simply empty space, containing nothing of apparent value or purpose. And this seemed to many to be inconsistent with the wisdom and economy of the Creator. There was, however, at least one thinker who embraced the expanded cosmos with enthusiasm, taking the Copernican implications even further than Copernicus himself had done, and this was Giordano Bruno, an Italian philosopher and former Dominican friar who lived a restless and wandering life, moving from city to city across Europe, teaching and writing and engaging in disputes with authorities both religious and academic. And Bruno proposed that the universe was not merely large but infinite, with no center and no boundary, containing not one sun but countless suns scattered throughout the boundless depths of space, each of them perhaps accompanied by its own planets. And in Bruno's vision, The stars that we see in the night sky were indeed distant suns, as Copernicus had suggested, but rather than being arranged on a sphere at some definite distance from us, they were scattered throughout infinite space, some closer and some unimaginably far away, and the problem of stellar parallax dissolved in this conception, for if the stars were at varying and perhaps infinite distances, then the absence of detectable parallax simply meant that we had not yet observed stars that were close enough to show a measurable shift, while countless other suns populated the infinite reaches of space beyond any hope of parallax detection. Bruno's ideas were radical in the extreme, and they brought him into conflict with the Catholic Church, not only for his cosmological speculations but for his theological and philosophical views, which were seen as heretical on multiple grounds, and he was eventually arrested by the Inquisition, tried over a period of years, and burned at the stake in Rome in the year 1600, though it remains unclear exactly which of his many controversial positions were considered most serious in his condemnation. And we should not imagine Bruno as a martyr for science in any simple sense, for his thought was a complex mixture of mysticism and philosophy and speculation, but his cosmological vision, whatever its other aspects, did offer a kind of solution to the parallax problem, by proposing that the universe was vast beyond measure and that the absence of detectable stellar parallax was simply a consequence of the enormous distances involved, though of course this solution required accepting an infinite universe, which carried its own difficulties and which most astronomers of the time were not prepared to embrace. And so the situation stood as the 16th century gave way to the 17th, with the Copernican system offering mathematical advantages and a certain elegance of conception, but lacking observational proof of the Earth's motion, while the Tychonic system preserved the stationary Earth and avoided the troubling implications of undetectable stellar parallax, and the question of whether the stars would reveal, through some tiny annual shift in their positions, the truth about the Earth's motion, remained open, awaiting instruments of greater precision and observers of greater patience, and the challenge that Copernicus had laid down, by acknowledging that his system predicted a stellar parallax that could not yet be detected, would continue to motivate astronomers for generations to come, driving them to build better instruments and to make more careful observations, in the hope that someday, somehow, they might detect that elusive wobble in the positions of the stars, and thereby settle one of the great questions of their age. The geometric reasoning was sound, and no one seriously disputed that if the Earth moved, stellar parallax must exist, for this followed necessarily from the basic principles of optics and perspective that had been understood since ancient times, and the only question was whether this parallax was simply too small to measure, as Copernicus and his followers maintained, or whether its absence indicated that the Earth truly did not move, as Tycho and other geocentrists argued. And resolving this question would require advances in the technology of astronomical measurement that could not be foreseen in the 16th century, for the instruments of that era, however carefully made, were limited by the unaided human eye and by the mechanical precision that craftsmen could achieve with the materials and techniques available to them, and the parallax of even the nearest stars, as we now know, is less than 1 arcsecond, which is 60 times smaller than the 1 arc-minute limit of Tycho's observations, and detecting such tiny angles would require not only better instruments but also a better understanding of the various effects that could cause apparent shifts in stellar positions, effects that had nothing to do with parallax and that would need to be identified and accounted for before the true parallax signal could be extracted from the observations. The stakes of this question were considerable, for at issue was not merely a technical matter of astronomical modeling but the very structure of the cosmos and humanity's place within it, and the theological dimensions of the problem ensured that it would remain controversial for many years to come, as the churches of both Catholic and Protestant Europe generally favored the traditional geocentric worldview, which seemed to accord better with certain passages of Scripture and with the long tradition of Christian cosmology, and the absence of detectable stellar parallax provided a convenient scientific argument against the Copernican system, one that did not rely solely on appeals to Scripture or tradition, but that seemed to arise from observation itself. And those who wished to defend the moving Earth would need to explain why God had created such an apparently wasteful expanse of empty space, or else find some way to detect the parallax that their system predicted. And neither of these paths was easy, and so the question remained unsettled, a gentle puzzle awaiting its solution in the fullness of time. In the early years of the 17th century, a new instrument appeared in the workshops of Europe, an arrangement of lenses held within a tube, which would in time transform everything that astronomers believed they knew about the heavens and their place within them. The telescope, as it came to be called, was not invented by any single person in any single moment, but emerged gradually from the craft of spectacle makers in the Netherlands, where the grinding of lenses for eyeglasses had become a refined trade. By the autumn of 1608, word had spread across the continent that certain Dutch craftsmen had discovered a way of combining lenses so that distant objects appeared much closer than they truly were, and this news eventually reached the ears of a mathematics professor in the Republic of Venice, a man named Galileo Galilei, who was then teaching at the University of Padua and who would soon become one of the most consequential figures in the history of science. Galileo learned of the Dutch invention through letters and travelers' reports, and being both curious and skilled with his hands, he set about constructing his own version of the device during the summer of 1609, working from nothing more than descriptions of what the instrument could do, without ever having seen one himself. His first attempts were modest, producing magnifications of only 3 or 4 times, but within months he had improved his technique considerably, grinding and polishing lenses with increasing precision until he possessed telescopes that could magnify objects 20 times or more, far surpassing anything the original Dutch makers had achieved. And it was with these improved instruments that Galileo turned his attention to the night sky in the autumn and winter of 1609 and into the early months of 1610, making observations that would change the course of astronomy and, indeed, of human thought more generally. What Galileo saw through his telescope was remarkable in ways both expected and unexpected. The moon, which had always appeared to the naked eye as a smooth and perfect sphere, was revealed to be rough and mountainous, covered with craters and valleys not unlike the terrain of the Earth itself. The planet Jupiter was accompanied by 4 small points of light that moved around it from night to night, clearly orbiting the great planet just as the moon orbits the Earth, providing a miniature model of a heliocentric system visible to anyone who cared to look. The Milky Way, that faint band of light stretching across the sky, was resolved into countless individual stars, far more numerous than anyone had imagined, suggesting that the universe was vastly larger and more populated than previous generations had supposed. Galileo published these discoveries in a small book called Sidereus Nuncius, or The Starry Messenger, in March of 1610, and the work spread rapidly through the intellectual circles of Europe, inspiring wonder in some readers and deep unease in others. For our purposes, following the thread of stellar parallax through the centuries, what matters most about Galileo's telescopic observations is not the mountains of the Moon or the satellites of Jupiter, but rather what he hoped to find among the fixed stars and what he did not find there. Galileo was a committed supporter of the Copernican system, believing that the Earth truly did move around the Sun rather than remaining stationary at the center of creation. And he understood very well that if the Earth moved, then the stars should display parallax, that apparent annual shift in position caused by our changing vantage point as we orbit from one side of the Sun to the other. He also understood that the failure to detect this parallax had long been one of the strongest arguments against the Copernican theory, and so he naturally hoped that his new and powerful instrument might succeed where the naked eye had failed, revealing at last the telltale wobble that would prove the Earth's motion beyond any reasonable doubt. But Galileo did not detect stellar parallax, despite his careful observations and his improved instruments. The stars, even when viewed through his best telescopes, remained stubbornly fixed in their positions throughout the year, showing no measurable shift that could be attributed to the Earth's orbital motion. This was disappointing, certainly, but Galileo was not discouraged by this failure, nor did he take it as evidence against the Copernican system. Instead, he reasoned that the stars must simply be so extraordinarily distant that even the baseline provided by the Earth's orbit, some 300 million kilometers from one extreme to the other, was not sufficient to produce a detectable shift, at least not with the instruments then available. The parallax was there, he believed, waiting to be found, but it was smaller than his telescopes could measure, hidden below the threshold of detection by the immense gulfs of space that separated our solar system from even the nearest stars. This argument, that the absence of observable parallax proved not that the Earth was stationary but rather that the stars were inconceivably remote, was not original to Galileo. It had been offered by Copernicus himself and by others before him. But Galileo developed and defended this position with particular vigor, most notably in his famous work Dialogo sopra I due massimi sistemi del mondo, or Dialogue Concerning the Two Chief World Systems, which was published in 1632 after many years of preparation and negotiation with church authorities. In this book, Galileo presented the arguments for and against the Copernican and Ptolemaic systems through a conversation among three characters, and when the subject of stellar parallax arose, he addressed the objection directly and at some length, acknowledging that no parallax had yet been observed but expressing confidence that future improvements in instruments and techniques would eventually reveal it. Galileo's position in the dialogue was that the technology of his day was simply not adequate to the task, that telescopes would need to become more powerful and methods of measurement more refined before parallax could be detected among the stars. He spoke of the matter with a kind of patient optimism, suggesting that what one generation could not accomplish might well be achieved by generations yet to come, and that the absence of evidence in the present did not constitute evidence of absence for all time. This was a reasonable and scientifically sound position, and it would eventually be vindicated more than 2 centuries later when Friedrich Bessel finally measured the parallax of 61 Cygni in 1838. But Galileo himself did not live to see this confirmation, passing away in 1642 while under house arrest for his advocacy of Copernican ideas. Working at roughly the same time as Galileo, though in the rather different intellectual climate of the Holy Roman Empire, was Johannes Kepler, the German mathematician and astronomer whose laws of planetary motion would form one of the foundations of modern physics. Kepler and Galileo were aware of each other's work and corresponded on various subjects, though their relationship was complicated by distance, by differing temperaments, and by the practical difficulties of communication in that era. Kepler was deeply interested in the question of stellar distances and devoted considerable thought to the problem of parallax, approaching it from both observational and theoretical perspectives and arriving at conclusions that, while ultimately incorrect in their details, represented serious and thoughtful attempts to grapple with one of the most difficult questions in astronomy. Kepler's greatest contribution to practical astronomy was his Tabulae Rudolphinae, or Rudolphine tables, published in 1627 after decades of labor. These tables, based on the extraordinarily precise observations made by the Danish astronomer Tycho Brahe, provided predictions of planetary positions that were far more accurate than anything previously available, and they remained the standard reference for astronomers for more than a century. In preparing these tables, Kepler had necessarily spent a great deal of time thinking about measurement and precision, about the limits of what could be observed and calculated, and about the sources of error that plagued astronomical work. He was therefore well equipped to consider the problem of stellar parallax, and he did so with characteristic thoroughness. One of the factors that complicated Kepler's thinking about stellar distances, and indeed the thinking of astronomers for the next 200 years, was the apparent size of stars as seen through telescopes of that era. When Kepler and his contemporaries observed bright stars through their instruments, they saw not mere points of light but small disks, typically measuring about 2 arc-minutes in diameter for the brightest stars such as Sirius or Vega. These disks seemed real and substantial, suggesting that stars were objects of definite angular size that could be measured and compared, and Kepler incorporated this apparent size into his calculations of stellar distances in ways that led him significantly astray. The problem, which would not be fully understood until much later, was that these stellar disks were not real. They were optical artifacts, caused by the diffraction of light as it passed through the small apertures of early telescopes and by various imperfections in the lenses themselves. A perfect point source of light, when viewed through any optical system with a finite aperture, will appear not as a point but as a small disk surrounded by faint rings, a phenomenon now known as the airy disk after the 19th-century astronomer who first described it mathematically. The apparent size of this disk depends on the diameter of the telescope's aperture and on the wavelength of the light being observed, not on any property of the distant star itself. But Kepler and his contemporaries had no way of knowing this, and so they took the spurious disks at face value, reasoning from them about the nature and distances of the stars in ways that were inevitably mistaken. In his epitome Astronomii Copernicani, a comprehensive textbook of Copernican astronomy published in 3 volumes between 1618 and 1621, Kepler worked through the implications of stellar sizes and distances with careful mathematical reasoning, arriving at conclusions that revealed just how strange the Copernican universe must be if it were true. If the stars were other suns, comparable in actual size and brightness to our own sun, and if they appeared as small as they did in the sky while still showing disks of about 2 arc-minutes, then they must be located at almost incomprehensible distances from us. Kepler calculated that a star like Sirius, on these assumptions, would need to be at least 2 million astronomical units away, where 1 astronomical unit is the distance from the Earth to the Sun. This was an enormous number, far larger than anything that had been seriously contemplated before, and it suggested that the universe was not merely large but almost inconceivably vast. What Kepler did not know, and could not have known, was that his estimate was actually far too small. The true distance to Sirius is approximately 8.6 light-years, which corresponds to roughly 544,000 astronomical units, about a quarter of Kepler's estimate. But this apparent accuracy is merely coincidental, arising from the fact that the spurious disk diameters led Kepler to underestimate stellar distances, while his assumption that bright stars must be comparable in luminosity to our Sun led him to overestimate them. And these two errors happened to partially cancel each other out. The nearest stars are actually somewhat closer than Kepler supposed, but they are also much smaller in angular size. Essentially point sources whose apparent disks are entirely artificial products of the telescope's limitations. The correspondence between Kepler and Galileo touched on these matters of stellar distances, though the two men approached the subject from somewhat different perspectives. Galileo was more focused on observational evidence and on defending the Copernican system against its critics, while Kepler was more inclined toward theoretical speculation and mathematical harmony, seeking to understand why the universe was constructed as it was rather than merely demonstrating that it was so constructed. Their exchange of letters was respectful and collegial, though marked by occasional misunderstandings and by the inevitable delays of 17th-century postal systems, and it represents one of the first serious scientific discussions of what we might now call the scale of the universe. Contemporary with Galileo and Kepler, though less well remembered today, was the German astronomer Simon Marius, who made many of the same telescopic discoveries as Galileo and published his own account of them in a work titled Mundus Jovialis, or The World of Jupiter, in 1614. Marius claimed to have observed the moons of Jupiter independently of Galileo and perhaps even slightly earlier, a claim that led to considerable acrimony between the two men and that has been debated by historians ever since. What is clear is that Marius was a capable observer who used his telescope to study the stars as well as the planets, and that he too grappled with the apparent sizes of stars and the implications of those sizes for the structure of the cosmos. Marius noted, as others had, that stars seen through the telescope appeared to have measurable disks, and he used this observation to argue about stellar distances and the plausibility of the Copernican system. His conclusions were broadly similar to those of Kepler and Galileo, acknowledging that if the Earth moved, the stars must be very far away indeed, though the precise figures varied depending on the assumptions one made about stellar sizes and brightnesses. The important point for our story is that Marius, like his more famous contemporaries, was misled by the spurious disks that his telescope produced, and that this misleading information would continue to complicate astronomical thinking about stellar distances for generations to come. The spurious stellar disks seen through early telescopes deserve a moment of further consideration, for their influence on the history of parallax measurement was profound and long-lasting. When an astronomer of the 17th or 18th century looked at a bright star through a telescope, what appeared was not a sharp point of light but a small, fuzzy disk with a definite angular diameter that could be measured and recorded. This disk seemed perfectly real, and there was no obvious reason to doubt that it represented the actual apparent size of the star itself. Different stars had disks of different sizes, with brighter stars generally appearing larger than fainter ones, and this pattern seemed consistent with the idea that the disks reflected some genuine property of the stars rather than being artifacts of the observing equipment. The consequences of this misunderstanding were significant. If stars had measurable angular diameters of 1 or 2 arc-minutes, then any parallax shift smaller than this diameter would be essentially impossible to detect, for it would be lost within the apparent size of the stellar disk itself. An astronomer trying to measure the parallax of a star would need to determine the position of its center with very high precision, and if the star appeared as a fuzzy blob rather than a sharp point, this determination would be difficult and uncertain. Furthermore, the apparent sizes of stellar disks seemed to place constraints on how distant stars could be, for if a star showed a disk of a certain angular size and was assumed to be similar in actual size to our Sun, Then simple geometry could be used to calculate its distance, and this calculated distance set an upper limit on how large the parallax could be. These spurious disks therefore had a double effect on parallax studies. First, they made the actual measurement of parallax more difficult by blurring the apparent positions of stars and introducing additional sources of error. Second, they led astronomers to believe that stellar parallaxes should be larger than they actually were, based on distance estimates derived from the apparent disk sizes. And when these predicted parallaxes failed to appear, some observers concluded that they must have made errors in their measurements or that the Copernican system was not correct after all. The truth was that the stars were much more distant than the spurious disk suggested, and that the parallaxes were correspondingly much smaller than anyone expected. But this truth would not be fully appreciated until the 19th century, when better telescopes and better understanding of optics finally dispelled the illusion. The decades following Galileo's death in 1642 and Kepler's death in 1630 saw continued efforts to detect stellar parallax, but these efforts were hampered by the same fundamental limitations that had frustrated the earlier pioneers. Telescopes improved gradually, with longer focal lengths and better quality lenses, but the spurious stellar disks persisted, and the precision of angular measurement remained insufficient to detect the tiny shifts produced by the Earth's orbital motion. Astronomers proposed various methods and claimed various successes, but none of these early claims withstood scrutiny, and the parallax of the stars remained an unsolved problem, a promise of the Copernican system that had not yet been fulfilled. And so the first promise of the telescope, that it might reveal the parallax of the stars and thereby prove the motion of the Earth, remained unfulfilled through the remainder of the 17th century and well into the 18th. The instrument had shown many wonders, had revealed the moons of Jupiter and the phases of Venus, had resolved the Milky Way into countless stars and shown the rough surface of the Moon, but it had not yet delivered the crucial measurement that Galileo and Kepler had sought. That measurement would require not only better instruments but better understanding of the instruments themselves, a recognition that the disks seen around stars were illusions rather than realities, and a willingness to search for signals far smaller than anyone in the early 17th century had imagined possible. In the quiet rooms of Gresham College, London, during the year 1669, a remarkable instrument began to take shape under the careful hands of Robert Hooke, a man whose curiosity seemed to extend into every corner of natural philosophy then known to human inquiry. Hooke was already celebrated for his work with microscopes, for his observations of the tiny structures within cork that he had named cells, and for his contributions to the understanding of springs and elasticity. But in these particular months his attention turned upward, toward the fixed stars, and toward a question that had troubled astronomers since Copernicus first placed the Earth in motion around the Sun more than a century before. The question, as you may recall from our earlier discussion, was whether anyone could detect the subtle shift in stellar positions that would confirm, through direct geometric observation, that our planet truly moves through the vastness of space during its yearly journey. The instrument that Hooke designed for this purpose was unlike most telescopes of his era, for rather than pointing toward the horizon or tracking objects as they arced across the sky, this telescope was fixed in position, aimed directly upward at the zenith, that point in the heavens situated exactly overhead. To accommodate this unusual orientation, Hooke made modifications to his living quarters at Gresham College that might strike us today as rather dramatic, for he cut openings through the floors and roof of his rooms, allowing a long tube to pass vertically through the building so that starlight from directly above could travel down its length to an eyepiece positioned at a comfortable height for observation. The telescope itself was approximately 36 feet in length, a considerable instrument for its time, and it was anchored firmly to the structure of the building to prevent any movement that might introduce errors into the delicate measurements Hooke hoped to make. The choice to observe stars at or very near the zenith was a thoughtful one, rooted in Hooke's understanding of a persistent problem that had plagued astronomical measurement since ancient times, namely the bending of starlight as it passes through the atmosphere that surrounds our world. When light from a distant star enters the Earth's atmosphere at an angle, it encounters air of varying density, thinner at great heights and progressively denser as it approaches the ground, and this gradient causes the light to curve gently toward the vertical, much as a stick appears to bend when partially submerged in water. The result is that stars appear slightly higher in the sky than their true geometric positions would suggest, and the amount of this displacement, which astronomers call atmospheric refraction, varies depending on the angle at which the starlight enters the atmosphere and also upon the temperature and pressure of the air itself, which change from hour to hour and from season to season. For stars observed near the horizon, where light must traverse a great thickness of atmosphere at a shallow angle, this refraction can shift the apparent position by more than half a degree, a substantial quantity that early astronomers found difficult to correct with any precision. But for stars observed at the zenith, where light travels straight down through the atmosphere along the shortest possible path and enters nearly perpendicular to the atmospheric layers, the refraction is at its minimum, amounting to very little displacement indeed. Hooke understood that if he wished to detect the tiny annual shift of parallax, which he suspected might amount to only a small fraction of a degree, he would need to eliminate or at least greatly reduce every source of error that might mask or mimic the effect he sought. And zenith observation offered a way to set aside the troublesome variable of atmospheric refraction almost entirely. The star that Hooke selected for his observations was Gamma Draconis, a moderately bright star in the constellation of the Dragon that passes almost directly through the zenith as seen from London's latitude. This fortuitous geometry meant that Hooke could observe the star under the most favorable conditions possible, with minimal refraction and with the telescope firmly fixed in a single position, eliminating the need for the complex mechanical adjustments that introduced their own uncertainties into measurements made with movable instruments. Over the course of 1669 and the years that followed, Hooke made repeated observations of Gamma Draconis, carefully noting any changes in its position relative to the crosshairs in his eyepiece and recording the dates and times of each measurement. In 1674, Hooke published his findings in a work titled An Attempt to Prove the Motion of the Earth from Observations, a modest and carefully worded title that nonetheless announced an ambitious goal. Within this publication, Hooke reported that he had detected a shift in the position of Gamma Draconis over the course of his observations, a displacement that he measured as approximately 27 arcseconds. An arcsecond, as we have noted before, is a very small unit of angular measurement, representing 1/3600th of a degree, and to claim a detection of 27 arcseconds was to claim a measurement of considerable precision for the instruments of that era. Hooke interpreted this shift as evidence of stellar parallax, and therefore as proof that the Earth truly moves around the Sun, just as Copernicus and his followers had maintained. The publication was received with interest by the community of natural philosophers. For Hooke was a respected figure and the question he addressed was one of fundamental importance. However, the reception was not without skepticism, for other astronomers recognized the extreme difficulty of the measurements Hooke had attempted and the many sources of error that might have influenced his results. The 27 arcseconds that Hooke reported was, in fact, far larger than the true parallax of Gamma Draconis, which we now know to be only about 21 thousandths of an arcsecond, a quantity far too small for any instrument of the 17th century to detect. What Hooke had actually observed remains a matter of some historical uncertainty, though it seems likely that his measurements were affected by small movements of his telescope, by thermal expansion and contraction of the materials from which it was made, or by some other systematic error that he was unable to recognize or correct. Despite the fact that Hooke's claimed detection would later be disproven, his work represented an important step forward in the quest to measure stellar parallax. He had demonstrated a sound methodology, identifying the zenith telescope as a promising approach and selecting a suitable target star. He had recognized the importance of minimizing atmospheric refraction and had designed an instrument specifically suited to this purpose. And he had published his methods and results openly, allowing others to examine his reasoning and to attempt improvements upon his technique. In this way, Hooke contributed to the gradual accumulation of knowledge and experience that would eventually lead, more than a century and a half later, to the first successful parallax measurements. The year following Hooke's publication, 1675, brought a development of lasting significance for British astronomy, with the appointment of John Flamsteed to a newly created position that would come to be known as the Astronomer Royal. Flamsteed was a young man of 30 when he received this appointment, already known for his careful astronomical observations and for his skill in mathematical calculation. King Charles II had been persuaded of the need for accurate stellar positions to aid in the determination of longitude at sea, a problem of great practical importance for navigation, and the establishment of a royal observatory was proposed as a means to this end. The site selected for this observatory was a hill in Greenwich, just to the east of London, where a small castle or tower had once stood, and here the Royal Observatory began to take shape under the direction of Christopher Wren, with Flamsteed installed as its first occupant and principal observer. The early years at Greenwich were marked by difficulties of many kinds. Funding was limited, and Flamsteed found himself obliged to supply many of his own instruments and to employ assistants at his own expense. The building itself was constructed with more attention to architectural elegance than to astronomical utility, and Flamsteed would later complain that it had been designed more for show than for the serious work of observation. Nevertheless, he set about his task with determination, beginning a program of systematic stellar observation that would continue for more than 40 years and would result in the most comprehensive and accurate catalogue of stellar positions yet produced. The principal instrument that Flamsteed employed for this work was a device known as a mural arc, a large graduated arc mounted against a wall aligned precisely with the meridian, the imaginary line running from north to south through the zenith. As stars crossed the meridian each night, Flamsteed would observe them through a telescope attached to the arc and note their positions against the graduated scale, recording the altitude of each star above the horizon at the moment of its transit. By combining these altitude measurements with precise timing of the transit, he could determine both the declination and the right ascension of each star, the two coordinates needed to specify its position on the celestial sphere. This method of meridian observation had been used before, but Flamsteed brought to it a level of care and systematic attention that set a new standard for positional astronomy. Over the decades that followed, Flamsteed accumulated thousands upon thousands of observations, gradually building a catalogue that would eventually include the positions of nearly 3,000 stars, each one measured multiple times under varying conditions and carefully reduced to account for the known effects of precession, nutation, and aberration. The work was painstaking and slow, For Flamsteed insisted on checking and rechecking his results, refusing to publish until he was satisfied that his catalogue met the highest standards of accuracy he could achieve. This deliberate pace brought him into conflict with others who wished to make use of his data, most notably Isaac Newton, who needed accurate stellar positions for his work on the theory of the moon and on the broader problem of celestial mechanics. The conflict between Flamsteed and Newton was protracted and bitter, extending over many years and involving accusations, legal disputes, and mutual recriminations that cast a shadow over the final decades of Flamsteed's life. Newton, impatient for data that he considered essential to his work, arranged in 1712 for the publication of a preliminary version of Flamsteed's catalogue without the astronomer's consent, a pirated edition that Flamsteed regarded as incomplete and inaccurate. Flamsteed was furious at this violation of what he considered his intellectual property and his right to control the presentation of his own work, and he managed eventually to obtain and destroy most of the copies of the unauthorized edition. The definitive version of his catalogue, the Historia Celestis Britannica, was not published until 1725, 6 years after Flamsteed's death, and it stands as a monument to his lifetime of careful observation. Among the many contributions that Flamsteed made to astronomy, one of particular relevance to our present subject was his effort to estimate the upper limit of stellar parallax based on his measurements. Flamsteed understood that if stars displayed any annual parallactic shift, this shift would appear in his observations as a systematic variation in stellar positions over the course of the year, and he looked carefully for any such effect in his data. He found none that he could confidently attribute to parallax, and from this absence he concluded that the parallax of the stars he observed must be smaller than the precision of his instruments could detect. His estimates suggested that stellar parallax, if it existed at all, must be less than 10 arcseconds for the stars he measured, a significant constraint that pushed the minimum distance to the stars ever further into the depths of space. This null result, while perhaps disappointing to those who hoped for direct proof of the Earth's motion, was itself a valuable contribution to astronomical knowledge. It demonstrated that the stars must be enormously distant, far more distant than even the most generous estimates of earlier astronomers had suggested, and it set a benchmark against which future observers could measure their own efforts. If parallax was to be detected, instruments of greater precision would be needed, and observers would have to find ways to reduce or eliminate sources of error that Flamsteed, for all his care, had been unable to overcome. The mural arc that Flamsteed employed, and the systematic approach he brought to its use, represented a significant advance in observational technique. Earlier astronomers had often relied on isolated observations, made opportunistically when conditions seemed favorable, but Flamsteed understood that accuracy could only be achieved through repetition and consistency. By observing the same stars night after night, season after season, year after year, he could average out the random errors that affected any single observation and could identify and correct for systematic effects that might otherwise go unnoticed. This methodical approach, which might seem obvious to us today, was not yet standard practice in Flamsteed's time, and his insistence upon it helped to establish the norms that would guide precision astronomy for generations to come. As we leave Flamsteed at his work in Greenwich, meticulously recording the positions of stars as they crossed his meridian, and as we leave Hooke with his zenith telescope and his disputed claim of parallax detection, we may reflect on the state of the quest as the 17th century drew toward its close. The theoretical framework for understanding parallax was well established, the geometry was clear, and the significance of a successful detection was widely appreciated. What was lacking was the instrumental precision and the observational technique needed to measure shifts of position so small that they approached the very limits of human perception. The parallax of even the nearest stars, as we now know, amounts to less than 1 arcsecond, and to measure such a quantity reliably would require advances in telescope design, in the manufacture of graduated scales and micrometers, and in the understanding and correction of all the subtle effects that could introduce spurious shifts into positional measurements. These advances would come, but they would come slowly, through the cumulative efforts of many observers working over many decades. Hooke and Flamsteed had shown what could be attempted with the instruments of their time and had demonstrated both the promise and the limitations of the methods available to them. The next generation of astronomers would build upon their work, refining their techniques and pushing the boundaries of measurement ever further, until at last the elusive parallax of the stars would yield its secrets to patient observation. But that story belongs to a later chapter in our account, and for now we may rest with the knowledge that the foundations had been laid, the groundwork prepared, and the quest was well begun. In the year 1725, a quiet partnership formed between two men who shared a common curiosity about the heavens and a determination to settle, once and for all, the question of whether the stars revealed any measurable parallax. James Bradley was at that time a young astronomer of considerable promise, holding the civilian chair of astronomy at Oxford, though he spent much of his time pursuing observational work rather than lecturing. Samuel Molyneux was a wealthy amateur, a member of Parliament with scientific interests and, most importantly for our story, the owner of a fine house at Kew, just outside London, where he had the means and the space to install a rather remarkable instrument. The two men had known each other for some years, and they shared a conviction that the failure of previous astronomers to detect stellar parallax was not proof that the Earth stood still, but rather evidence that the instruments used had simply not been precise enough for the task. They believed that with sufficient care, with a telescope of adequate length, and with a method designed to eliminate the errors that had plagued earlier attempts, they might finally succeed where Hooke and Flamsteed and so many others had fallen short. The instrument they chose to employ was a zenith sector, which is a type of telescope designed specifically to observe stars that pass very nearly overhead, through that point in the sky called the zenith. There were good reasons for this choice, and they are worth understanding because they speak to the careful thinking that Bradley and Molyneux brought to their enterprise. When you observe a star that passes directly overhead, or very close to it, you avoid many of the complications that arise when observing stars lower in the sky. The atmosphere through which the starlight must travel is at its thinnest when you look straight up, and the bending of light caused by atmospheric refraction, which we discussed earlier in connection with the difficulties faced by astronomers of the 17th century, is at its minimum. Furthermore, a zenith sector could be mounted in a fixed position, attached rigidly to a chimney or a wall, which meant that it was not subject to the flexing and shifting that occurred with telescopes mounted on movable stands. The instrument would always point in the same direction relative to the building, and by measuring tiny changes in where a star appeared within the field of view, one could detect correspondingly tiny changes in the star's position on the sky. The zenith sector that Molyneux commissioned for this work was built by George Graham, who was among the finest instrument makers in England and perhaps in all of Europe at that time. Graham was a clockmaker by trade, celebrated for his precision mechanisms, and he brought to the construction of astronomical instruments the same meticulous attention to detail that he applied to his timepieces. The telescope he produced for Molyneux had a focal length of 24.5 feet, which is to say that the distance from the main lens at the top to the eyepiece at the bottom was nearly 8 meters. This great length was necessary to achieve the magnification and the precision of measurement that the project required. The instrument was installed in Molyneux's house at Kew, passing vertically through an opening cut in the roof so that it could observe stars as they crossed the meridian near the zenith. A graduated arc near the eyepiece allowed the observer to read off the angle at which the star appeared, and the divisions on this arc were fine enough to permit measurements to a fraction of an arcsecond, which was an extraordinary level of precision for the time. The star they selected for their primary observations was Gamma Draconis, a moderately bright star in the constellation of the Dragon. This choice too was deliberate and well considered. Gamma Draconis passes almost exactly through the zenith as seen from London, which made it ideal for observation with a fixed zenith sector. It is bright enough to be easily visible through the telescope, and it was known from earlier catalogues to be a star of relatively simple behavior, without the complications that might arise from observing a double star or a variable star. Bradley and Molyneux reasoned that if parallax existed, they had as good a chance of detecting it with Gamma Draconis as with any other star. The observations began in earnest in December of 1725, and they continued through the following months with the regularity and patience that characterize all good astronomical work. Night after night, when the weather permitted and the star was suitably placed, one or the other of the two astronomers would take readings, noting the precise angle at which Gamma Draconis appeared in the zenith sector. They accumulated a growing collection of measurements, each one recorded carefully in their notebooks, and as the weeks passed and the data accumulated, a pattern began to emerge. Gamma Draconis was not remaining fixed in position. Its apparent place in the sky was shifting, slowly but unmistakably, by an amount that was easily large enough to be detected with their instrument. This was, in one sense, exactly what they had hoped to find. A shift in the star's position over the course of the year would be precisely the signature of parallax, the tiny wobble that would prove the Earth was moving around the Sun. But as Bradley examined the measurements more closely, he realized that something was wrong. The shift was there, certainly, and it was surprisingly large, amounting to roughly 40 arcseconds over the course of a year, which was far greater than anyone had expected. Yet the direction of the shift was not what parallax would produce. If the Earth's motion around the Sun were causing the star to appear to wobble back and forth against the background of more distant objects, then the wobble should reach its extreme positions at certain predictable times of the year, corresponding to the points where the Earth's position in its orbit placed it at maximum displacement relative to the line of sight to the star. But the times at which Gamma Draconis reached its extreme positions did not match this prediction. The shift was reaching its maximum and minimum values about 3 months out of phase with where parallax would place them. This was deeply puzzling. The observations themselves seemed sound. Graham's instrument was performing beautifully, giving consistent readings night after night, and there was no indication of any systematic error that might explain the discrepancy. The shift was real. Bradley was certain of that, but it was not parallax. Something else was happening, something that no astronomer had anticipated. Samuel Molyneux died in April of 1728, before the mystery could be solved, and the work fell to Bradley alone to continue. He commissioned a second zenith sector, this one installed at the house of his aunt at Wanstead in Essex, and he expanded his observations to include other stars near the zenith, hoping that by comparing the behavior of different stars, he might find some clue to the nature of the effect he was observing. The new data confirmed what he had already seen with Gamma Draconis. All the stars showed the same kind of annual shift, all of them with the same curious phase relationship that could not be explained by parallax. The breakthrough came during a boat trip on the River Thames, sometime in the autumn of 1728. Bradley was travelling by boat, as one often did in that era when the roads around London were poor and the river provided a convenient highway. And as the boat moved along the water, he noticed something about the behavior of the pennant or small flag that flew from the mast. When the boat was stationary, the pennant streamed in the direction from which the wind was blowing. But when the boat was moving, the pennant shifted its direction, pointing somewhere between the direction of the wind and the direction opposite to the boat's motion. The faster the boat moved, the greater this shift became. The apparent direction of the wind, as shown by the pennant, was a combination of the true wind direction and the motion of the boat itself. This observation sparked a connection in Bradley's mind. He realized that the same principle might apply to light coming from the stars. Light, he knew, traveled at a finite speed. This had been demonstrated some 50 years earlier by the Danish astronomer Ole Romer, who had deduced from observations of the moons of Jupiter that light took a measurable amount of time to cross the diameter of Earth's orbit. If light had a finite speed, and if the Earth was moving through space as it orbited the Sun, then the direction from which starlight appeared to come would be affected by the combination of these two motions, just as the apparent direction of the wind was affected by the motion of the boat. The Earth was like the boat, the starlight was like the wind, and the apparent position of the star was like the direction of the pennant. This phenomenon, which Bradley came to call the aberration of light, would produce exactly the kind of annual shift that he had been observing. When the Earth was moving toward a star, the star would appear to be shifted slightly forward, in the direction of the Earth's motion. When the Earth was moving away, the star would appear to be shifted backward. And because the Earth's velocity is always perpendicular to the line joining it to the Sun, the timing of these shifts would be exactly what Bradley had observed, with the maximum displacement occurring 3 months after the point where parallax would predict it. Bradley presented his findings to the Royal Society in January of 1729, in a paper that carefully described his observations and explained the theory of aberration that accounted for them. The reception was enthusiastic, for his explanation was elegant and convincing, and it resolved a puzzle that had no other obvious solution. More than that, it provided a new and independent confirmation that the Earth was indeed moving through space, orbiting the Sun as Copernicus had proposed 2 centuries earlier. The aberration of starlight could only occur if the Earth had a velocity, if it was actually traveling through space rather than sitting motionless at the center of the universe. For those who still harbored doubts about the Copernican system, Bradley's discovery was a powerful piece of evidence against them. Bradley's observations also allowed him to calculate the speed of light, using the known velocity of the Earth in its orbit and the measured amount of aberration. The maximum aberration he observed was about 20¼ arcseconds, which when combined with the orbital velocity of the Earth, around 18½ miles per second, gave a speed of light of approximately 183,000 miles per second. This figure was remarkably close to the true value, within about 2% of what we now know the speed of light to be. It was a beautiful demonstration of the interconnectedness of physical phenomena, showing how observations of star positions could be used to measure something as fundamental as the speed at which light travels. Yet for all its importance, the discovery of aberration was in one sense a disappointment. Bradley had set out to measure stellar parallax, and in that aim he had failed. The shift he had detected was not the signature of the Earth's changing position in its orbit, but rather the signature of the Earth's velocity, its motion through space at any given moment. Parallax remained undetected. The aberration of light was a much larger effect than parallax, amounting to some 40 arcseconds in total amplitude, and it had been discovered first precisely because it was large enough to measure with the instruments of the day. But parallax, the effect that Bradley and Molyneux had originally sought, was still too small to see. What Bradley's work demonstrated, however, was just how small parallax must be. His observations were precise enough to detect the aberration effect, which meant that any parallax effect larger than about 1 arcsecond would certainly have been noticed as well. The fact that no parallax was detected alongside the aberration meant that even the nearest stars must be so distant that their parallax was less than 1 arcsecond. This placed a lower limit on the distances to the stars, showing that they must lie at least 200,000 times farther from the Sun than the Earth does. The stellar realm was revealed to be vaster than most people had imagined, a finding that was both humbling and inspiring. Bradley continued his astronomical work for many more years, eventually succeeding Edmund Halley as Astronomer Royal in 1742. He made many other important contributions to the science, including the discovery of a second small motion in the apparent positions of the stars, called nutation, which is caused by a slow wobbling of the Earth's axis of rotation. But the discovery of aberration remained his most celebrated achievement, a piece of work that demonstrated both his observational skill and his theoretical insight. He had gone looking for one phenomenon and found another, but in doing so he had advanced human understanding in ways he could not have anticipated. The story of James Bradley and the aberration of light is in many ways a story about the unexpected paths that scientific discovery can take. Bradley and Molyneux began with a clear goal: to measure stellar parallax and thereby confirm the motion of the Earth, and they pursued that goal with admirable diligence and carefully designed instruments. What they found was something quite different, a phenomenon that no one had predicted, arising from the combination of the Earth's motion and the finite speed of light. This discovery was in its own way just as significant as the parallax measurement would have been, and it led to important advances in both astronomy and physics. But it also meant that the original goal remained unachieved, the prize of parallax still waiting for some future astronomer with still more precise instruments. In the decades that followed Bradley's work, the quest for stellar parallax continued, though with a heightened appreciation for just how difficult the task would be. The discovery of aberration had shown that the stars were immensely far away, their parallaxes probably amounting to no more than a fraction of an arcsecond, at the very limit of what the instruments of the time could possibly detect. It would take more than a century of further development in telescope design, in measurement techniques, and in the understanding of systematic errors before that final breakthrough would come. But Bradley's work had set the stage, demonstrating what could be achieved with careful observation and establishing the standard of precision that future parallax hunters would need to surpass. His accidental discovery of aberration was a milestone on the long road to measuring the stars, a reminder that in science, the journey itself often yields treasures that the traveler never expected to find. And so we find ourselves continuing along this quiet thread of astronomical history, where James Bradley, having already transformed our understanding of starlight through his discovery of aberration, now turned his patient attention to yet another subtle dance of the heavens, another gentle wobble that would require nearly 2 decades of careful watching before it revealed its true nature to him. You may recall that Bradley had been observing the star Gamma Draconis with his zenith sector, that long and slender telescope pointed almost directly overhead, and that in doing so he had noticed the curious elliptical wandering of stars across the sky that we now call stellar aberration. But Bradley was not the sort of man to declare victory and move on to other pursuits. He continued watching, night after night, season after season, because the numbers were not quite settling into the neat patterns he expected, and there was something else moving beneath the surface of his data, something smaller and slower and more elusive than aberration, something that would require extraordinary patience to tease apart from all the other motions of the celestial sphere. The aberration effect, you see, traces out its ellipse over the course of a single year, tied as it is to the Earth's journey around the Sun. Bradley had mapped this motion with great precision, and he could now account for it in his observations, subtracting away its influence to see what lay beneath. But when he did so, the stars still did not sit perfectly still. There remained a small additional wandering, a gentle nodding motion that seemed to operate on a much longer timescale than the annual aberration, and Bradley suspected that this too must have some physical cause rooted in the mechanics of our Earth and its relationship with its celestial companions. He began his systematic investigation of this new phenomenon around 1727 or 1728, shortly after his aberration discovery became clear to him, and he would continue observing and recording and calculating for roughly 18 years before he felt confident enough to announce his findings to the world. 18 years of looking upward, 18 years of careful measurement, 18 years of watching the stars trace out patterns so subtle that most observers would never have noticed them at all. This is the tempo of precision astronomy, unhurried and methodical, and there is something rather soothing in contemplating such dedication to the gradual accumulation of knowledge. What Bradley eventually discovered, and what he announced to the Royal Society in the year 1748, was a phenomenon he called nutation, from the Latin word nutar, meaning to nod or to sway. He had found that the Earth's axis does not simply precess in a smooth and stately cone over its 26,000-year cycle, as astronomers had long known, but rather it wobbles slightly as it goes, nodding gently back and forth like a spinning top that has been given a small periodic nudge. This nutation, Bradley determined, has an amplitude of approximately 9.2 arcseconds, which is to say that the celestial pole wanders in a small ellipse with a semi-major axis of this size, and it completes one full cycle of this nodding motion every 18.6 years or so. Now, 18.6 years is a rather specific and curious period, and Bradley recognized that it must correspond to something physical, some astronomical cycle that operates on this same timescale. The answer, he determined, lay with the Moon and the peculiar geometry of its orbit around our Earth. The Moon does not orbit in the same plane as the Earth's equator, nor does it orbit precisely in the plane of the ecliptic, that imaginary surface on which the Earth travels around the Sun. Instead, the Moon's orbital plane is tilted by about 5 degrees with respect to the ecliptic, and this plane itself rotates slowly over time, completing one full rotation in approximately 18.6 years. This is the lunar nodal cycle, the time it takes for the points where the Moon's orbit crosses the ecliptic to travel all the way around the sky and return to their starting positions. The gravitational pull of the Moon on the Earth's equatorial bulge, that slight flattening of our planet caused by its rotation, is the ultimate source of both precession and nutation. The Moon tugs on this bulge, trying to pull the Earth's equator into alignment with the orbital planes, and this produces the slow wobble of precession. But because the Moon's own orbit is inclined and because this inclination varies as the nodes regress around the ecliptic, the strength and direction of this lunar pull changes in a periodic fashion, and this produces the additional wobble of nutation superimposed on top of the longer precession. Bradley worked all of this out with great care, combining his observational data with the gravitational theory that had been developed by Newton and refined by subsequent mathematicians. He showed that the nutation could be understood as a natural consequence of lunar mechanics, and he provided the astronomical community with the corrections necessary to account for this effect when reducing their observations. It was a triumph of patient observation married to theoretical understanding, and it established Bradley as perhaps the most accomplished observational astronomer of his generation. By the time Bradley announced his discovery of nutation in 1748, he had already held the position of Astronomer Royal for 6 years, having been appointed to this prestigious post in the year 1742 upon the death of his predecessor, Edmund Halley. The Astronomer Royal was responsible for the Royal Observatory at Greenwich, that institution founded in 1675 to provide accurate astronomical data for the improvement of navigation, and Bradley took his duties there with the same systematic dedication he had brought to his earlier work at Wanstead. When Bradley arrived at Greenwich, he found the observatory in a somewhat neglected state. Halley had been an energetic and brilliant astronomer in his youth, the man who had befriended Newton and financed the publication of the Principia, who had catalogued southern stars from the island of St. Helena, who had predicted the return of the comet that now bears his name. But Halley had been 85 years old when he died, and the observatory had suffered from his advanced age and declining health in his final years. The instruments were aging, the records were incomplete, and much work needed to be done to restore Greenwich to its proper function as the premier astronomical institution of Britain. Bradley set about this task with characteristic thoroughness. He obtained new instruments, including an improved transit telescope and a mural quadrant of exceptional quality, and he established rigorous observational routines that would provide a continuous record of stellar positions. Over the course of his tenure as Astronomer Royal, which lasted until his death in 1762, Bradley accumulated observations of some 3,222 stars, recording their positions with a precision that far exceeded anything that had come before. These observations, which became known simply as the Bradley observations, established a new gold standard for positional astronomy. Bradley understood, perhaps better than anyone before him, all of the various effects that must be accounted for when determining the true position of a star. There was atmospheric refraction, which bends starlight as it passes through our air and makes stars appear slightly higher in the sky than they actually are. There was precession, the slow drift of the coordinate system itself as the Earth's axis wheels through space. There was aberration, that discovery of his own that showed how the Earth's motion causes starlight to appear shifted in the direction of travel. And now there was nutation, adding yet another layer of complexity to the conversion between observed and true positions. Bradley applied all of these corrections systematically, and his reduced star positions were so accurate that they remained useful for more than a century after his death. Later astronomers would return to the Bradley observations again and again, using them as a reference point for detecting the proper motions of stars over decades and centuries. The data he gathered at Greenwich formed a foundation upon which subsequent generations would build, and his methods set the pattern for all precision astrometry that followed. It is worth pausing here to appreciate what Bradley had accomplished in human terms. He had spent decades looking upward, recording tiny angular measurements, correcting for known effects, searching for patterns in the residuals. He had discovered not one but two fundamental phenomena of positional astronomy, aberration and nutation, and he had provided the theoretical explanations for both. He had transformed Greenwich into a model institution and created a body of observations that would remain valuable for generations. All of this required not genius alone, though Bradley certainly possessed that quality, but also patience and dedication and an almost monastic commitment to the slow accumulation of precise data. Bradley's discoveries did not go unnoticed on the continent. Other astronomers were making their own careful observations, and some of them were able to confirm his findings independently. Among these was Tobias Meyer, a German astronomer working at the University of Göttingen, who conducted his own investigation of nutation using observations made from that city in the years following Bradley's announcement. Meyer was a careful observer and a skilled mathematician, and his independent confirmation added weight to Bradley's claims while also helping to refine the precise parameters of the nutational wobble. Meyer went on to produce lunar tables of exceptional accuracy, using his understanding of nutation and other effects to predict the Moon's position with sufficient precision to be useful for determining longitude at sea. This was the great practical problem of the age: finding a reliable method for sailors to determine their east-west position on the trackless ocean, and Meyer's tables represented one of the most successful astronomical approaches to the longitude problem. The British Board of Longitude eventually awarded a substantial prize to Meyer's widow in recognition of this work, and his contributions to precision astronomy helped establish Göttingen as one of the leading centers of astronomical research in Europe. The combined effect of Bradley's discoveries was to demonstrate just how difficult the detection of stellar parallax would be. Before Bradley, astronomers had been searching for parallax effects on the order of several arcseconds or more, and they had failed to find them. Now it was clear that any true parallax must be smaller than the effects of aberration and nutation, both of which had been hiding in the data all along, masquerading as the very parallax that astronomers sought. Aberration has a maximum amplitude of about 20.5 arcseconds, which is to say that a star can appear shifted by this amount from its true position due to the Earth's orbital motion. Nutation has an amplitude of about 9.2 arcseconds, adding its own contribution to the apparent wandering of stars. Both of these effects had to be understood and corrected for before any hope remained of detecting the much smaller parallax signal that would reveal stellar distances. And the fact that no parallax had been detected despite decades of careful observation by Bradley and others meant that stellar parallax must be quite small indeed. The consensus that emerged from Bradley's work was that parallax must be less than about half an arcsecond, perhaps much less, for even the nearest stars. This placed a lower limit on stellar distances that pushed them to scales almost beyond comprehension. If the nearest stars have parallaxes of less than half an arcsecond, then they must lie at distances of more than 200,000 times the distance from the Earth to the Sun. In modern terms, this corresponds to distances of several light-years at minimum, meaning that the light we see from these stars has been traveling through space for years before reaching our eyes. The stars were not merely far away in the sense of being difficult to reach. They were separated from us by gulfs of emptiness so vast that light itself, traveling at the unimaginable speed of 186,000 miles per second, required years to cross them. This was a profound realization, though it emerged gradually rather than all at once. Each improvement in observational precision, each new correction factor discovered and applied, each null result in the search for parallax, pushed the stars further away and made the universe larger. The comfortable celestial sphere of antiquity, with its fixed stars arranged on a crystalline vault not terribly far beyond Saturn, had given way to a cosmos of staggering dimensions, and the process was not yet complete. Bradley died in the year 1762, having spent his final years troubled by illness and by disputes over the ownership of his observational records. He left behind a legacy of precision and care that would guide astronomical practice for generations, and he had set the stage for the eventual detection of stellar parallax by showing exactly what obstacles lay in the path and what level of precision would be required to overcome them. The aberration correction, the nutation correction, the improved instruments, the systematic methods, all of these would be essential tools for those who came after. The search for parallax would continue through the late 18th century and into the 19th, as new generations of astronomers took up the challenge with ever more refined instruments and ever greater patience. They knew, thanks to Bradley, that the effect they sought was tiny, less than an arcsecond and perhaps far less, hidden beneath layers of atmospheric effects and instrumental errors and the subtle wanderings of the Earth itself. They knew that success would require not only technical skill but also the kind of dedicated persistence that Bradley had exemplified throughout his long career. And so we leave James Bradley here, his work complete, his discoveries secure, his observations forming a foundation for all that would follow. The stars continued their apparent dance across the sky, tracing out their aberrational ellipses and their nutational nods, and somewhere beneath all of these motions, invisible as yet to human instruments, the tiny parallax shifts waited to be found, promising at last to reveal the true scale of the stellar realm. But that discovery would not come for many decades yet, and there is no need to hurry toward it. The stars are patient, and so may we be, resting here for a while in the gentle certainty that the universe keeps its secrets well, revealing them only to those with the dedication to watch and wait and measure, night after quiet night. In the year 1757, a young German musician named Friedrich Wilhelm Herschel made the crossing from Hanover to England, carrying with him little more than his oboe, his modest savings, and whatever quiet ambitions stirred within him during the long sea voyage. He was just 19 years old at the time, the son of a military bandsman who had encouraged his children to pursue music with some seriousness, and young Wilhelm had already served briefly as an oboist in the Hanoverian Guards before deciding that England might offer better prospects for a musician of his abilities. The journey itself was unremarkable in most respects, the sort of emigration that thousands of Germans undertook during that century, seeking employment in a country whose royal house maintained close ties to Hanover through the succession of King George I some decades earlier. Wilhelm anglicized his name to William upon arrival, as many immigrants did, and set about establishing himself in a musical career that would eventually lead him to positions as organist, music teacher, and conductor in various English towns, including Leeds and Halifax, before he finally settled in the spa city of Bath in 1766. Bath was at that time a fashionable resort where the English gentry came to take the waters and enjoy the social season, and a skilled musician could find steady employment providing entertainment for the assembled company. William Herschel became the organist at the Octagon Chapel and directed public concerts, earning a comfortable living and bringing his sister Caroline over from Hanover to assist him and to pursue her own career as a singer. The Herschels were a close family despite the distances that circumstances had imposed upon them, and Caroline would eventually become her brother's indispensable partner in astronomical work, though neither of them could have predicted such a future during those early years in Bath when music occupied nearly all their waking hours. It was during this period of relative prosperity and stability that William Herschel began to develop what would prove to be an all-consuming interest in astronomy, sparked initially by his purchase of some books on optics and harmonics that led him naturally toward questions about the construction of telescopes and the nature of light itself. The connection between music and astronomy may seem tenuous to us today. Yet Herschel himself would not have found it strange at all, for both disciplines in the 18th century were understood to involve mathematical relationships and the investigation of natural harmonies, and a mind trained to perceive patterns in one domain might readily apply itself to the other. By the early 1770s, Herschel had begun constructing his own reflecting telescopes, grinding and polishing the specular metal mirrors himself with a patience and precision that would eventually make him the foremost telescope builder of his age. The work was physically demanding and often tedious, requiring hours of careful polishing to achieve the parabolic curvature necessary for bringing starlight to a sharp focus. And Herschel would later recall sessions lasting 16 hours or more during which Caroline would read aloud to him or place food directly into his mouth so that he need not interrupt the rhythmic motions of his polishing strokes. The instruments he produced grew steadily larger and more powerful, surpassing in quality anything that could be purchased from commercial opticians. And by the late 1770s Herschel was conducting systematic surveys of the heavens with a thoroughness that few observers had ever attempted. It was during one such survey, on the night of the 13th of March in 1781, that William Herschel noticed an object in the constellation Gemini that did not appear quite star-like through his telescope. The disk was slightly fuzzy at the edges, suggesting either a nebula or perhaps a comet, and Herschel initially announced it as a comet in his report to the Royal Society. Other astronomers soon calculated the object's orbit, however, and found that it moved in a nearly circular path at a vast distance from the Sun, far beyond the orbit of Saturn, which meant that Herschel had not discovered a comet at all but rather a new planet, the first to be found since antiquity. The discovery brought Herschel instant fame throughout Europe and the patronage of King George III, who appointed him as the king's personal astronomer with an annual salary of £200, sufficient to allow Herschel to abandon his musical career entirely and devote himself fully to the study of the heavens. He named the new planet Georgium Sidus, or George's star, in honor of his patron, though astronomers on the continent preferred to call it Uranus after the ancient Greek god of the sky, and this latter name eventually prevailed in international usage. The royal patronage transformed Herschel's circumstances completely, enabling him to move from Bath to a location nearer to Windsor Castle so that he might demonstrate celestial wonders to the king and his court whenever requested, and more importantly allowing him to construct telescopes of unprecedented size and power. The king provided a substantial grant for the building of a great 40-foot telescope at Slough, a project that occupied several years and was not completed until 1789, resulting in an instrument whose main mirror measured 4 feet in diameter and whose tube stretched 40 feet in length, requiring an elaborate system of scaffolding and pulleys for its operation. The 40-foot telescope was in many respects more impressive as a feat of engineering than as a practical observing tool, for its enormous mirror was difficult to figure precisely and tarnished readily in the damp English air, requiring frequent repolishing that kept the instrument out of service for extended periods. Herschel's most productive observations were often made with smaller instruments of his own construction, particularly a 20-foot reflector that combined excellent optical quality with reasonable ease of use, and it was with telescopes of this more moderate size that he conducted his systematic surveys of double stars, nebulae, and the structure of the Milky Way. The investigation of double stars held particular interest for William Herschel because it offered what seemed to him a promising method for measuring stellar parallax, that elusive quantity which had defeated so many astronomers before him. His reasoning was characteristically practical and displayed the sort of lateral thinking that often distinguishes great observers from merely competent ones. Rather than attempting to measure the absolute parallax of a star against the distant background of the celestial sphere, which required angular measurements of almost impossible precision, Herschel proposed to measure the relative parallax between two stars that appeared very close together in the sky but were presumably at vastly different distances from the Earth. If one could identify pairs consisting of a bright star and a much fainter star lying nearly in the same direction, it seemed reasonable to assume that the bright star was relatively nearby while the faint star was immensely more distant, since stellar brightness ought generally to correlate with proximity, other things being equal. Herschel presented this method to the Royal Society in 1781. The same year he discovered Uranus, and explained its advantages with characteristic clarity in his paper. When the Earth moved from one side of its orbit to the other, a relatively nearby star should appear to shift its position slightly against the background of more distant stars, and if a faint star happened to lie almost exactly behind a bright star as seen from Earth, then the bright star would appear to move back and forth relative to the faint one as the year progressed. The angular separation between the two stars could be measured far more precisely than the absolute position of either star alone, because the measurement became a matter of detecting small changes in the gap between two objects seen simultaneously in the same field of view, rather than trying to determine positions against the entire celestial coordinate grid. It was an elegant idea, building on earlier suggestions by Galileo and others, but developed by Herschel into a systematic observational program that would occupy him intermittently for many years. To implement this method, Herschel needed first to identify a large number of suitable double star pairs, cataloguing their positions and the angular separations between their components so that any future changes could be detected by comparison with these baseline measurements. He threw himself into this task with the same methodical energy he brought to all his observational work, systematically sweeping the heavens with his excellent telescopes and recording every instance where two stars appeared close together in the field of view. The work was painstaking but well suited to Herschel's temperament, requiring sharp eyesight, steady attention, and the patience to repeat measurements many times to ensure their accuracy. Caroline Herschel assisted her brother throughout these surveys, recording his observations as he called them out from the eyepiece, keeping meticulous logs of dates and times and instrument settings, and performing the tedious calculations necessary to reduce the raw observations into useful catalogues. Between 1782 and 1784, William Herschel compiled a catalogue of 848 double stars, an unprecedented collection that dwarfed all previous attempts to enumerate such objects. Earlier astronomers had noted perhaps a few dozen close stellar pairs, but Herschel's systematic surveys revealed that double stars were far more common than anyone had suspected, scattered abundantly across the sky in every constellation and at every distance from the Milky Way central band. He published his first catalogue in 1782, followed by a second catalogue in 1785, and later supplemented these with additional discoveries that eventually brought his total count to over 2,500 pairs. Each entry recorded the positions of both stars, the angular distance between them measured in seconds of arc, the angle at which the fainter star lay relative to the brighter one, and various notes about the colors and magnitudes of the components, providing future astronomers with a rich data set for comparison. The double star catalogues were valuable in themselves as contributions to astronomical knowledge, But Herschel's original purpose had been to use them for parallax measurements, and he continued to monitor his pairs over the years, hoping to detect the telltale annual oscillation that would reveal the distance to the nearer component. What he found instead was something entirely unexpected and, in its own way, far more significant than the parallax he had sought. When he compared his measurements from the 1780s with new observations made in the 1790s and early 1800s, Herschel discovered that many of his double stars had indeed changed their configurations, but not in the manner that parallax would produce. Instead of oscillating back and forth with a yearly period, the components of numerous pairs showed steady progressive motions relative to one another, with the fainter star gradually revolving around the brighter one over periods of years or decades, tracing out what appeared to be elliptical orbital paths. This was an extraordinary finding, for it demonstrated that many of the pairs Herschel had catalogued were not merely optical doubles, chance alignments of unrelated stars at vastly different distances, but physical binaries, genuine stellar systems in which two suns orbited around their common center of mass under the influence of mutual gravitational attraction. The implications for physics were profound. Newton's law of universal gravitation had been formulated to explain motions within the solar system, where planets orbit the sun and moons orbit their planets according to precise mathematical rules. But it had remained an open question whether the same law governed the behavior of matter throughout the universe or was merely a local phenomenon applying only to our own cosmic neighborhood. Herschel's binary stars provided the first direct evidence that Newtonian gravity operated identically in the distant realms of the fixed stars, that the same inverse square law which held the Earth in its orbit also bound these remote suns together across interstellar space. Herschel published his analysis of binary star orbits in papers delivered to the Royal Society in 1793, 1802, and 1803, carefully documenting the orbital motions he had detected and discussing their implications for gravitational theory. The orbital periods he observed ranged from several decades to centuries, meaning that most binaries he discovered would require generations of continued observation before their orbits could be fully characterized. But the reality of the orbital motion itself was unmistakable in the clearest cases. The star Castor, one of the bright twins in the constellation Gemini, showed particularly convincing evidence of binary motion, as did several other pairs scattered across the sky. What had begun as a search for parallax had yielded instead a fundamental proof about the universality of physical law, transforming our understanding of the cosmos from a collection of isolated phenomena into a unified system governed everywhere by the same mathematical principles. The failure of the parallax search itself was instructive, however, for it placed meaningful constraints on how close even the nearest stars could possibly be. If the nearby stars in Herschel's double pairs had been only a few hundred or a few thousand times the Earth-Sun distance away, their annual parallactic shifts would have been easily detectable with his instruments, but no such shifts appeared in any of his measurements. This null result meant that even the closest stars must lie at distances vastly greater than the scale of the solar system, thousands upon thousands of times farther than the most distant planets. Herschel attempted to estimate just how far this might be by various indirect methods, including comparisons of stellar brightness with the brightness of the Sun and calculations based on the proper motions of stars across the sky, and he arrived at figures suggesting that the nearest stars lay at distances requiring light several years to traverse. The concept of the light year as a unit of astronomical distance was not yet standard terminology in Herschel's time, but his estimates placed the nearest stars at roughly the distance we would now describe as approximately 9 light-years. meaning that the light from these stars had been traveling through space for 9 years before reaching Herschel's eye at the telescope eyepiece. This figure was remarkably close to modern determinations of the distances to some of the nearer stars. Though Herschel had no way of knowing how accurate his estimates actually were without a direct parallax measurement to provide calibration. The true distances might have been somewhat greater or somewhat less than his calculations suggested, but the fundamental insight was sound. The stars were immensely far away, farther than any human being had previously comprehended, separated from our solar system by gulfs of empty space so vast that even light required years to cross them. The 40-foot telescope at Slough, despite its limitations for routine observing, contributed to Herschel's growing fame and attracted visitors from across Europe who wished to see this wonder of modern technology. The king himself came often, bringing members of the royal family and distinguished guests to peer through the eyepiece at Saturn's rings or the cloudy patches of distant nebulae. And these visits helped cement the public association between astronomy and enlightened royal patronage. The telescope's great mirror, when freshly polished and in good condition, could reveal fainter objects than any other instrument then in existence, and Herschel used it to discover 2 new moons of Saturn and 2 of Uranus, adding to his already considerable reputation as an explorer of the solar system. The instrument remained in use, intermittently, until 1815, when Herschel's advancing age and declining health made its demanding operation impractical, and it stood in its garden setting for decades afterward as a monument to Georgian astronomy until it was finally dismantled in 1840. William Herschel's career illustrated how astronomical progress often occurs through the interweaving of unexpected discoveries with systematic programs of investigation, and how a single observer's persistence can transform entire fields of inquiry. He had come to England as a musician seeking employment, had taken up telescope making as something between a hobby and an obsession, had discovered a new planet almost by accident during a routine survey, and had then applied his methodical approach to the double star problem in hopes of measuring parallax, only to discover instead the reality of gravitational interaction between distant suns. Each step followed logically from the one before, yet the overall trajectory could hardly have been predicted, and the scientific harvest exceeded anything Herschel himself had originally sought. His catalogues of double stars became foundational documents for 19th-century astronomy, providing the raw material from which later investigators would extract precise orbital parameters and eventually, in the hands of Friedrich Bessel and others, the parallax measurements that had eluded Herschel's own search. The distinction between optical doubles and physical binaries that Herschel established remains fundamental to our understanding of stellar systems today, and the techniques he developed for measuring close stellar pairs evolved into the specialized branch of astronomy known as visual binary studies, which continued to produce important results well into the 20th century. His observation that gravitational attraction operated identically in distant stellar systems as in our own solar neighborhood constituted one of the great unifying insights in the history of physics, placing Newton's mechanics on a truly universal footing for the first time and encouraging subsequent generations to seek similar universal laws governing other physical phenomena. And his estimates of stellar distances, though imprecise by later standards, correctly grasped the immense scale of the cosmic theater and prepared astronomers mentally for the quantitative breakthroughs that would come in the decades following his death in 1822, when new instruments and new methods would finally succeed in measuring what Herschel had sought. Nevil Maskelyne arrived at the Royal Observatory in Greenwich in the year 1765, assuming the position of Astronomer Royal at the age of 32, and he would remain in that role for 46 years, until his death in 1811, making his tenure one of the longest and most consequential in the observatory's history. He was a man of careful habits and methodical disposition, qualities that would prove essential for the painstaking work of improving astronomical measurement, and his appointment marked the beginning of what we might gently call an instrumental revolution, a period during which the tools of astronomy were refined to such extraordinary precision that measurements once thought impossible began to seem merely difficult. The quest to detect stellar parallax, that tiny angular shift caused by Earth's orbit around the Sun, required instruments capable of measuring fractions of an arcsecond, and when Maskelyne took up his post, the best instruments could manage perhaps a few arcseconds of accuracy on a good night, which was still far too coarse for the delicate work of catching a star's apparent wobble against the distant background. Before we settle into the details of instruments and measurements, it is worth pausing to understand the scale of the challenge that faced Maskelyne and his contemporaries. An arcsecond is a very small angle indeed, being 1/3600th of a degree, which means that a full circle contains 1,296,000 arcseconds. To put this in more tangible terms, if you were to hold a coin at arm's length, the angle it subtends against your view would be roughly 2,000 arcseconds, and so an arcsecond is about 2,000 times smaller than that coin appears. The parallax of even the nearest stars, as we now know, amounts to less than 1 arcsecond, and so the instruments of Maskelyne's era needed to improve by at least an order of magnitude before any hope of detection could reasonably be entertained. This improvement would come gradually, through the combined efforts of astronomers, instrument makers, and mathematicians, each contributing small refinements that accumulated over decades into something truly remarkable. One of Maskelyne's first and most enduring contributions was the establishment of the Nautical Almanac, which began publication in 1767 and immediately became an essential resource for navigators at sea. The almanac contained tables of predicted positions for the Sun, Moon, planets, and bright stars, calculated years in advance with sufficient accuracy that sailors could use these positions to determine their longitude through the method of lunar distances. This method required comparing the observed angle between the Moon and a reference star with the predicted angle given in the almanac, and from the difference, the navigator could work out the local time and hence the longitude. The production of such tables required the Greenwich Observatory to maintain a continuous program of precise observations, and this in turn demanded that the instruments be kept in the finest possible condition and their errors thoroughly understood. In this way, the practical needs of navigation drove improvements in astronomical precision that would eventually benefit the more abstract goal of parallax measurement. The controversy surrounding John Harrison and his marine chronometers forms an important thread in this story, though perhaps not in the way one might initially expect. Harrison, a self-taught clockmaker from Yorkshire, had spent decades developing timepieces accurate enough to keep time at sea despite the rolling of the ship and the variations in temperature and humidity. His fourth chronometer, known simply as H4, had proven itself on a voyage to Jamaica in 1761 and 62, losing only about 5 seconds over the entire journey, which was far better than any previous timekeeping device. However, Maskelyne, along with other members of the Board of Longitude, favored the lunar distance method and were skeptical of Harrison's claims, subjecting the chronometer to tests at Greenwich that Harrison considered unfair. The dispute dragged on for years and generated considerable ill feeling, but its relevance to our story lies not in the personal animosities but in the underlying principle that both methods shared, namely the recognition that precise timekeeping was fundamental to astronomical observation. whether one used a chronometer or the moon as a celestial clock. The essential requirement was knowing exactly when an observation was made. Because the positions of celestial objects change continuously and a few seconds of error in time could translate to a significant error in position. For parallax observations specifically, precise timing was necessary to account for the effects of atmospheric refraction, which varied with the altitude of the star and the conditions of the air, and to correct for the aberration of light, that subtle effect discovered by Bradley that caused stars to appear displaced in the direction of Earth's motion. Each of these corrections depended on knowing the exact time, and so the development of accurate clocks, whether mechanical or celestial, contributed directly to the precision needed for parallax work. By the end of Maskelyne's tenure, the observatory possessed regulators, which were precision pendulum clocks designed for stationary use, that could maintain time to within a fraction of a second per day, and this reliability underpinned all the other measurements made at Greenwich. In 1774, Maskelyne undertook an experiment that might seem at first glance to have little connection with stellar parallax, but which demonstrated techniques of precise measurement that would prove broadly applicable to astronomical work. The experiment took place at Heliometer, a mountain in the Scottish Highlands whose unusually regular shape made it suitable for a particular kind of investigation, namely an attempt to measure the gravitational attraction of the mountain itself. The idea was straightforward in principle though demanding in execution. One would set up a plumb line near the mountain and observe how much the line was deflected from true vertical by the gravitational pull of the rock. By surveying the mountain carefully to determine its volume and shape, and by measuring the deflection with precision, one could calculate the ratio of the mountain's density to the Earth's average density, and from this deduce something about the composition of our planet's interior. The Heliometer experiment required Maskelyne to measure very small angles with great accuracy, specifically the angular deflection of the plumb line, which amounted to only about 12 arcseconds. To achieve this, he used a zenith sector, an instrument designed to measure the angle between the vertical direction and a star passing near the zenith, and by observing the same stars from stations on opposite sides of the mountain, he could detect the difference caused by the plumb line being pulled toward the mountain at each location. The work involved setting up temporary observatories, protecting the instruments from wind and temperature changes, and making hundreds of observations over several months to reduce the effects of random errors. The result was a measurement of Earth's mean density of about 4.5 times that of water, which later refinements would correct to closer to 5.5. But more importantly for our purposes, the experiment demonstrated that angles of a few arcseconds could be reliably measured in the field under challenging conditions. This gave encouragement to those who hoped that stellar parallax, if it existed at a similar scale, might eventually be detected. The instruments that Maskelyne used at Greenwich included the Bird mural quadrant, a large brass arc mounted permanently on a wall aligned precisely with the north-south meridian. John Bird was a skilled instrument maker who had constructed this quadrant in 1750, and it remained the principal instrument for measuring the altitudes of stars as they crossed the meridian throughout much of Maskelyne's tenure. The quadrant was divided into degrees, minutes, and fractions of minutes by hand, using techniques of geometric division that required extraordinary care and patience. Bird would mark the divisions using a beam compass, stepping off intervals around the arc and then subdividing these by bisection and further bisection until he reached the finest graduations the instrument could accommodate. The accuracy of these divisions determined the ultimate precision of the instrument, and even the best craftsman working by hand could not entirely eliminate small irregularities in the spacing of the marks. Maskelyne devoted considerable attention to calibrating the bird quadrant, determining the errors in its divisions and applying corrections to his observations accordingly. This process involved comparing measurements of the same star made with different parts of the arc, looking for systematic discrepancies that would reveal errors in the graduation. It was slow and meticulous work, requiring many nights of observation and careful record-keeping, but it yielded a detailed map of the instrument's imperfections that allowed more accurate results to be extracted from the raw observations. This philosophy of understanding and correcting instrumental errors, rather than simply assuming the instrument was perfect, became a hallmark of the Greenwich approach and contributed significantly to the observatory's reputation for reliable measurements. A significant advance in the art of instrument making came in 1775, when Jesse Ramsden completed his first dividing engine, a device that mechanized the process of marking graduations on circular scales. Ramsden was a London instrument maker of exceptional skill and ambition, and he recognized that the hand methods used by Bird and others would always be limited by human dexterity and patience. His dividing engine used a large master wheel, very carefully graduated by hand to the highest possible accuracy, which could then be used to transfer divisions to any number of smaller scales through a system of gears and levers. The operator would advance the master wheel by one division, move a cutting tool to mark the corresponding line on the scale being graduated, and then repeat the process for each mark around the circle. Because the machine performed each operation in exactly the same way, the resulting divisions were more uniform than any handwork could achieve, and the process was much faster, allowing Ramsden to produce instruments in quantities that would have been impossible otherwise. The impact of the dividing engine on astronomical instruments was profound though not immediate. Ramsden himself was notoriously slow in completing orders, and astronomers sometimes waited years for instruments they had commissioned, but when those instruments arrived, they represented a clear advance over what had been available before. Scales that had previously been divided to single minutes of arc could now be divided to seconds, and the regularity of the divisions meant that calibration corrections were smaller and more predictable. By the 1780s and 90s, instruments graduated by Ramsden's engine were in use at observatories across Europe, and the standard of precision had improved accordingly. Where earlier observers might have claimed accuracy of a few arcseconds, the new instruments made claims of 1 arcsecond or better seem reasonable, though actually achieving such accuracy in practice required attention to many other sources of error beyond the scale divisions alone. Edward Troughton emerged as another master instrument maker in the later part of this period, refining and extending the techniques pioneered by Ramsden. Troughton experimented with different metals and alloys for his instruments, seeking materials that would be stable under changing temperatures and resistant to the gradual distortions that plagued earlier brass constructions. He also developed improved methods for mounting and adjusting telescopes, ensuring that the optical axis remained aligned with the mechanical axis of the instrument despite the stresses of use and the settling of foundations. One of Troughton's most significant contributions was his work on dividing techniques, which he continued to refine throughout his long career, and his instruments became the standard by which others were judged in the early 19th century. In 1812, the year after Maskelyne's death, a 6-foot mural circle made by Troughton was installed at Greenwich, replacing the aging bird quadrant as the principal instrument for meridian observations. This circle represented the culmination of decades of progress in instrument making, incorporating all the lessons learned about materials, graduation, mounting, and adjustment. Unlike a quadrant, which covers only 90 degrees, The full circle allowed observations on both sides of the zenith and provided built-in checks on the accuracy of the readings. The 6-foot diameter was chosen to give a scale large enough that very fine graduations could be marked and read without excessive crowding, and the divisions were cut using a dividing engine of Troughton's own design, successor to Ramsden's pioneering device. With instruments of this quality, the observers at Greenwich could routinely measure star positions to within about 1 arcsecond, and on especially favorable nights with careful technique, the uncertainty might approach 1/10 of an arcsecond. This was the threshold needed for parallax work, for the nearest stars, as we now know, have parallaxes of roughly 1 arcsecond or a bit less, and detecting such a displacement against the noise of measurement errors, atmospheric disturbances, and systematic instrumental effects required this level of precision as a minimum. The instrumental revolution that Maskelyne had helped to initiate, and that Ramsden and Troughton had advanced through their mechanical ingenuity, had finally brought stellar parallax within reach, though the actual detection would have to wait for another generation of astronomers with even better tools and more refined techniques. It is worth reflecting on the nature of this progress, for it did not come through any single dramatic breakthrough but through the steady accumulation of small improvements over many years. Each refinement in the dividing engine, each better understanding of thermal expansion in metals, each improvement in clock regulation and each more careful analysis of atmospheric refraction contributed a small increment to the overall precision. Maskelyne himself spent decades at the eyepiece, night after night, recording observations that differed from their predecessors by tiny amounts, and it was only through this patient accumulation of data that the systematic errors could be identified and corrected. The work was not glamorous and the progress was often imperceptible in the short term, but looking back over the span from 1765 to 1812, the improvement was unmistakable. Instruments that had struggled to achieve 10 arcseconds of accuracy at the beginning of this period could now approach 1/10 of an arcsecond, an improvement of roughly 100-fold in less than 50 years. The human elements of this story deserve mention as well, for these instruments did not operate themselves and the measurements did not record themselves. Observers like Maskelyne and his assistants spent long cold nights in the unheated dome, waiting for clouds to clear and for moments of atmospheric steadiness when the star images would sharpen enough for precise measurement. They learned to recognize the subtle signs of instrumental misbehavior, the slight stiffness in a bearing that indicated the need for cleaning, the gradual drift in a clock rate that signaled a change in temperature or a wearing of the escapement. They developed techniques for reducing observational errors, such as making multiple readings and averaging them, or observing the same star on successive nights to look for systematic effects. All of this knowledge accumulated alongside the physical improvements in the instruments, and the two developments together enabled the progress we have been describing. The Nautical Almanac continued throughout this period to be a major driver of precision astronomy, for the tables it contained needed to be more accurate with each passing year as navigators demanded better performance and as rival nations produced competing publications. Maskelyne took the work seriously and devoted considerable resources to maintaining the quality of the predictions, hiring human computers, which was the term then used for people who performed calculations, to carry out the lengthy arithmetic needed to reduce observations and predict future positions. The interaction between the practical demands of navigation and the theoretical goals of astronomy was fruitful for both, with each pushing the other toward greater precision and reliability. By the time Maskelyne died in 1811, the stage was set for the detection of stellar parallax, though he did not live to see it accomplished. The instruments existed, The techniques had been developed, and the importance of the measurement was universally recognized. What remained was to find the right star, one close enough to show a measurable parallax yet far enough from its neighbors that the parallax could be distinguished from other effects, and to observe it with sufficient persistence and care that the tiny annual wobble would emerge from the noise. This would fall to the next generation, armed with the tools that Maskelyne, Ramsden, Troughton, and their contemporaries had created, and it is perhaps fitting that the culmination of their work would come within a few decades of the instrumental revolution they had set in motion. Let us rest here for a moment with the thought that precision in measurement is not merely a technical achievement but a kind of discipline, a commitment to understanding every source of error and accounting for it as carefully as possible. The astronomers and instrument makers of this era embodied that discipline in their work, spending years on tasks that might seem tedious to an outside observer but which were essential for the advancement of knowledge. Their legacy was not just the instruments they built or the observations they recorded, but a culture of careful measurement that would carry forward into the succeeding generations and make possible the discoveries that lay ahead. The stars kept their secrets a little longer, but the tools for extracting those secrets were now in hand, and the quiet, patient work continued, as it always does in science, one night at a time, one observation at a time, one small improvement at a time. And so we come now to a rather lovely chapter in this long and patient story, one in which astronomers began to notice something quite unexpected about the stars themselves, something that would eventually help them choose which stars to observe most carefully in their continuing search for parallax. For you see, up until the early 18th century, most people who thought about such things assumed that the stars were fixed in their positions, pinned to the celestial sphere like tiny lights sewn into a great dark canopy, unchanging from age to age and generation to generation. This was the ancient view, inherited from Aristotle and passed down through Ptolemy and the medieval scholars, and it seemed reasonable enough given that no one had ever noticed the stars doing anything other than wheeling overhead each night in their familiar patterns. The constellations that shepherds watched in ancient Greece were the same constellations that farmers saw in 18th century England, and this apparent permanence suggested that the stars were truly eternal and motionless, or at least motionless in relation to one another even as the whole celestial sphere appeared to rotate around the Earth each day. But in the year 1718, a discovery was made that would gently overturn this ancient assumption, and it came from a man whose name you may recognize from a rather famous comet. Edmund Halley was by this time in his early 60s, serving as the second Astronomer Royal at Greenwich following the death of John Flamsteed, and he had spent much of his long career compiling observations and thinking deeply about the motions of celestial bodies. Halley was a thorough and careful scholar, the sort of person who enjoyed comparing old records with new measurements to see what had changed over the centuries, and it was this habit of careful comparison that led him to notice something remarkable about three particular stars. The stars in question were Arcturus, the bright orange star in the constellation of Boötes the herdsman, Sirius, the brilliant white star in Canis Major that is the brightest star in our night sky, and Aldebaran, the ruddy eye of Taurus the bull. When Halley compared his own measurements of these stars with the positions recorded by Ptolemy some 16 centuries earlier, he found that they had moved by a noticeable amount, perhaps half a degree or more in some cases, which was far too large to be explained by any errors in Ptolemy's observations or by the known effects of precession, which Halley had already accounted for in his calculations. This was proper motion, though Halley did not use that precise term, and it meant that the stars were not fixed after all. They were drifting slowly across the sky, each star following its own path through space at its own particular velocity, though this motion was so gradual that it took centuries to become apparent to the naked eye. Halley published his findings in the Philosophical Transactions of the Royal Society, noting with characteristic understatement that these stars had changed their places since the time of Hipparchus, and that there was no reason to suppose they should be the only stars possessed of such motion. He suggested that if one could observe for long enough, one might find that many or even all stars had some proper motion of their own, and that the seeming fixedness of the stellar realm was simply an illusion created by the vast timescales involved. This discovery, gentle as it might seem, had profound implications for the search for stellar parallax, though it would take some decades for astronomers to fully appreciate its significance. The key insight was this: if a star showed a large proper motion, drifting noticeably across the sky over the course of years or decades, this was a strong indication that the star was relatively close to our solar system. A distant star, even if it were hurtling through space at tremendous speed, would appear to move very slowly from our perspective, just as an aeroplane high overhead seems to crawl across the sky while a bird flying past your window flashes by in an instant. The stars with the largest proper motions were therefore likely to be our nearest neighbors in the cosmos, and this made them the most promising candidates for parallax detection. After all, the parallax shift depends on the star being close enough for the change in our viewing angle to produce a measurable displacement, and a star that was already revealing its proximity through rapid proper motion was advertising itself, in a sense, as exactly the sort of target that parallax hunters should pursue. This logic took time to develop and refine, and in the decades following Halley's announcement, several astronomers contributed to our growing understanding of stellar motions. Among them was Tobias Meyer, a German astronomer and cartographer who worked at the university in Göttingen during the 1750s. Meyer was a meticulous observer with a particular talent for precise measurement, and he undertook a systematic program to determine the positions of stars with the greatest possible accuracy. His goal was not specifically to detect proper motion, but rather to create a reliable catalogue that could serve as a foundation for future work in astronomy and navigation. Meyer used a mural quadrant, which was a large graduated arc fixed to a wall and aligned precisely with the meridian, allowing him to measure the altitudes of stars as they crossed the north-south line each night. He also employed a transit instrument for timing these meridian crossings, and through careful attention to the sources of error that had plagued earlier observers, he achieved a level of precision that was remarkable for his time. Meyer's observations from Göttingen provided valuable data on stellar positions, and when his measurements were compared with those made by Ole Romer some 50 years earlier, small but definite proper motions could be detected for a number of stars. Meyer himself compiled a list of about 80 stars whose positions he had determined with particular care, and this catalogue became an important reference for later astronomers seeking to identify stars with significant proper motion. His work demonstrated that systematic, long-term observation was essential for understanding the true nature of stellar movements, and that the careful accumulation of precise measurements over decades and centuries was the only way to tease out the slow drifts of individual stars against the background of the celestial sphere. The story of stellar motion grew more complicated still with a discovery made by William Herschel, the musician turned astronomer who had already found the planet Uranus and catalogued thousands of nebulae and double stars. In 1783, Herschel published a paper in which he announced that the Sun itself was in motion, carrying the entire solar system along with it through space. He had reached this conclusion by analyzing the proper motions of a number of stars and noticing a pattern in their movements. Stars in one part of the sky seemed to be spreading apart from one another, while stars in the opposite direction appeared to be drawing together. And this was exactly what one would expect if the sun were moving toward a particular point in space. Just as trees beside a road seem to part before you as you walk forward and close together again behind you, so too the stars would appear to drift apart ahead of the sun's motion and converge in its wake. Herschel identified this point, which he called the solar apex, as lying in the constellation of Hercules, roughly in the direction of the bright star Vega, and subsequent observations have confirmed that the Sun is indeed moving in approximately this direction at a speed of about 20 kilometers per second relative to the nearby stars. This discovery was beautiful in its own right, revealing that our solar system was not fixed at the center of creation but was instead journeying through the galaxy like a ship sailing across a vast ocean. But it also complicated the interpretation of stellar proper motions, because now astronomers had to distinguish between the true or peculiar motion of each star, meaning the star's own movement through space, and the apparent motion caused by the sun's drift. A star might appear to have a small proper motion not because it was distant and slow-moving, but because its true motion happened to be carrying it in nearly the same direction as the sun, so that the two motions partially cancelled out. Conversely, a star with a large observed proper motion might be moving in the opposite direction to the sun, so that the two motions added together to produce an exaggerated apparent drift. Disentangling these effects required careful analysis and, ideally, measurements of many stars in different parts of the sky, so that the solar motion could be subtracted out and the true peculiar velocities revealed. Despite this complication, the basic principle remained sound. Stars with large proper motions were, on average, likely to be among the nearest to our solar system, even if one could not be certain about any individual star without additional information. And so astronomers continued to catalogue stellar positions and track proper motions with ever-increasing precision, building up a body of knowledge that would eventually guide the search for parallax toward its successful conclusion. Among the most important contributors to this effort was Giuseppe Piazzi, an Italian astronomer who directed the observatory at Palermo in Sicily. Piazzi is perhaps best remembered for his discovery of Ceres, the first asteroid, on the first night of the 19th century, but his lasting contribution to stellar astronomy was his great catalogue of star positions, published in 1803 and 1814. Working with a fine altitude and azimuth circle made by Jesse Ramsden, one of the premier instrument makers of the age, Piazzi measured the positions of nearly 8,000 stars with a precision that surpassed anything that had come before. His catalogue became a standard reference for the astronomical community, and it was particularly valuable for the study of proper motion because Piazzi had been so careful to eliminate systematic errors and to record his observations with full details of the methods and conditions involved. It was in the course of this work that Piazzi identified a number of stars with unusually large proper motions, and among them was a rather faint star in the constellation of Cygnus the Swan, designated 61 Cygni in Flamsteed's numbering system. This star, barely visible to the naked eye under good conditions, was found to be moving across the sky at the remarkable rate of about 5.2 arcseconds per year, which was by far the largest proper motion known for any star at that time. To give you a sense of what this means, imagine dividing a single degree of arc, which is roughly the width of your little finger held at arm's length, into 3,600 equal parts. Each of those parts is 1 arcsecond, and 61 Cygni was drifting across the sky by more than 5 of those tiny units every single year. Over the course of a human lifetime, the star would move by several arc minutes, an amount easily detectable with even a modest telescope. This rapid motion made 61 Cygni stand out as an exceptional object, a star that was almost certainly very close to our solar system, and it became known informally as Piazzi's flying star in honor of its discoverer. The significance of 61 Cygni's large proper motion was not lost on astronomers, and as the 19th century progressed, this star came to be regarded as one of the most promising targets for parallax measurement. Its faintness, which might have been a disadvantage for other purposes, was actually consistent with its being a nearby star of modest intrinsic luminosity, perhaps a sun somewhat smaller and cooler than our own. And its position in the northern sky made it accessible to observatories in Europe, where the best instruments and most experienced observers were to be found. We shall return to 61 Cygni in due course, but for now it is enough to note that Piazzi's catalogue had identified this star as a prime candidate for the long-sought measurement of stellar distance. Another astronomer who contributed greatly to our understanding of stellar motions was Friedrich Wilhelm August Argelander, a German who spent much of his career at the Observatory in Bonn. Argelander was a prodigious observer and cataloguer, best known for his Borner Durchmusterung, a survey that recorded the positions and approximate brightnesses of over 300,000 stars in the northern sky. But he was also deeply interested in the problem of stellar motions, and he devoted considerable effort to compiling and analyzing proper motion data for stars throughout the heavens. Argelander recognized that accurate proper motions required observations spanning many years, ideally many decades, and he was careful to combine his own measurements with those of earlier observers whenever reliable historical data were available. His work helped to establish proper motion as a standard tool for stellar astronomy, one that could be used not only to identify nearby stars but also to investigate the structure and dynamics of the stellar system as a whole. Argelander also contributed to the refinement of Herschel's determination of the solar apex, using his more extensive dataset to improve the estimate of the direction and speed of the Sun's motion through space. This was important for the parallax problem because, as we have noted, the Sun's motion introduces a systematic drift into the apparent positions of all stars, and this drift must be accounted for when interpreting observations made over a period of years. Argelander's work helped to clarify the magnitude of this effect and provided a foundation for later astronomers who would need to separate the tiny parallax shift from the much larger motions caused by the Sun's journey through the galaxy. By the early decades of the 19th century, then, the logic connecting proper motion to stellar distance had become well established in the astronomical community. The reasoning was simple and compelling. Stars that appeared to move quickly across the sky were, in all likelihood, closer to us than stars that appeared to drift slowly, just as a person walking past your window seems to move faster than a distant figure crossing a far-off hillside. This did not mean that proper motion could tell you exactly how far away a star was, because that depended also on the star's true velocity through space, which was unknown. But it did provide a way to identify the most promising candidates for parallax measurement, the stars that were most likely to be close enough for their tiny annual wobble to be detected with existing instruments. And among all the stars in the sky, 61 Cygni stood out as the fastest moving and therefore, almost certainly, one of the very nearest to our own solar system. This insight would prove crucial in the years to come, as astronomers turned their attention once more to the ancient problem of stellar parallax, armed now with better instruments, better techniques, and a clearer understanding of which stars to observe. The patient accumulation of proper motion data, stretching back through the work of Argelander and Piazzi and Meyer and Herschel and Halley, had provided a roadmap of sorts, pointing the way toward those few stars where the parallax shift might just barely be within reach of human measurement. And so, with these preparations complete, the stage was set for the final chapter in the long quest to determine the distances to the stars. A chapter that would unfold in the observatories of Königsberg and Dorpat and the Cape of Good Hope, and that would at last bring the dream of measuring the cosmic scale within the grasp of patient and determined observers. But that story will wait for another time, another section of this gentle telling. For now, let us simply rest with the knowledge that the stars are not fixed after all, that they drift slowly across the heavens on journeys of their own, and that by watching their subtle movements over the years, astronomers learned to recognize which among them were our nearest neighbors in the vastness of space. The heliometer stands as one of the most exquisitely precise instruments ever devised for the measurement of the heavens, and its story begins not with the stars at all, but with our own sun, that familiar golden presence that warms the earth and marks the passage of our days. The very name heliometer tells us of these solar origins, derived from the Greek word helios, meaning sun, combined with metron, meaning measure, and it was this instrument's remarkable ability to determine the apparent diameter of the solar disk that first brought it into being, though astronomers would eventually discover that its true genius lay elsewhere, in the patient and painstaking measurement of the tiny angular separations between stars, those almost imperceptibly small gaps in the firmament that would finally yield the secrets of stellar distance. The invention of the heliometer is credited to the English optician John Dolland, who in the year 1754 conceived of a novel approach to measuring small angles in the sky with a precision that exceeded anything previously achievable. Dolland was already well established as a maker of fine optical instruments, working from his shop in London where he crafted spectacles and lenses of considerable quality, and his mind turned naturally to the problems that vexed the astronomers of his day, particularly the difficulty of measuring the sun's apparent size with sufficient accuracy to detect the small variations caused by Earth's elliptical orbit. The traditional method of solar measurement involved observing the moments when the edges of the sun crossed the meridian, timing this transit with the best available clocks, but this approach was fraught with difficulties, as the blinding brightness of the solar disk made precise observation challenging, and atmospheric effects introduced troublesome uncertainties that were difficult to eliminate. Dolland's solution was elegant in its conception, involving the division of the telescope's objective lens into two separate halves, each capable of forming its own complete image of the observed object. By mounting these two half lenses so that they could slide past one another in a carefully controlled manner, with the amount of displacement measured by a precise scale, an observer could bring two images of the same object into apparent contact or overlap, and the reading on the scale would then indicate the angular size of that object with remarkable accuracy. When applied to the sun, this meant that the observer could slide the half lenses until the two solar images just touched at their edges, or until they overlapped by a precisely known amount, and from the lens separation required to achieve this configuration, the apparent diameter of the sun could be calculated. This was a measurement that could be performed quickly and repeatedly, without the need for transit timings or the uncertainties of clock-based methods, and the results were correspondingly more consistent and reliable. The principle underlying the heliometer's operation involves the fundamental optical property that when a lens is displaced perpendicular to its optical axis, the image it forms is also displaced, and the amount of this image displacement is directly related to the lens displacement through the geometry of the optical system. In the heliometer, each half of the divided objective lens forms a separate image, and as the half lenses are moved apart, These two images separate by an angular amount that depends both on the physical displacement of the lenses and on the focal length of the instrument. For a given focal length, the relationship between lens displacement and angular separation is fixed and calculable, meaning that the micrometer scale measuring the lens positions can be calibrated directly in angular units, allowing the observer to read off small angles with a precision determined only by the quality of the mechanical components and the care of the observation. Yet for all the cleverness of Dollond's original design, the heliometers of the 18th century remained relatively crude instruments, limited by the quality of the available glass and the precision of the mechanical components. The lenses of Dollond's time were typically simple singlets, uncorrected for the chromatic aberration that caused different colors of light to focus at different distances, producing images surrounded by distracting color fringes that compromised the precision of measurement. The mechanical slides and scales, while adequate for solar measurement, lacked the refinement necessary for the exacting work of stellar observation, where the angles to be measured were many thousands of times smaller than the diameter of the Sun. It would take another generation, and the genius of a young Bavarian optician, to transform the heliometer from a useful solar instrument into the supreme tool of parallax measurement. Joseph von Fraunhofer was born in the year 1787 in the town of Straubing in Bavaria, the 11th child of a master glazier, and his early life was marked by hardship and adversity that might have crushed a lesser spirit. Orphaned at the age of 11, young Joseph was apprenticed to a harsh master in Munich, where he labored under difficult conditions making mirrors and decorative glass. A fortunate turn came in 1801 when the workshop building collapsed, trapping the young apprentice in the rubble, and his dramatic rescue attracted the attention of Prince-Elector Maximilian Joseph of Bavaria, who provided financial support for his education and ultimately his career. From these unpromising beginnings, Fraunhofer would rise to become the greatest optical craftsman of his age, revolutionizing the manufacture of astronomical instruments and establishing standards of precision that would guide telescope makers for generations to come. At the heart of Fraunhofer's achievements was his mastery of the achromatic doublet lens, a compound lens consisting of two elements made from different types of glass, carefully figured and combined so that the chromatic aberration of one element was cancelled by that of the other. The principle of the achromatic lens had been known since the middle of the 18th century, and Dollond himself had made important contributions to its development, but the practical realization of large, high-quality achromatic lenses had remained elusive, limited by the difficulty of producing optical glass of sufficient purity and homogeneity. Fraunhofer attacked this problem at its source, learning the secrets of glassmaking and eventually establishing his own glassworks at Benedict Boyen, where he could control every aspect of the production process, from the selection of raw materials to the final annealing of the finished blanks. The glass that emerged from Fraunhofer's works was of unprecedented quality, free from the striae, bubbles, and compositional variations that had plagued earlier manufacturers, and this excellence of material provided the foundation for a new generation of optical instruments. Fraunhofer combined his superior glass with equally superior craftsmanship in the figuring and polishing of lens surfaces, developing techniques that allowed him to achieve optical accuracy approaching the theoretical limits imposed by the wave nature of light itself. His attention extended equally to the mechanical components of his instruments, to the tubes and mountings and drives and micrometers, all of which were constructed to standards of precision that matched the optical excellence of the lenses they supported. In the early 1820s, Fraunhofer turned his attention to the construction of a heliometer of unprecedented capability, an instrument intended to exploit the full potential of Dollond's split lens design for the most demanding astronomical measurements. This project occupied several years of intensive work at his Munich optical establishment, and the result was an instrument that represented the absolute pinnacle of early 19th century precision engineering. The objective lens, constructed as an achromatic doublet of 6.2 inches in aperture, was divided along its diameter into two precisely matched halves, each capable of forming stellar images of crystalline sharpness. The focal length of 102 inches provided a scale sufficiently expanded to allow the measurement of extremely small angular separations, while the mechanical components that controlled the movement of the half lenses were engineered to permit displacements measurable to a tiny fraction of a thousandth of an inch. The precision screws that drove the movement of the heliometer's half lenses were themselves masterpieces of the machinist's art, cut with a uniformity and smoothness that allowed them to be read with confidence to divisions corresponding to fractions of an arcsecond in the sky. Fraunhofer understood that the accuracy of the entire instrument depended critically upon these screws, for any irregularities in their threads would translate directly into errors in the measured angles, and he devoted extraordinary care to their manufacture and calibration. Each screw was tested and measured repeatedly, and tables of corrections were prepared to account for any remaining imperfections, so that the observer could apply small adjustments to the raw readings and achieve the maximum possible accuracy. Tragically, Joseph von Fraunhofer did not live to see his magnificent heliometer contribute to one of the great triumphs of 19th century astronomy. In the year 1826, at the age of only 39, Fraunhofer died in Munich, his health broken by years of exposure to the noxious substances employed in the manufacture of optical glass. The heavy metals, the acids, the toxic fumes that were inseparable from the glass-making processes of that era had taken their toll on his constitution, and though he had achieved more in his shortened life than most accomplish in a full span of years, one cannot help but wonder what further marvels he might have created had he been granted more time. His death robbed optics of its foremost practitioner, and the instruments he left behind became treasured relics of an achievement that would not be equaled for many decades. The great heliometer was completed after Fraunhofer's death by his successors at the Munich Optical Works, following his designs and specifications with faithful precision, and in the year 1829 it was delivered to the Königsberg Observatory in Prussia, where it came into the hands of Friedrich Wilhelm Bessel. Bessel, as we have discussed, was one of the foremost observational astronomers of his generation, a man who combined mathematical brilliance with practical skill and an unwavering commitment to the elimination of error, and he immediately recognized the heliometer as an instrument uniquely suited to the long-sought measurement of stellar parallax. Unlike earlier approaches that had relied upon meridian observations, with all their atmospheric and instrumental complications, the heliometer offered the possibility of measuring the tiny angular shift of a nearby star directly against the background of more distant stars, all within the same field of view, all observed under identical conditions. The superiority of the heliometer for parallax work stemmed from its ability to perform what astronomers call differential measurement, the precise determination of small angular separations between objects seen simultaneously in the same telescope. When a meridian circle or transit instrument measures the position of a star, it does so by determining the moment when the star crosses a reference line defined by the instrument itself, and this measurement is affected by every imperfection in the instrument's alignment, every variation in the properties of the atmosphere, every uncertainty in the rotation of the Earth. These sources of error are systematic rather than random, and they can accumulate over the course of observations spread across months or years. introducing spurious signals that masquerade as the genuine parallax shift being sought. Many earlier attempts at parallax measurement had been confounded by just such systematic errors, producing claimed detections that could not be confirmed and controversial results that remained in dispute for decades. The heliometer avoided these difficulties by measuring not the absolute position of the target star, but rather its position relative to other stars in the immediate vicinity, stars that would be affected by the same instrumental and atmospheric conditions but that, being presumably much more distant, would show no detectable parallax of their own. Any shift in the apparent position of the nearby star against this background of distant comparison stars could therefore be attributed with confidence to genuine parallax motion, for all the common mode errors would cancel out in the differential measurement. This was the key insight that made the heliometer so powerful, and Bessel exploited it to the full in his observations of the star 61 Cygni, systematically measuring its position relative to a pair of faint comparison stars over the course of more than a year. While Bessel worked with his Fraunhofer heliometer at Königsberg, other astronomers pursued the parallax quest with different instruments, each hoping to achieve the first definitive detection. At the Dorpat Observatory in what is now Estonia, Friedrich Georg Wilhelm Struve wielded a magnificent 9.6-inch refracting telescope, the largest in the world at that time, also a product of Fraunhofer's workshops. This great telescope, though not equipped with a heliometer mechanism, possessed sufficient light-gathering power and optical quality to permit highly precise measurements using a filler micrometer, that device of fine threads moved by precision screws which we have previously encountered. Struve selected the bright star Vega, also known as Alpha Lyrae, as his target, reasoning that its exceptional brilliance might indicate relative proximity and therefore a measurable parallax. At the Cape of Good Hope, at the southern extremity of Africa, the Scottish astronomer Thomas Henderson had access to a more modest instrument, a mural circle of the sort traditionally used for meridian observations. Henderson had selected the star Alpha Centauri as his target, the third brightest star in the entire sky and one that showed an exceptionally large proper motion, that gradual drift across the heavens that had long been suspected to correlate with proximity. The mural circle, though less well suited to parallax work than the heliometer, could yield useful results when applied to a star with a sufficiently large parallax, and Alpha Centauri, as would eventually become clear, possessed the largest parallax of any star visible from Henderson's location. The competition among these three observers, and the near-simultaneous announcements of their results, would form one of the most dramatic episodes in the history of astronomy, though we shall save the details of that story for another time. For now it is sufficient to note that Bessel's heliometer observations proved the most convincing to the astronomical community, owing to the thoroughness of his analysis, the careful attention to error sources, and the intrinsic advantages of the differential measurement technique that the heliometer made possible. The other instruments had their merits, and the results obtained by Struve and Henderson were ultimately vindicated by later observations, but it was the Königsberg heliometer that established the paradigm for precision parallax measurement, a paradigm that would dominate the field for the remainder of the 19th century. The heliometer's design embodied a truth that all practitioners of precision measurement eventually learn: that accuracy is most readily achieved not by attempting to determine absolute quantities directly, but by arranging matters so that one measures differences between quantities, allowing all the errors common to both quantities to cancel in the subtraction. This principle appears throughout the physical sciences, from the analytical balance that compares an unknown mass against a standard mass, to the interferometer that measures distances by counting the wavelengths of light between two mirrors. In the astronomical context, the heliometer realized this principle with beautiful directness, placing the two objects to be compared within the same optical field, under identical conditions, so that their angular separation could be determined with a precision far exceeding what would be possible from independent measurements of their individual positions. As the night deepens and the stars will slowly overhead in their ancient patterns, we may picture Bessel at the eyepiece of his heliometer, patiently adjusting the great instrument, sliding the half-lenses back and forth until the images of his target star and its comparison stars assumed exactly the configuration needed for measurement. The observatory would have been cold in the Prussian winter, the astronomer's breath visible in the lantern light, his fingers chilled as he manipulated the precision screws and recorded each reading in his observation book. This was the work of months and years, a campaign of systematic observation repeated through all seasons, through good nights and poor, through the inevitable discouragements and setbacks that attend any demanding scientific enterprise. The heliometer represented the culmination of centuries of development in astronomical instrumentation, a device that combined the finest materials, the most precise craftsmanship, and the deepest understanding of optical principles into a tool capable of detecting angular shifts of less than a third of an arcsecond, a quantity so small as to be almost unimaginable. To place this in perspective, we might recall that the apparent diameter of the full moon is approximately half a degree, or some 1800 arcseconds, and that the parallax of even the nearest star is barely more than a single arcsecond. The heliometer could measure such tiny angles with confidence because every aspect of its design had been optimized for precision, from Fraunhofer's flawless glass to his immaculate screws to the stable mounting that held all in proper alignment. And so the instrument stands before us as a monument to human ingenuity and patience, a machine designed for the sole purpose of answering one of the oldest questions in astronomy, the question of how far away the stars might be. The answer to that question, when it finally came, would transform our understanding of the universe, revealing distances so vast that they strained the imagination and demanded new units of measurement to express them. But all of that lay in the future as Bessel and his contemporaries worked through the nights of the 1830s, slowly accumulating the observations that would at last yield the long-sought parallax, using instruments that embodied the best that human craft and science could achieve. And now we come to the moment when the ancient dream finally became real, when the distance to a star beyond our own sun was measured for the first time with certainty, and the cosmos opened up before human understanding in a way that had never quite happened before. The person who achieved this milestone was not born into privilege or academic circles, but rather emerged from circumstances that might have kept most people occupied with simpler concerns for their entire lives. Friedrich Wilhelm Bessel came into the world on the 22nd of July in 1784, in the small German town of Minden, which lies along the river Weser in what was then part of the Kingdom of Prussia. His father held a position as a minor civil servant, and the family was respectable but by no means wealthy, and when Friedrich was still young, his father passed away, leaving the boy in circumstances that required him to find his own way in the world rather earlier than most children of his age might have expected. At the age of 14, young Friedrich was apprenticed to a trading company in Bremen, a bustling port city where merchants conducted business with ships arriving from distant corners of the world. The work involved keeping accounts, calculating exchange rates, learning the intricacies of international commerce, and developing the kind of practical mathematical skills that would serve a merchant well throughout a long career. And here we might pause to imagine the young apprentice bent over ledgers late into the evening, tallying figures and checking calculations, developing without quite realizing it a facility with numbers and a patience for careful, repetitive work that would later prove essential to his scientific achievements. The trading company dealt with goods arriving by sea, and this meant that young Bessel needed to understand something of navigation, of how ships found their way across trackless oceans using the positions of stars and the careful measurement of angles with sextants and other instruments. It was this practical necessity that first drew Bessel's attention upward toward the night sky, and what began as a professional requirement gradually transformed into something deeper. A genuine fascination with the movements of celestial bodies and the mathematics that described their paths through space. In his spare hours, after the day's commercial work was completed, he began teaching himself the principles of astronomy and the mathematical techniques needed to calculate the orbits of planets and comets. He obtained books on these subjects and worked through them methodically, mastering techniques that university students struggled to learn even with the benefit of professors to guide them. There is something rather comforting in this image, if you let yourself dwell on it, of a young clerk in a counting house, surrounded by invoices and bills of lading, who spent his evenings contemplating the paths of comets and working through equations by candlelight, pursuing knowledge for its own sake with no particular expectation that it would lead anywhere beyond the satisfaction of understanding. In 1804, when Bessel was 20 years old, he decided to test his self-taught abilities by undertaking a genuinely ambitious project. He obtained the original observations that Edmund Halley had made of the great comet of 1682, the comet that would later bear Halley's name, and set himself the task of recalculating its orbit using more modern mathematical methods. This was not a trivial undertaking, as orbital calculations involved complex iterative procedures and required considerable skill to perform correctly. When Bessel completed his work, he sent the results to Heinrich Wilhelm Olbers, a physician in Bremen who was also a highly respected amateur astronomer known for his work on comets and asteroids. Olbers examined the young man's calculations and found them to be not merely competent but genuinely impressive, demonstrating a level of mathematical sophistication that belied Bessel's lack of formal training. Recognizing exceptional talent, Olbers took Bessel under his wing and introduced him to other astronomers, opening doors that might otherwise have remained firmly closed to a merchant's apprentice without university credentials. Through these connections, Bessel came to the attention of Johann Hieronymus Schroeter, who operated a private observatory at Lilienthal, not far from Bremen. Schroeter offered the young man a position as his assistant, and in 1806, at the age of 22, Bessel left behind the world of commerce forever and began his career as a professional astronomer. The transition from counting house to observatory was complete, and though he never attended university or obtained a formal degree, Bessel would go on to become one of the most influential astronomers of the 19th century, eventually receiving honorary doctorates and membership in scientific academies throughout Europe in recognition of achievements that needed no academic credentials to validate their worth. Bessel's abilities quickly became apparent to everyone who worked with him, and his reputation grew steadily through the early years of his career. In 1809, the Kingdom of Prussia decided to establish a new observatory at Königsberg, a city in East Prussia that was home to a distinguished university where the philosopher Immanuel Kant had spent his entire career. The position of director for this new observatory needed to be filled, and despite his youth and lack of formal qualifications, Bessel was offered the post. He accepted and arrived in Königsberg in 1810, at the age of 26, to oversee the construction and equipping of what would become one of the finest observatories in Europe. He would remain there for the rest of his life, and it was from Königsberg that he would eventually achieve the measurement that astronomers had sought for centuries. For many years after his arrival at Königsberg, Bessel devoted himself primarily to the painstaking work of cataloguing star positions and refining the fundamental measurements upon which all astronomy depended. He understood that measuring stellar parallax would require positional accuracy far beyond what had previously been achieved, and so he worked systematically to eliminate every possible source of error, studying the behavior of his instruments, accounting for the effects of atmospheric refraction, and developing mathematical techniques for extracting the maximum information from observational data. This preparatory work was not glamorous, and it produced results that might seem rather dry to anyone not deeply versed in the technical aspects of astronomy, but it was absolutely essential. Bessel was not the sort of person to rush toward a spectacular result while leaving fundamental problems unsolved. He preferred to build his edifice of knowledge on solid foundations, brick by careful brick, even if this meant that the final structure took longer to complete. By the late 1830s, Bessel felt that both his instruments and his methods had reached a level of refinement that might finally make parallax detection possible. The telescope he would use was a heliometer, an instrument originally designed for measuring the apparent diameter of the Sun, but well suited to making extremely precise measurements of the angular separation between nearby objects in the sky. The particular heliometer at Königsberg had been built by the renowned optical firm of Joseph von Fraunhofer in Munich and represented the finest achievement of the instrument maker's art. Its lens was divided into two halves that could be moved past each other by precisely calibrated amounts, allowing the observer to bring the images of two different stars into apparent coincidence and thereby measure their angular separation with extraordinary accuracy. In skilled hands, this instrument could detect angular changes far smaller than those accessible to ordinary telescopes. The choice of which star to observe was crucial, and Bessel selected his target with considerable care. The star he chose was 61 Cygni, an unassuming point of light in the constellation of the Swan that would be invisible to anyone unfamiliar with the night sky, lost among the brighter stars of the summer Milky Way. This particular star had a property that made it especially attractive for parallax observations, namely an unusually large proper motion, which is the gradual drift of a star across the sky due to its actual movement through space relative to the Sun. Proper motion and parallax are distinct phenomena, since proper motion is a real displacement that accumulates steadily year after year, while parallax is an apparent back and forth wobble caused by Earth's orbital motion. But early astronomers had suspected that stars with large proper motions might tend to be relatively nearby, simply because a given velocity through space would produce a larger apparent angular motion for a closer star than for a more distant one. 61 Cygni had the largest proper motion of any star then known, having been measured by the Italian astronomer Giuseppe Piazzi as moving more than 5 arcseconds per year, a remarkably swift drift by stellar standards. This made it a promising candidate for being one of our nearer stellar neighbors. There was another feature of 61 Cygni that made it particularly suitable for Bessel's purposes. The star is actually a binary system, consisting of two stars orbiting around their common center of mass, and the two components are separated by enough angular distance to be easily distinguished through a telescope. This meant that Bessel could measure not only the positions of these stars relative to more distant background stars, but also their positions relative to each other, providing additional checks on the reliability of his measurements. The presence of two stars moving together also helped confirm that any detected parallax was real rather than being some artifact of instrumental or observational error, since both components should show the same parallax signature if they were truly at the same distance from Earth. Bessel began his systematic observations of 61 Cygni in the autumn of 1837. And he continued them with methodical dedication through the following year and into the winter of 1838, a campaign spanning approximately 16 months in total. During this period, he made more than 400 separate measurements of the positions of the two component stars relative to two fainter comparison stars that appeared nearby in the sky but were presumably much more distant and therefore essentially stationary. The technique required extraordinary patience and care. Each measurement session involved centering the images in the heliometer, adjusting the divided lens to bring the target star into apparent coincidence with each comparison star in turn, recording the micrometer readings, and repeating the whole procedure multiple times to reduce random errors. Bessel would then need to apply corrections for atmospheric refraction, for the flexure of the telescope tube, for tiny imperfections in the driving mechanism that tracked the stars across the sky, and for numerous other factors that could affect the results. As the months passed and the measurements accumulated, Bessel began the mathematical analysis that would reveal whether a parallax signal was present in his data. The expected signature was a small ellipse traced out over the course of a year as Earth moved around its orbit, causing each star to appear to shift back and forth against the more distant background. For 61 Cygni, this ellipse would appear nearly as a straight line because the star lies close to the plane of Earth's orbit, and the major axis of the parallax ellipse is always perpendicular to the direction toward the Sun at any given time. The proper motion of the star also had to be accounted for, subtracted out of the data so that the small oscillating signal of parallax could be isolated from the steady drift across the sky. When Bessel analyzed his measurements, a clear signal emerged from the data. The two stars of 61 Cygni both showed the expected annual oscillation, and the amplitude of this oscillation could be determined with unprecedented precision thanks to the large number of measurements and the sophisticated error analysis that Bessel applied to his data. On the 10th of December in 1838, Bessel presented his results to the Berlin Academy of Sciences, announcing that he had detected the parallax of 61 Cygni and measured it to be 0.314 arcseconds, with an uncertainty small enough that the detection was statistically unambiguous. To appreciate what this number means, we need to understand the scale involved. An arcsecond is 1/3600th of a degree, an almost inconceivably tiny angle. If you imagine the full circle of the horizon as being divided into 360 degrees, and then each degree being subdivided into 60 arcminutes, and then each arcminute being further subdivided into 60 arcseconds, you begin to appreciate how small these units really are. The parallax that Bessel measured was about 1/3 of one of these arcseconds, a shift so minute that it had eluded every previous observer despite centuries of searching. For comparison, the human eye at its best can barely resolve details separated by about 1 arcminute, which is 60 times larger than the shift that Bessel detected. Only through the combination of excellent optics, mechanical precision, and sophisticated mathematical analysis could such a tiny signal be extracted from the noise of observation. Bessel was careful to demonstrate that his result was statistically significant and not merely a fluctuation that might have arisen by chance from random measurement errors. He calculated what we would now call the signal-to-noise ratio of his detection and showed that the measured parallax exceeded the expected random error by approximately a factor of 10. In modern terminology, We would say that his detection was significant at roughly the 10 sigma level, meaning that the probability of obtaining such a result by chance alone, if the true parallax were zero, was vanishingly small, less than 1 in billions. This careful attention to error analysis was characteristic of Bessel's approach throughout his career. He understood that claiming to have measured stellar parallax carried enormous weight, given how many previous claims had proven illusory, and he wanted to leave no room for doubt about the reliability of his result. From the measured parallax angle, the distance to 61 Cygni could be calculated using straightforward geometry. If a star shifts back and forth by 0.314 arcseconds as Earth moves from one side of its orbit to the other, then the star must lie at a distance where the diameter of Earth's orbit appears to subtend that angle. Working through the mathematics, Bessel found that 61 Cygni must be approximately 660,000 times farther from the Sun than Earth is, a distance of roughly 10.3 light-years in units that would be adopted later in the century. A light-year, of course, is the distance that light travels in 1 year, moving at approximately 300,000 kilometers per second, and so 10 light-years represents a span so vast that numbers alone struggle to convey its magnitude. The light that Bessel observed from 61 Cygni had left those distant suns more than a decade before reaching his telescope, beginning its journey while he was still refining his instruments and planning his observations. Modern measurements have refined Bessel's value slightly downward. The currently accepted parallax of 61 Cygni is approximately 0.287 arcseconds, corresponding to a distance of about 11.4 light-years rather than the 10.3 that Bessel calculated. But this modest discrepancy should not diminish our appreciation of his achievement. Given the limitations of his instruments and the inherent difficulty of the measurement, Bessel's result was remarkably close to the true value, accurate to within about 10%. More importantly, his conclusion that 61 Cygni lay at a distance of roughly 10 light-years was correct in its essential character. The stars were immensely far away, far more distant than any object in the solar system, but not infinitely so. They could be measured, their distances determined, their actual luminosities calculated once their distances were known. Bessel published his results in Astronomische Nachrichten, the leading astronomical journal of the era, which was edited by his friend Heinrich Christian Schumacher in Altona. The paper laid out his observations and analysis in meticulous detail, allowing other astronomers to scrutinize his methods and verify his conclusions. The response from the international scientific community was one of profound respect and acceptance. Bessel had such a formidable reputation for precision and rigor that his announcement carried immediate credibility. Where previous claims of parallax detection had been met with skepticism, often justified, Bessel's work was recognized as meeting the highest standards of evidence. Within a few years, 2 other astronomers would announce parallax measurements of different stars, providing independent confirmation that stellar distances could indeed be determined by this method. The publication of Bessel's parallax measurement marked a turning point in human understanding of the universe. For the first time, an actual distance to a star had been established on a firm empirical foundation. The cosmos had revealed one of its closely guarded secrets, yielding a concrete number where before there had been only speculation and imagination. And yet, as with many scientific advances, this triumph also illuminated how much remained unknown. If the nearest stars were 10 light-years distant, then the countless fainter stars sprinkled across the Milky Way must lie at distances that challenged comprehension, hundreds or thousands or tens of thousands of light-years from our small planet. The universe was not merely large. It was large beyond any scale that everyday experience could have prepared us to imagine. And so Bessel, the orphaned merchant's apprentice who had taught himself mathematics by candlelight, accomplished what Tycho and Galileo and Hooke and Herschel had all attempted without success. Through patience and skill and the steady accumulation of hundreds of careful measurements, he bridged the gap between our own solar system and the wider realm of the stars, demonstrating that human ingenuity could penetrate even the deepest mysteries of cosmic geography. His achievement stands as a testament to what methodical work and clear thinking can accomplish, and as an invitation to rest assured that the universe, however vast, is not beyond our capacity to understand. And so we come now to the other astronomers who were working, at the very same time as Friedrich Bessel, toward that ancient goal of measuring the distances to the stars. And it is a curious feature of scientific history that great discoveries so often arrive not alone but in clusters, as though the collective effort of many minds were somehow preparing the ground for revelation. And the measurement of stellar parallax proved to be no exception to this pattern, for within the span of just a few years, 3 separate astronomers, working at 3 different observatories spread across the globe, would each succeed in detecting the tiny angular shift that had eluded their predecessors for more than 2 centuries, and their stories interweave in ways that are both instructive and gently fascinating, touching as they do upon questions of priority and recognition, of confidence and hesitation, and of the peculiar ways in which scientific credit comes to be assigned. Let us turn our attention first to Friedrich Georg Wilhelm Struve, who was working at the Dorpat Observatory in what was then part of the Russian Empire, in the city now known as Tartu in modern Estonia, a place of long winters and clear cold skies, well suited to the demanding work of precision astronomy, and Struve himself was a figure of considerable distinction in the astronomical community of his day, having been born in 1793 in the German town of Altona, near Hamburg, and having made his way to Dorpat as a young man, where he would build one of the finest observatories in all of Europe and establish a dynasty of astronomers that would span 4 generations, a remarkable legacy in a field where such continuity is uncommon. The instrument that Struve employed in his pursuit of stellar parallax was itself a thing of beauty and precision, a great refracting telescope built by the master optician Joseph von Fraunhofer, whose name you may recall from the dark lines that appear in the solar spectrum and bear his name to this day. And this telescope, with its lens measuring 9¼ inches in diameter, was at the time of its construction the largest refracting telescope in the world, a marvel of optical engineering that had been delivered to Dorpat in 1824 and had immediately established the observatory as a center of observational excellence, allowing Struve to undertake a comprehensive survey of double stars that would occupy him for many years and bring him considerable renown. Struve's choice of target star for his parallax observations was Vega, the brightest star in the constellation Lyra and the 5th brightest star in the night sky as seen from Earth, a bluish-white beacon that passes nearly overhead for observers in the northern temperate latitudes. And his reasons for selecting Vega were similar to those that had guided Bessel toward 61 Cygni. For Vega too displayed a measurable proper motion, that gradual drift across the sky that suggested proximity to our solar system, though its motion was considerably smaller than that of Bessel's chosen star, amounting to about 1/3 of an arcsecond per year, a difference that would prove significant in the precision of the final result. The observations themselves began in earnest in the early 1830s, and Struve applied to them the full capability of his magnificent Fraunhofer refractor, measuring with great care the angular separation between Vega and several fainter stars that appeared nearby in the field of view, stars that were presumably much more distant and could therefore serve as fixed reference points against which any parallactic wobble might be detected. And this work continued over many months, accumulating the data that would eventually allow Struve to announce, in the year 1837, that he had detected a parallax for Vega of approximately 0.125 arcseconds, a value that he presented with appropriate caution, acknowledging the difficulty of the measurement and the possibility of systematic errors that might affect the result. This preliminary announcement came in December of 1837, just a few months before Bessel would present his own more confident measurement of 61 Cygni. And there is a certain poignancy in the timing, for Struve had in a sense been first to publish a parallax result. Yet his announcement lacked the certainty and the careful error analysis that would characterize Bessel's work. And the astronomical community, while interested, remained somewhat reserved in its acceptance, waiting for confirmation and refinement before declaring the long-sought measurement to have been finally achieved. And it is perhaps for this reason that history has tended to grant Bessel the laurels of priority, though the question of who truly measured parallax first is rather more nuanced than such simple attributions might suggest. Struve continued his observations of Vega over the following years, accumulating more data and refining his analysis, and by 1840 he had revised his parallax estimate significantly upward, to a value of 0.262 arcseconds, more than twice his original figure, a revision that speaks to the genuine difficulty of these measurements and the ease with which systematic effects could contaminate the results. And even this refined value would prove to be somewhat too large when compared with modern determinations, which place the parallax of Vega at approximately 0.13 arcseconds, corresponding to a distance of about 25 light-years, so that Struve's final published parallax was roughly double the true value, an error that would not be fully appreciated until many decades later when photographic techniques and larger telescopes permitted more accurate measurements. The reasons for Struve's overestimate are instructive, for they illuminate the particular challenges he faced in his chosen method. And chief among these was the difficulty of finding suitable comparison stars sufficiently close to Vega in the telescope's field of view. For Vega is so bright that it tends to overwhelm fainter stars nearby, and the comparison stars that Struve employed may not have been as distant as he assumed, which would have introduced systematic errors into his parallax determination. And additionally, the great brightness of Vega itself posed challenges for the precise measurement of its position, challenges that were less severe for Bessel's much fainter target star, 61 Cygni, which could be observed under more favorable conditions and compared with stars of similar brightness. Yet despite these difficulties and the overestimation of his result, Struve deserves recognition as one of the pioneers of stellar parallax measurement, for he had demonstrated that such measurements were possible with the instruments of his day, and he had contributed to the growing body of evidence that would soon convince the astronomical community that the parallax problem had at last been solved, and his observatory at Dorpat would continue to produce important astronomical work for many decades thereafter, cementing Estonia's place in the history of observational astronomy. And now we must turn our attention southward, far southward indeed, to the Cape of Good Hope at the southern tip of Africa, where another astronomer was making observations that would prove to be of the greatest significance, though he himself remained uncertain of their value for many years. And this astronomer was Thomas Henderson, a Scotsman who had been appointed as His Majesty's astronomer at the Cape in 1831, a position that placed him at one of the most southerly permanent observatories in the world at that time, with access to portions of the sky that were forever hidden from observers in Europe, including some of the most interesting and potentially nearest stars in the heavens. Henderson had been born in Dundee in 1798 and had come to astronomy by a somewhat indirect route. Having trained originally as a lawyer and practiced that profession for several years before his mathematical talents and his interest in celestial mechanics brought him to the attention of the astronomical establishment. And he had made his reputation through careful calculations of cometary orbits and other problems of positional astronomy. Work that was highly valued in an age when accurate star catalogues and ephemerides were essential tools for navigation and surveying. And it was this reputation that had led to his appointment at the Cape, a position of some prestige though also of considerable hardship. For the Cape Observatory in those early years was not yet the well-equipped institution it would later become. The star that drew Henderson's attention was Alpha Centauri, the third brightest star in the night sky and invisible from European latitudes. A brilliant golden point of light in the southern constellation of Centaurus that had long intrigued astronomers who suspected it might be among the nearest stars to our solar system. And the evidence for this suspicion lay in its substantial proper motion, which had been measured at nearly 4 arcseconds per year, a value exceeded only by a handful of other stars and suggestive of relative proximity. And Henderson recognized that Alpha Centauri might therefore be an excellent candidate for the detection of parallax, if such a thing were possible with the instruments at his disposal. The observations were made during the years 1832 and 1833, a period when Henderson was also occupied with a great many other duties at the Cape Observatory, including the fundamental work of cataloguing the positions of southern stars and monitoring various astronomical phenomena, and the parallax measurements were undertaken somewhat opportunistically, whenever conditions permitted and the necessary reference stars were visible, and Henderson employed a mural circle, a type of graduated arc mounted on a wall and aligned precisely with the meridian, to measure the declination of Alpha Centauri as it passed overhead at its highest point each day, comparing these measurements with those of other stars whose positions were presumed to be fixed. By the time Henderson departed from the Cape in May of 1833, having found the climate and the conditions uncongenial to his health, he had accumulated a substantial body of observations that seemed to show a detectable shift in the position of Alpha Centauri over the course of the year, a shift that was consistent with what one would expect from parallax if the star were indeed relatively nearby. And yet Henderson did not immediately publish these results, nor did he announce them to his fellow astronomers. And this hesitation would prove to be of considerable consequence in the subsequent debates over priority and recognition. The reasons for Henderson's delay were rooted in his own uncertainties about the quality of his data and the reliability of his instrument. For the mural circle at the Cape was not a new instrument but rather one that had been in use for some years and whose calibration Henderson had reason to doubt. And he worried that the apparent parallax he had detected might be spurious, an artifact of instrumental errors rather than a genuine cosmic signal. And he had no wish to add his name to the long list of astronomers who had claimed to detect stellar parallax only to be proved wrong by subsequent investigation, a fate that he regarded as worse than the mere failure to make a discovery at all. And so Henderson returned to Scotland, where he was appointed in 1834 as the first Astronomer Royal for Scotland, a position based at the Calton Hill Observatory in Edinburgh, and he carried with him his Cape observations, intending to analyze them more carefully when he had access to better facilities and more time for reflection. And the years passed while he occupied himself with his new duties, and still he did not publish. And still he waited for some confirmation that his data were sound, some assurance that he was not deceiving himself about what he had measured. It was only when news reached Edinburgh of Bessel's successful parallax measurement of 61 Cygni, announced in late 1838, that Henderson was finally stirred to action. For Bessel's work demonstrated beyond reasonable doubt that stellar parallax could indeed be measured with existing instruments. And this gave Henderson the confidence he had lacked, the assurance that his own observations were not merely instrumental noise but might actually represent a genuine detection. And so at last he prepared his results for publication, presenting them to the Royal Astronomical Society in January of 1839, more than 5 years after the observations had been made. The parallax that Henderson announced for Alpha Centauri was remarkably large by the standards of such measurements, amounting to approximately 0.91 arcseconds, a value that if correct would make Alpha Centauri by far the nearest star to our solar system yet measured, closer even than 61 Cygni, and this result was immediately recognized as being of the greatest importance, for it suggested that the distances to the stars varied enormously, with some being relatively nearby and others presumably much more remote, and it opened the prospect of mapping the three-dimensional structure of our stellar neighborhood, a project that would occupy astronomers for generations to come. The true parallax of Alpha Centauri, as we know it today from measurements of exquisite precision made by space-based observatories, is approximately 0.75 arcseconds, corresponding to a distance of about 4 light-years, making it indeed the nearest star system to our own, and Henderson's original measurement was therefore somewhat too large, overestimating the parallax by about 20%, an error that was entirely understandable given the limitations of his instrument and the difficulties of the observations, and which does not diminish the significance of his achievement, for he had correctly identified Alpha Centauri as the nearest star and had measured its distance to within a reasonable margin of error. The irony of Henderson's situation was not lost on his contemporaries, for his observations had predated those of Bessel by several years, and had he published promptly upon his return from the Cape, he rather than Bessel would have been credited with the first successful measurement of stellar parallax, a priority that would have brought him considerable fame and established his reputation for all time. And yet his caution, his reluctance to publish uncertain results, had cost him this honor, and he was left in the position of confirming what another had already demonstrated rather than announcing a wholly new discovery, a fate that seems somewhat unjust but which reflects the genuine difficulty of the decisions that scientists must make about when to publish and when to wait. The question of priority in scientific discovery is never a simple one, and the case of stellar parallax is perhaps more complicated than most, for we have 3 astronomers, working independently at 3 different observatories, who all succeeded in measuring parallax within a span of just a few years, and the assignment of credit among them has been the subject of some discussion and occasional dispute, though the passage of time has generally brought a recognition that all 3 deserved honor for their achievements, each having contributed something essential to the final success. Bessel is generally accorded the primary credit, and not without justice, for his measurement of 61 Cygni was the most careful, the most thoroughly analyzed, and the most convincing to his contemporaries, and it was his announcement in 1838 that truly persuaded the astronomical community that the parallax problem had been solved, and his error analysis set a standard for precision that others would strive to emulate. And for these reasons his name is most often associated with the first stellar parallax measurement, a connection that seems likely to endure. Struve deserves recognition as the first to publish a parallax result, albeit a preliminary and uncertain one, and his work with the great Fraunhofer refractor at Dorpat demonstrated the potential of the new generation of telescopes for this most delicate of measurements. And though his final parallax for Vega proved to be too large, his contributions to observational astronomy were substantial and lasting, and his observatory would continue to produce important work for many decades. Henderson, despite his hesitation and his delayed publication, deserves credit for having measured the parallax of the nearest star system to our own, a discovery of fundamental importance for our understanding of our place in the cosmos, and the circumstances of his work at the Cape, with inadequate instruments and challenging conditions, make his achievement all the more remarkable, and there is something rather touching in his cautious nature, his unwillingness to claim more than he could prove, even at the cost of priority. The disputes over credit that arose in the immediate aftermath of these discoveries have largely faded now, for history has been generous enough to honor all three astronomers, and we may think of them today as collaborators in a great enterprise rather than competitors for a single prize, each having played an essential role in establishing beyond doubt that the stars are suns like our own, scattered through a vast three-dimensional space at distances that can be measured by patient and careful observation. And this knowledge, once gained, could never be lost, and formed the foundation for all subsequent investigations into the structure and scale of the universe. And so, as you settle deeper into your pillow and feel the gentle weight of sleep beginning to gather at the edges of your awareness, you may take comfort in knowing that the universe reveals its secrets not to individual genius alone, but to the collective effort of many minds working toward a common goal, and that the measurement of stellar parallax, that ancient problem that had frustrated astronomers since the days of Tycho Brahe, was solved not by one astronomer but by three, working at observatories separated by thousands of miles, in Königsberg and Dorpat and at the Cape of Good Hope, and their success marked the beginning of a new era in astronomy, an era in which the stars would be known not merely as points of light on a celestial sphere, but as physical objects distributed through an immense three-dimensional space. And the story of how that knowledge was extended and refined is a tale for another time. But for now it is enough to know that the first steps had been taken, and that the universe had revealed itself to be even more wonderful and more vast than anyone had previously imagined. In the year 1839, on a gentle rise of land some 19 kilometers south of St. Petersburg, there came into being an observatory that would shape the course of precision astronomy for generations to come. This was Pulkovo, founded by the decree of Tsar Nicholas I, who understood, as many rulers of his age did, that national prestige could be measured not only in military strength or territorial expanse, but also in the quiet achievements of science. The hill upon which the observatory was built rises only some 75 meters above the surrounding countryside, which may seem modest, but it offered something precious to astronomers, which was a clear and relatively stable atmosphere, removed from the smoke and flickering lights of the growing city, and it provided a firm foundation of ancient rock upon which the most delicate instruments could be mounted without fear of the subtle tremors that plague less fortunate locations. The design of the observatory buildings was entrusted to the architect Alexander Bryalov, brother of the famous painter Karl Bryalov, and he brought to the task a refined neoclassical sensibility that resulted in structures of considerable elegance and practical efficiency. The main building extended in a long, graceful arc, with the central dome rising above the rest to house the great refractor, while the wings stretched outward to accommodate the meridian instruments and the living quarters of the astronomers who would dedicate their lives to the painstaking work of measuring the heavens. Bryalov understood that an observatory is not merely a place of science but also a kind of temple to human curiosity, and his design reflected this understanding through proportions that were harmonious and materials that were chosen for their durability, so that the building might serve its purpose for centuries to come, as indeed it has, though not without interruption, as we shall gently mention in due course. The soul of any observatory, however, lies not in its architecture but in the quality of its instruments and the dedication of its observers. And in both respects Pulkovo was blessed from its very beginning. The great refractor that became the centerpiece of the observatory was built by the Munich firm of Merz and Mahler, successors to the legendary workshop of Joseph von Fraunhofer, whose name we have encountered before in connection with the Königsberg heliometer used by Friedrich Bessel. This new telescope possessed an objective lens of 15 inches in diameter, which is to say approximately 38 centimeters. And at the time of its installation it was the largest refracting telescope in the world, a distinction it would hold for some years before being surpassed by later instruments in other lands. The optical quality of the lens was exceptional, as one would expect from the Fraunhofer tradition, and the mounting was designed with the utmost care to allow for the smooth and precise movements necessary for the observation of double stars and the measurement of stellar positions. The man appointed as the first director of this magnificent new institution was Friedrich Georg Wilhelm Struve, whom we have already met in our discussion of the earliest parallax measurements, and whose determination of the distance to Vega had placed him among the pioneers of stellar distance measurement alongside Bessel and Henderson. Struve was by this time in his mid-50s. With decades of experience in the patient work of positional astronomy, and he brought to Pulkovo not only his personal expertise but also a comprehensive vision of what a great observatory might accomplish through systematic and sustained observation. He understood that the measurement of stellar parallax, while dramatic in its implications for our understanding of the universe, was but one aspect of a broader program of astrometry, which is the careful determination of the positions and motions of celestial objects, and he set about organizing the work of Pulkovo along lines that would make it the world's leading center for such measurements. The program that Struve established at Pulkovo was characterized above all by its systematic nature, for he believed that the advancement of astronomy depended not upon occasional brilliant observations but upon the steady accumulation of precise measurements made according to consistent methods over extended periods of time. Under his direction, the astronomers of Pulkovo undertook to observe and catalogue the positions of thousands of stars, paying particular attention to the double stars that had long been Struve's special interest. These binary systems, in which two stars orbit around their common center of gravity, held fascination not only for their beauty when seen through the eyepiece but also for their scientific value, since the careful measurement of their orbital motions could reveal information about the masses of stars and the operation of gravitational forces at stellar distances. In 1847, Struve published a comprehensive catalogue of double stars that represented the culmination of many years of patient observation, much of it conducted at Pulkovo with the great Merz refractor. This catalogue contained measurements of 2,874 double star systems, recording for each pair the angular separation between the components, the position angle indicating the direction from the brighter star to the fainter, and various other details relevant to the understanding of these celestial couples. The precision of these measurements was remarkable for the time, and the catalogue quickly became an essential reference work for astronomers throughout Europe and beyond who wished to study the slow orbital dances of binary stars or to use them as tests of their own instrumental accuracy. The work at Pulkovo extended far beyond the great refractor, for the observatory was equipped with a range of instruments suited to different aspects of positional astronomy. Among the most important of these was a meridian transit instrument constructed by the Hamburg firm of Adolf Repsold and Sons, who were among the foremost makers of precision astronomical instruments in the 19th century. A transit instrument is designed for a very specific purpose, which is to observe stars as they cross the meridian, that imaginary line running from due north to due south through the zenith, And by timing these crossings with extreme precision, astronomers can determine the right ascensions of stars, which is one of the two coordinates needed to specify a star's position on the celestial sphere. The Repsol transit instrument at Pulkovo was a masterpiece of mechanical engineering, with a telescope mounted so that it could move only in the plane of the meridian, rotating about a horizontal east-west axis that was adjusted with extraordinary care to ensure perfect alignment. The telescope itself was of modest aperture, for in transit work the critical factors are the stability of the mounting and the precision of the graduated circles that measure the angles of observation, rather than the light-gathering power of the objective. Night after night, the observers at Pulkovo would watch through this instrument as stars drifted into the field of view, carried by the rotation of the Earth, and at the precise moment when each star crossed the central wire of the eyepiece reticle, they would record the time using chronometers of the finest quality, thereby building up an ever more accurate picture of the positions of stars across the sky. The reputation of Pulkovo for accuracy grew steadily through the 1840s and 50s, until the phrase Pulkovo precision became a byword among astronomers for the highest standard of observational care. This reputation was not acquired through any single dramatic achievement but through the consistent quality of measurements made year after year, measurements that other observatories found they could rely upon when checking their own work or when seeking reference positions for newly discovered objects. The culture of precision that Struve established permeated every aspect of the observatory's operations, from the maintenance of the instruments to the training of the observers to the careful reduction of the raw observations into final catalogued positions. While the stellar work proceeded at Pulkovo, the observatory also played a central role in one of the great geodetic enterprises of the 19th century, the measurement of an enormous arc of meridian extending from the mouth of the Danube in the south to the shores of the Arctic Ocean in the north. This project, which spanned the years from 1816 to 1852, was designed to determine with precision the shape of the Earth, which is not a perfect sphere but rather an oblate spheroid, slightly flattened at the poles and bulging at the equator due to the planet's rotation. By measuring the length of a degree of latitude at different points along the meridian, geodesists could calculate the exact amount of this flattening, information that was essential for accurate map-making and navigation. The arc measured under Struve's direction extended through some 25 degrees of latitude, covering a distance of approximately 2,820 kilometers. From a point near Ismail on the Danube to the Norwegian coast at Hammerfest, well within the Arctic Circle. This was the longest arc of meridian that had ever been measured at that time, and the undertaking required the cooperation of astronomers and surveyors from the Russian Empire, Norway, and Sweden, working in conditions that ranged from the mild summers of the southern provinces to the harsh and unforgiving environment of the far north, where observations had to be made during the brief periods when the weather permitted and the midnight sun provided continuous illumination. The techniques used in the arc measurement combined traditional surveying methods with astronomical observations of the highest precision. On the ground, surveyors measured the distances between a chain of triangulation points, using the methods that geodesists had refined over more than a century. At each major station, astronomers determined the latitude by observing the altitudes of stars as they crossed the meridian, and here the expertise developed at Pulkovo proved invaluable, for the accuracy of the final result depended critically upon the precision of these astronomical observations. The instruments, the methods of observation, and the procedures for reducing the data all benefited from the culture of precision that Struve had cultivated, and the completed arc measurement stood for many decades as a monument to international scientific cooperation and meticulous observational practice. Friedrich Struve continued as director of Pulkovo until 1862, when advancing age and declining health compelled him to relinquish his responsibilities. He passed away in 1864, having seen the observatory he directed grow from a new institution into the acknowledged world leader in positional astronomy. But the legacy of Pulkovo did not depend upon any single individual, however distinguished, for Struve had built an institution and a tradition that could be carried forward by others, and among those others was his own son, Otto Wilhelm Struve, who succeeded his father as director and continued the program of precision astrometry for another generation. Otto Wilhelm Struve had grown up in the environment of astronomical observation, learning from childhood the patient discipline required for work at the eyepiece, and by the time he assumed the directorship, he was already an accomplished observer with decades of experience. Under his leadership, Pulkovo continued its systematic programs of stellar observation, and the younger Struve himself made significant contributions to several areas of astrometry. Among his achievements was a refined determination of the constant of precession, which describes the slow wobble of Earth's axis that causes the celestial pole to trace out a circle among the stars over a period of roughly 26,000 years. Precession had been known since the time of the ancient Greek astronomer Hipparchus, who had noticed that the positions of stars relative to the equinoxes shifted slowly over time, but the precise rate of this motion required careful measurement extending over many years, and the value of the constant had been refined repeatedly as observational techniques improved. Otto Wilhelm Struve brought to this problem the full resources of Pulkovo, examining the observations accumulated over the decades since the observatory's founding and combining them with historical data from earlier epochs to derive an improved value for the precessional constant. This work exemplified the approach that made Pulkovo great: the patient accumulation of precise observations and their careful analysis to extract knowledge about the fundamental motions of the celestial sphere. The meridian observations continued under the younger Struve's direction, with the Repsol transit instrument and its successors tracking stars night after night, building up catalogues of positions that served as the foundation for astronomical work throughout the scientific world. The techniques of observation were refined over time, as astronomers learned to account for ever more subtle sources of error, from the flexure of the telescope tube under its own weight to the personal equation of the observer, that small but measurable delay between the moment when a star actually crosses the wire and the moment when the observer registers the crossing. At Pulkovo, these matters were studied with characteristic thoroughness, and methods were developed to minimize their effects or to correct for them mathematically. The international standing of Pulkovo remained high throughout the latter half of the 19th century, and astronomers from many nations came to learn the methods practiced there or to compare their own observations with the Pulkovo standards. The observatory served as a kind of reference point for the astronomical community, a place where positions were measured with such care that they could be trusted when discrepancies arose between the results of different institutions. This role as an arbiter of precision was perhaps the highest achievement of the Pulkovo tradition, for it meant that the painstaking work of the observers, carried out night after night in the cold domes, contributed not only to the catalogues bearing the observatory's name but also to the integrity of astronomical measurement worldwide. The physical circumstances of observation at Pulkovo were demanding, as they are at any observatory, but the Russian climate presented particular challenges that the astronomers met with characteristic stoicism. The winters were long and dark and bitterly cold, and the observers wrapped themselves in heavy clothing as they worked at their instruments, keeping one eye adapted to the darkness while the other made careful measurements through the eyepiece. The summers were short but offered long twilight hours during which certain observations could not be made because the sky remained too bright, and the astronomers turned to other tasks, reducing their winter observations, maintaining their instruments, and preparing for the next season of intensive work. Through all these years, the methods established by the elder Struve continued to guide the observatory's work. Observations were recorded in standard formats, reduced according to established procedures, and accumulated in archives that grew steadily decade by decade. The catalogues that emerged from this work were monuments of patience and precision, listing thousands upon thousands of stellar positions with accuracies that pushed against the fundamental limits imposed by the Earth's atmosphere and the resolving power of the telescopes. Each entry in these catalogues represented the labor of many nights, the careful repetition of observations to average out errors, and the meticulous application of corrections for instrumental effects, atmospheric refraction, aberration, precession, and all the other influences that the astronomer must account for before claiming to know where a star truly lies. As the 19th century drew toward its close, the program of parallax measurement continued at Pulkovo alongside the broader work of positional astronomy. The techniques had been refined since the pioneering days of the 1830s, and the accuracies achievable had improved correspondingly, but the fundamental challenge remained the same: to detect the tiny annual shifts in stellar positions caused by the Earth's orbit around the Sun. The Great Refractor, now no longer the world's largest but still an instrument of formidable capability, was turned upon stars suspected of being relatively nearby, and the observers measured and measured again, accumulating data that might eventually yield a parallax angle and thus a distance. The legacy of Pulkovo extends in many directions, through the catalogues that bear its name, through the geodetic measurements that helped define the shape of the Earth, through the techniques of precision observation that were developed and refined within its walls, and through the astronomers who trained there and carried the Pulkovo tradition to other institutions around the world. The phrase Pulkovo precision remained meaningful to astronomers well into the 20th century, a reminder that the careful work of positional astronomy, unglamorous though it might seem compared to the more dramatic discoveries of astrophysics, formed an essential foundation upon which all astronomical knowledge ultimately rested. And so the observatory founded by Tsar Nicholas I, designed by Alexander Bryalov, and led for its crucial early decades by Friedrich and Otto Wilhelm Struve, took its place in the history of our slow and patient effort to measure the distances to the stars, an effort that required not brilliant inspiration so much as steady dedication, not dramatic breakthroughs so much as the gradual accumulation of precise measurements, night after night, year after year, in the service of knowledge that would outlast any individual observer and contribute to the ever-growing understanding of our place among the distant suns. In the quiet hours before dawn, when the sky begins to pale and the stars grow dim, there is a moment of perfect stillness that astronomers have always known, that gentle pause between the labors of the night and the slow awakening of the day. And it was in such moments, across the middle decades of the 19th century, that a profound transformation began to take hold in the practice of measuring the heavens, a change so fundamental and so far-reaching that it would eventually reshape everything astronomers understood about how to record the positions of stars. This transformation came not from a new telescope, nor from a more refined mathematical theory, but from a thin sheet of metal coated with chemicals, exposed to light, and developed in a darkened room. The photograph, that curious invention of the 1830s, would gradually find its way into the observatory dome, and there it would begin to change the ancient art of astrometry in ways that no one could have fully anticipated when the first faint images of celestial objects began to appear on silver-coated plates. The story of astronomical photography begins, as many stories in science do, with a series of modest experiments that seemed at first to have little practical value. In the year 1840, a physician and chemist named John William Draper, working in the city of New York, turned a small telescope toward the moon and attempted something that had never before been accomplished. Using the daguerreotype process, which had been announced to the world only the previous year by Louis Daguerre in Paris, Draper sought to capture an image of our nearest celestial neighbor on a silver-coated copper plate. The daguerreotype process was delicate and demanding, requiring the plate to be polished to a mirror finish, sensitized with iodine vapors, exposed to light, and then developed over heated mercury. Draper's first attempts were disappointing, producing only faint smudges that barely suggested the lunar disk, but he persisted through the winter months, refining his technique and extending his exposure times. In March of 1840, after an exposure of approximately 20 minutes, he succeeded in obtaining a recognizable image of the moon, showing the dark and light regions of its surface with tolerable clarity. The image was small, measuring only about an inch across, and it lacked fine detail, but it represented something genuinely new in the long history of astronomy. For the first time, light from a celestial body had been captured and preserved through a purely chemical process, without the intervention of the human eye and hand. Draper's daguerreotype of the moon was not, in truth, useful for any scientific measurement, but it demonstrated that such things were possible, and it planted a seed that would grow steadily over the following decades. The daguerreotype process, for all its ingenuity, was poorly suited to astronomical work. The plates were not very sensitive to light, requiring long exposures that were difficult to achieve when tracking the apparent motion of celestial objects. The images could not be easily reproduced, and the silver surfaces were fragile and easily damaged. Nevertheless, astronomers continued to experiment with the new technology, drawn by the tantalizing possibility of obtaining permanent records of celestial phenomena. A particularly significant advance came in 1850, when a father and son working at the Harvard College Observatory succeeded in capturing the first photograph of a star. William Cranch Bond, who served as the first director of the Harvard Observatory, and his son George Phillips Bond, had been following the development of photography with great interest, recognizing its potential value for astronomical research. In collaboration with a Boston photographer named John Adams Whipple, who possessed considerable skill in the technical aspects of the daguerreotype process, the Bonds undertook a systematic effort to photograph celestial objects through the observatory's 15-inch refractor, which was at that time one of the largest telescopes in the world. Their early attempts to photograph stars met with consistent failure, the faint points of light proving too dim to register on the insensitive plates. But on the night of July 16 and 17, 1850, after many months of patient effort, they succeeded in obtaining a daguerreotype of Vega, the brilliant blue-white star in the constellation Lyra. The image showed Vega as a small bright spot surrounded by the circular diffraction pattern produced by the telescope's optics, and while it was far from impressive as a visual record, it marked a milestone of considerable importance. A star, that distant sun lying so far beyond the reach of human travel, had left its trace upon a metal plate, captured by nothing more than the patient accumulation of its own ancient light. The Bonds continued their photographic experiments over the following years, obtaining images of the Moon that surpassed anything previously achieved. And George Phillips Bond in particular became convinced that photography would eventually transform astronomical measurement. He recognized that a photograph could record the positions of many stars simultaneously, capturing their relative locations in a way that would be difficult or impossible for a human observer working with a micrometer at the eyepiece. He also understood that photographs could be measured at leisure, in the comfort of a warm room during daylight hours, rather than requiring the astronomer to spend long cold nights at the telescope. These advantages seemed compelling, but the technical obstacles remained formidable, and the daguerreotype process was simply too insensitive and too cumbersome for routine astronomical work. Across the Atlantic, other investigators were pursuing similar lines of research. Warren de la Rue, an English businessman and amateur scientist of considerable means, became deeply interested in astronomical photography during the 1850s. De la Rue possessed both the financial resources and the technical skill to construct specialized equipment for celestial photography, and he devoted particular attention to obtaining detailed images of the Sun and Moon. Working from his private observatory at Cranford in Middlesex, de la Rue developed techniques for photographing the Sun that would prove valuable for studying sunspots and other solar phenomena. He also obtained lunar photographs of remarkable quality, showing craters and mountain ranges with a clarity that impressed even skeptical astronomers. In 1857, de la Rue presented a proposal to the British Association for the Advancement of Science, suggesting that photography might be employed to create comprehensive catalogues of stellar positions. He envisioned a systematic program in which photographs of the entire sky would be taken and measured, producing a record of stellar positions that would be both more complete and more accurate than anything that could be achieved through traditional visual observation. The proposal was visionary, perhaps too visionary for its time, and the technical means to realize such an ambitious project did not yet exist. But the idea had been planted, and it would continue to grow in the minds of astronomers over the following decades. The daguerreotype process, despite its historical importance, was soon superseded by newer photographic technologies that offered significant advantages for scientific work. The wet collodion process, introduced in 1851 by Frederick Scott Archer, represented a substantial improvement in sensitivity and image quality. In this method, a glass plate was coated with a solution of collodion, which is guncarton dissolved in ether, mixed with potassium iodide. The coated plate was then immersed in a solution of silver nitrate, which reacted with the iodide to form light-sensitive silver iodide crystals within the collodion film. The plate had to be exposed while still wet, hence the name of the process, and developed immediately afterward, which imposed considerable practical constraints on the photographer. Nevertheless, wet collodion plates were substantially more sensitive than daguerreotypes, and they produced negatives from which multiple positive prints could be made, a tremendous advantage for scientific work. Astronomers adopted the wet collodion process with enthusiasm, and the quality of celestial photographs improved markedly during the 1860s and 70s. Among the most accomplished practitioners of early astronomical photography was Lewis Morris Rutherford, a wealthy New York lawyer who abandoned his legal career to pursue scientific research. Rutherford established a private observatory on the roof of his family home in Manhattan, where he devoted himself to the development of techniques for celestial photography. He recognized early on that the objectives of conventional refracting telescopes, which were designed to produce sharp visual images, did not necessarily perform well for photographic work. This was because the chemical emulsions used in photography were most sensitive to blue and violet light, while the human eye is most sensitive to yellow and green. And telescope lenses that brought visual wavelengths to a sharp focus often produced blurred images at the wavelengths to which photographic plates responded. To address this problem, Rutherford designed and constructed specialized lenses that were corrected for photographic rather than visual wavelengths, producing what he termed astrographic objectives. These lenses, which represented a significant technical achievement, enabled Rutherford to obtain stellar photographs of unprecedented quality. During the 1860s, he photographed numerous star fields, and he developed methods for measuring the positions of stars on his photographic plates with considerable precision. Rutherford's work demonstrated that photography could indeed be used for serious astrometric measurements, and his techniques influenced many later investigators. The wet collodion process, despite its advantages over the daguerreotype, still presented serious obstacles for astronomical photography. The requirement that plates be exposed while wet meant that the astronomer had to coat, sensitize, expose, and develop each plate in rapid succession, a demanding procedure that left little room for error. Long exposures were particularly problematic, as the collodion film tended to dry out before the exposure was complete, rendering the plate useless. This limitation was especially troublesome for photographing faint objects, which required extended exposure times to accumulate sufficient light. The astronomical community eagerly awaited the development of dry plates, which would retain their sensitivity over extended periods and could be exposed for as long as necessary. Dry plate processes were developed gradually during the 1870s, and by the early 1880s, commercially manufactured dry plates had become available that were well suited to astronomical work. These plates could be prepared in advance, stored for weeks or months, exposed for hours at a time, and developed at the astronomer's convenience. The liberation from the constraints of wet collodion opened new possibilities for celestial photography, and astronomers were not slow to exploit them. The event that perhaps most dramatically revealed the potential of photography for astrometric work occurred in the Southern Hemisphere, at the Royal Observatory at the Cape of Good Hope, in the year 1882. David Gill, a Scottish astronomer who had been appointed Her Majesty's astronomer at the Cape in 1879, was an energetic and innovative scientist with a particular interest in stellar positions and celestial mechanics. In September of 1882, a brilliant comet appeared in the southern skies, becoming so bright that it was visible in broad daylight and attracting worldwide attention. Gill recognized the opportunity to obtain photographs of this spectacular visitor, and he arranged to have a portrait camera attached to his observatory's equatorial telescope. The resulting photographs of the Great Comet of 1882 were striking images that captured the comet's long, graceful tail stretching across the star fields of the southern sky. But when Gill examined these photographs closely, he noticed something that excited him even more than the comet itself. The background of each photograph was filled with the images of thousands of stars, their positions recorded with apparent precision on the photographic plates. Gill realized immediately that photography offered a means of surveying the stellar sky that would be vastly more efficient than traditional visual methods. A single photograph could record the positions of more stars in a few hours than an observer could measure in months of painstaking work at the eyepiece. Gill's photographs of the Great Comet led directly to one of the most ambitious undertakings in the history of astronomy. Inspired by the wealth of stellar data revealed in his comet photographs, Gill proposed a comprehensive photographic survey of the southern sky, and this proposal, combined with similar ideas that had been circulating among European astronomers, eventually gave rise to the Carte du Ciel project. Announced in 1887 at an international congress of astronomers held in Paris, the Carte du Ciel was an audacious plan to photograph the entire sky and to produce both a photographic atlas and a catalogue of stellar positions. The project was divided among observatories in both hemispheres, each responsible for photographing and measuring a designated zone of the sky. The Carte du Ciel represented the first truly international astronomical enterprise of such scope, and it consumed the energies of observatories around the world for decades. The project was never fully completed, as its ambition exceeded the technical means available, but it demonstrated beyond question that photography had become an essential tool for astrometric work. Yet for all its promise, photography introduced complications of its own that early practitioners had not anticipated. The photograph, which seemed to offer an objective record free from the biases of human observation, turned out to carry its own subtle sources of error that required careful understanding and correction. One such source was the tilt of the photographic plate relative to the optical axis of the telescope. If the plate was not precisely perpendicular to the incoming light, the images of stars would be displaced from their true positions by amounts that varied across the field of view, introducing systematic errors into the measured coordinates. Great care was needed in mounting the plate holder to ensure proper alignment, and methods were developed for detecting and correcting residual tilt errors in the measurement process. The photographic emulsion itself was another source of concern. The silver halide crystals that formed the light-sensitive layer were not uniformly distributed, and local variations in the density and sensitivity of the emulsion could affect the recorded positions of stellar images. Bright stars produced larger images than faint stars, and the centers of these images might be displaced from the true position of the star by irregularities in the emulsion. The glass plates on which the emulsion was coated were not perfectly flat, and slight curvature or local distortions could introduce additional positional errors. Astronomers developed techniques for mapping and correcting these effects, but the process added complexity to what had initially seemed a straightforward recording method. Atmospheric refraction, which had long troubled visual observers, affected photographic observations as well, bending the light from stars by amounts that depended on their altitude above the horizon and on the wavelength of the light. Because photographic emulsions were sensitive to a range of wavelengths, and because different wavelengths were refracted by different amounts, the effective position recorded on the plate was a kind of average that did not correspond precisely to any single well-defined direction. This chromatic effect of atmospheric refraction required careful modeling and correction, especially for observations made at low altitudes. Despite these complications, the advantages of photography for astrometric work were compelling, and the transition from visual to photographic methods proceeded steadily through the closing decades of the 19th century. The photograph offered permanence, allowing observations to be preserved indefinitely and remeasured with improved techniques as they became available. It offered simultaneity, capturing the positions of many stars in a single exposure and eliminating errors that might arise from measuring stars one at a time over extended periods. And it offered objectivity of a certain kind, replacing the variable responses of different observers with a chemical process that, while imperfect, was at least consistent and reproducible. The quest to measure the distances of stars, which had motivated Tycho Brahe and Bradley and Bessel, now had a powerful new instrument at its disposal: and the astronomers of the late 19th century looked forward with quiet confidence to the advances that photography would bring to their ancient science. In the closing decades of the 19th century, as astronomers around the world continued their patient work of measuring stellar positions and searching for the subtle signatures of parallax, there arose an idea of remarkable ambition, an idea that would require not just the efforts of a single observer or even a single institution, but the coordinated labors of observatories scattered across the entire globe. This was the Carte du Ciel, which translates from the French as the map of the sky, and it represented the first truly international astronomical project, a collaborative endeavor that sought to photograph and catalogue every star visible through a modest telescope, creating a permanent record of the heavens that would serve astronomers for generations to come. The story of how this project came to be, how it was organized and executed, and how it ultimately both succeeded and fell short of its grand vision, is a gentle and instructive tale about the nature of scientific ambition, the challenges of international cooperation, and the way that technological progress can sometimes overtake even the most carefully laid plans. The origins of the Carte du Ciel can be traced to the rapid improvements in astronomical photography that occurred during the 1870s and 1880s, improvements that transformed what had been a curiosity into a genuine scientific tool. We have already spoken of the work done at various observatories to apply photography to the measurement of stellar positions, and by the middle of the 1880s it had become clear that photographic plates offered certain advantages over visual observation that were difficult to ignore. A photograph could record the positions of hundreds or even thousands of stars in a single exposure, capturing them all simultaneously and preserving their relative positions with a fidelity that would be extremely tedious to achieve through visual methods. Moreover, a photograph constituted a permanent record, one that could be measured and remeasured over the years, checked for errors, and compared with photographs taken at later dates to detect changes in stellar positions that might indicate proper motion or parallax. The potential of photography for astronomical research seemed almost limitless, and it was natural that astronomers should begin to dream of applying this new tool to the most comprehensive survey imaginable. The man who did more than anyone else to transform this dream into a concrete plan was Admiral Ernest Mouchez, who served as the director of the Paris Observatory from 1878 until his death in 1892. Mouchez was an interesting figure in the history of astronomy, for he came to the directorship not from a background in observational astronomy but from a distinguished career in the French Navy, where he had made his reputation as a hydrographer and chart maker, surveying coastlines and producing navigational charts of exceptional accuracy and utility. This experience gave Mouchez a particular appreciation for the value of systematic mapping and precise measurement, and when he took up his position at Paris, he brought with him the practical sensibilities of a man accustomed to organizing large surveying projects and coordinating the work of many individuals toward a common goal. Under his direction, the Paris Observatory became a center for the development of astronomical photography, and it was there that the brothers Paul and Prosper Henry developed a new type of photographic telescope, known as an astrograph, that was specifically designed to produce sharp stellar images across a wide field of view. The Henry brothers were skilled opticians and instrument makers, and their astrograph represented a significant advance over earlier photographic telescopes. It employed a carefully figured objective lens with an aperture of 33 centimeters, or approximately 13 inches, and a focal length of 343 centimeters, which is nearly 11¼ feet. These particular dimensions were chosen with great care, for they produced images at a very convenient scale, one where 60 arcseconds of sky corresponded to exactly 1 millimeter on the photographic plate. This meant that angular measurements on the sky could be converted to linear measurements on the plate, and vice versa, through a simple and elegant relationship, making the subsequent work of measurement considerably more straightforward. The telescope was designed to photograph a field approximately 2 degrees on a side, and the images it produced were of remarkable quality, showing stars as small, well-defined points that could be measured with considerable precision. It was the success of the Henry brothers' astrograph that convinced Mouchez that the time was ripe for an audacious undertaking, a systematic photographic survey of the entire sky that would record the positions and brightnesses of millions of stars. But Mouchez understood that such a project was far beyond the resources of any single observatory, even one as well equipped as Paris. The sky is vast, and the work of photographing it systematically, plate by overlapping plate, would require many telescopes operating over many years. Moreover, the sky is divided between the northern and southern hemispheres, and no single observatory could observe the entire celestial sphere. What was needed was international cooperation on an unprecedented scale, a pooling of resources and effort that would unite observatories around the world in a common scientific enterprise. To bring this vision into reality, Mouchez issued invitations to the directors of the world's leading observatories, asking them to send representatives to Paris in April of 1887 for a congress that would consider the feasibility of an international photographic survey of the heavens. The response was remarkable, and when the congress convened on the 18th of April, it brought together 56 delegates from observatories in 17 countries, representing institutions scattered across Europe, the Americas, and the Southern Hemisphere. For several days, these astronomers discussed the technical requirements of such a survey, debated the division of labor among participating observatories, and considered the standards and procedures that would need to be adopted to ensure that the work done at one institution would be compatible with that done at another. By the time the Congress concluded, a detailed plan had been drawn up and 18 observatories had committed themselves to participating in what would become known as the Carte du Ciel. The plan that emerged from the Paris Congress was ambitious in the extreme. The project would actually comprise 2 separate but related undertakings. The first was the Carte du Ciel proper, the photographic atlas of the sky, which would consist of long-exposure photographs reaching down to stars of the 14th magnitude, capturing objects far too faint to be seen with the naked eye and recording them for posterity. These plates were intended primarily as a visual record, a comprehensive portrait of the heavens that would preserve the appearance of the sky as it existed in the late 19th century. The second component was the astrographic catalogue, which would employ shorter exposures to record stars down to approximately the 11th magnitude, and for which the positions of every star on each plate would be carefully measured and tabulated. It was estimated that the catalogue portion alone would include some 3 million stars, making it by far the most comprehensive stellar catalogue ever attempted. To ensure uniformity across the work done at 18 different observatories, the Congress established strict standards for the equipment to be used and the procedures to be followed. Every participating observatory would construct or acquire an astrograph built to the same specifications as the Henry brothers instrument, with the same 33 cm aperture, the same 343 cm focal length, and the same plate scale of 60 arcseconds per millimeter. The photographic plates would be of standard dimensions, 16 centimeters square, and each would be exposed using standardized procedures to ensure consistent results. The sky was divided into zones of declination, strips running around the celestial sphere parallel to the celestial equator, and each participating observatory was assigned responsibility for photographing and measuring the stars within its designated zone. The observatories in the northern hemisphere would cover the northern portions of the sky, while those in the southern hemisphere would attend to the southern regions, and together they would encompass the entire celestial sphere. Among the most important contributors to the organization of the project was David Gill, whom we have already encountered in connection with his pioneering work in stellar photography at the Royal Observatory at the Cape of Good Hope. Gill had demonstrated through his own observations that photography could be used to determine stellar positions with remarkable precision, and his enthusiasm for the medium made him a natural advocate for the Carte du Ciel. At the Paris Congress, Gill played a leading role in discussions of technical standards and procedures, drawing on his extensive practical experience to help shape the guidelines that would govern the project. He was also instrumental in organizing the participation of observatories in the Southern Hemisphere, where the Cape Observatory would take responsibility for photographing a substantial zone extending from declination -40 degrees to -52 degrees. This was known as the Cape Zone, and under Gill's direction it would become one of the most successfully completed portions of the entire project. Once the photographs were taken, the work of extracting precise stellar positions from them required specialized measuring machines of considerable sophistication. Several instrument makers developed devices for this purpose, but among the most widely used were those designed and manufactured by the firm of Repsold and Sons in Hamburg, the same Repsold family whose heliometers and other precision instruments had played such an important role in the history of parallax measurement. The Repsold measuring machines employed finely graduated scales and precision screws to allow an operator to position crosshairs on each stellar image and read off its coordinates on the plate to within a few micrometers. The process was painstaking and time-consuming, requiring many hours of careful work for each plate, and since the complete survey would ultimately involve tens of thousands of plates, each containing hundreds or thousands of measurable stars, the total labor required was almost beyond imagining. Other measuring engines were developed by different manufacturers and individual observatories, but all were designed with the same goal in mind: to transform the photographic images into numerical positions that could be compiled into catalogues and published for the use of astronomers everywhere. The work of the Carte du Ciel began in earnest in the early 1890s, with participating observatories undertaking the systematic photography of their assigned zones and commencing the laborious process of plate measurement. The early years of the project saw steady progress, with plates accumulating in observatory archives and measurements being compiled for eventual publication. But as the years passed and the true magnitude of the undertaking became apparent, the project began to encounter difficulties that would ultimately prevent its completion in the manner originally envisioned. The work was simply too vast for the resources available. Each observatory had many other responsibilities and could devote only a portion of its efforts to the Carte du Ciel, and the measuring work in particular proved to be so tedious and time-consuming that it fell further and further behind the photography. Staff turnover, funding shortages, and the disruptions caused by 2 world wars all took their toll, and by the middle of the 20th century it was clear that the project would never be finished according to the original plan. Some zones were completed and published, representing heroic efforts by the observatories responsible for them, while others remained partially done or were abandoned entirely. The photographic atlas portion, the Carte du Ciel proper, fared somewhat better than the astrographic catalogue, as the plates themselves constituted a permanent record even if they were never systematically measured. But even here the coverage remained incomplete. By the 1960s and 1970s, when the project was finally acknowledged to have effectively ended, something like 80 years had passed since the hopeful gathering in Paris, and the astronomical world had changed beyond recognition. New technologies, including electronic detectors and eventually space-based observatories, had rendered the original photographic methods obsolete, offering capabilities that the founders of the Carte du Ciel could never have imagined. The project stands as a monument to both the ambition and the limitations of 19th-century astronomy, a reminder that even the best-laid plans must contend with the practical realities of time, resources, and technological change. And yet, to describe the Carte du Ciel simply as a failure would be to miss an important part of its legacy, for the work that was completed proved to be of considerable scientific value, particularly for the measurement of stellar parallaxes and proper motions. The plates that were taken and the positions that were measured represented a snapshot of the sky at a particular moment in time, the late 19th and early 20th centuries. And as the decades passed, this snapshot became increasingly valuable precisely because it was old. By comparing the positions of stars as recorded on Carte du Ciel plates with positions measured at later epochs, astronomers could detect the slow drifts that betrayed stellar motion through space. And by analyzing these motions, they could identify stars that were likely to be nearby and thus good candidates for parallax measurement. The systematic nature of the survey, covering large areas of sky with uniform procedures and equipment, meant that the resulting data could be analyzed statistically in ways that would have been impossible with the more heterogeneous observations of earlier eras. The plate material itself proved useful in unexpected ways as well. Even plates that had never been formally measured could be retrieved from observatory archives and examined with modern measuring machines, which were far more efficient than the laborious manual devices of the 19th century. Computer-controlled measuring engines developed in the late 20th century could scan a photographic plate and extract the positions of all the stars it contained in a fraction of the time that would have been required using traditional methods. And this made it practical to exploit the Carte du Ciel archive in ways that would have astonished Mouchez and his contemporaries. The positions derived from these remeasurements, when combined with modern observations, provided baselines of a century or more for the determination of proper motions, and this in turn fed into improved understanding of stellar distances and the structure of our galaxy. In a curious way, then, the Carte du Ciel accomplished something different from what its founders intended, but something valuable nonetheless. It did not provide the definitive photographic atlas and catalogue of its time, for it was never finished and was in any case superseded by better methods before it could be completed. But it did produce a vast archive of photographic material that has continued to serve astronomy long after the original project was abandoned, and it established precedents for international scientific cooperation that would prove influential in later endeavors. The experience of organizing and managing a project of such complexity, with its challenges of standardization and coordination across national boundaries and institutional cultures, provided lessons that informed subsequent international collaborations, including those that would eventually lead to space-based parallax missions of extraordinary precision. As you lie there listening to this account of a grand project that did not quite achieve its goals, you might find a certain comfort in the knowledge that even incomplete efforts can leave behind something of lasting worth. The astronomers who devoted years of their lives to photographing and measuring their assigned zones of the Carte du Ciel could not have known that their work would be superseded, could not have foreseen the electronic and computational revolutions that would transform their science. They worked with the tools and methods available to them, doing their best to contribute to an enterprise they believed would benefit astronomy for generations to come. And in this they were not entirely wrong. The plates they took still exist, stored in observatory archives around the world, and the measurements they made still have their uses. The story of the Carte du Ciel is not a story of failure, but rather a story of human endeavor encountering the limits of what can be accomplished with the resources of a given time. And there is nothing shameful in that. The stars that were photographed for the Carte du Ciel continue to shine in the night sky, following their slow paths across the heavens just as they have done for millennia. Some of them have moved appreciably in the century and more since they were first captured on those glass plates in Paris and Greenwich and the Cape of Good Hope. And by measuring that movement, astronomers have learned something about where those stars are and how fast they are traveling. This is the way of science, building upon what has come before, using the work of earlier generations as a foundation for new discoveries, and finding value in old observations that their makers might never have anticipated. The Carte du Ciel, for all its troubles and incompleteness, takes its place in this long tradition, a chapter in the ongoing story of humanity's effort to understand the universe. And you may find that thought a peaceful one as you rest and let your thoughts drift toward sleep. And now we come to something rather lovely, a way of understanding the stars that does not rely on watching them shift against the background as the Earth moves, but instead asks the starlight itself to tell us what it knows. This is the story of spectroscopy, and how the careful study of light, broken apart into its constituent colors, would eventually offer astronomers another path toward measuring the distances to stars. It is a gentler kind of measurement in some ways, built not on trigonometry and baseline calculations, but on the physics of light and the surprising discovery that the stars, however remote they may be, are made of the same substances we find here on Earth. The story begins properly in the year 1814, in a workshop in Bavaria belonging to a man named Joseph von Fraunhofer. Though to understand what he discovered, we must first recall what happens when sunlight passes through a glass prism. Isaac Newton had shown, more than a century earlier, that white light could be spread out into a band of colors, a spectrum ranging smoothly from red at one end through orange and yellow and green and blue to violet at the other. This was well known by Fraunhofer's time, and the rainbow-like spectrum of the sun had been studied by many natural philosophers. But Fraunhofer was not an astronomer or a physicist in the academic sense. He was an optician, a maker of lenses and instruments, and he was interested in the spectrum of sunlight because he wanted to understand the optical properties of different types of glass. To test his lenses and prisms, he needed precise reference points within the spectrum, fixed positions where he could make reliable measurements. What Fraunhofer noticed, when he examined the solar spectrum with particular care using equipment of his own making, was that the smooth band of colors was not smooth at all. It was crossed by hundreds upon hundreds of fine dark lines, like narrow gaps or shadows interrupting the continuous rainbow. Some of these lines were quite prominent, easy to see even with modest equipment, while others were exceedingly faint and required the finest instruments to detect. Fraunhofer did not know what caused these dark lines, but he was a methodical and patient man, and he set about cataloguing them with great precision. He labeled the most prominent lines with letters of the alphabet, beginning with A in the deep red portion of the spectrum and proceeding through B, C, D, E, and so on toward the violet end. The D line, which appeared as a distinctive pair of closely spaced dark lines in the yellow region, would become particularly famous in later years. These labels, assigned by an optician in Bavaria for purely practical reasons, are still used by astronomers and physicists today, more than 2 centuries later, a quiet testament to the durability of careful work. Fraunhofer eventually catalogued some 574 of these dark lines in the solar spectrum, and he went further, turning his instruments toward other sources of light. He examined the spectra of Venus and several bright stars, and he discovered that while Venus showed the same pattern of dark lines as the Sun, which made sense because Venus shines only by reflected sunlight, the stars displayed different patterns. The bright star Sirius, for instance, showed lines that did not match the solar pattern, and other stars showed still other arrangements. This was a genuinely mysterious finding, and Fraunhofer did not live long enough to see it explained. He died in 1826 at the age of only 39. His lungs damaged by years of working with glass dust and chemical fumes in his workshop. But he left behind both a puzzle and the tools for solving it, for his techniques of spectral analysis would be taken up and refined by others. The explanation for Fraunhofer's dark lines came more than 4 decades after his death, in 1859, from 2 researchers working together at the University of Heidelberg. Their names were Gustav Kirchhoff and Robert Bunsen, and their collaboration would transform our understanding of both light and matter. Bunsen was a chemist, well known for his work on the analysis of substances through flame tests and for the design of the burner that still bears his name. Kirchhoff was a physicist with a talent for precise measurement and theoretical insight. Together, they began a systematic study of the light emitted by various chemical elements when those elements were heated to incandescence in a flame. What Kirchhoff and Bunsen discovered was that each chemical element, when heated until it glowed, produced a characteristic pattern of bright-colored lines in its spectrum. Sodium, for instance, produced a distinctive pair of bright yellow lines in exactly the same position where Fraunhofer had found the dark D lines in the solar spectrum. This was not a coincidence. Every element had its own unique spectral signature, as individual as a fingerprint, and these patterns were always the same regardless of how the element was obtained or what compounds it had previously been part of. Iron produced one pattern of lines, calcium another, hydrogen another still, and so on through all the elements that Kirchhoff and Bunsen were able to test. The connection to Fraunhofer's dark lines became clear through a simple but crucial experiment. When Kirchhoff passed light from a hot, continuous source through a cooler gas containing a particular element, the resulting spectrum showed dark lines in exactly the positions where that element's emission spectrum would show bright lines. The cool gas was absorbing light at precisely the same wavelengths at which it would emit light when heated. This meant that the dark lines in the solar spectrum were caused by absorption, by cooler gases in the outer layers of the Sun absorbing specific wavelengths of light from the hotter regions beneath. And the positions of those dark lines could tell you what elements were present in the solar atmosphere. The implications were profound and far-reaching. Here was a method for determining the chemical composition of a body millions of miles away, without ever needing to obtain a physical sample. Kirchhoff himself used spectroscopy to identify several familiar elements in the Sun, including iron, magnesium, sodium, and calcium. The Sun, that brilliant and seemingly alien body, was made of ordinary matter, the same substances found in rocks and seawater and the flames of a laboratory burner. This was a revelation that quietly changed humanity's relationship with the cosmos, though it happened too gradually for most people to notice. It fell to an English amateur astronomer named William Huggins to extend this method from the Sun to the stars, and he began this work in earnest in 1863. Huggins was a man of independent means who had sold his family's silk business and retired to Tulse Hill in South London, where he built a private observatory in his garden. He was 40 years old when he first learned of Kirchhoff and Bunsen's work, and he was immediately struck by the possibility of applying their methods to stellar light. If the dark lines in the solar spectrum revealed the sun's composition, then surely the dark lines in stellar spectra, which Fraunhofer had shown were different from the solar pattern, could reveal what the stars were made of. The technical challenges were considerable. Stars are very much fainter than the sun, and spreading their light out into a spectrum made it fainter still. Huygens needed sensitive instruments and long, careful observations, but he was patient and meticulous, and over the following years he accumulated spectroscopic observations of dozens of stars, nebulae, and other celestial objects. What he found was deeply reassuring in its ordinariness. The stars contained iron, sodium, calcium, magnesium, hydrogen, and other elements familiar from terrestrial chemistry. Some stars showed stronger lines of certain elements and weaker lines of others, suggesting differences in composition or temperature, but the basic building blocks were the same. Sirius was not made of some exotic celestial substance unknown on Earth, nor was Aldebaran, nor Betelgeuse. The stars were made of atoms, the same kinds of atoms found in the Earth and in the bodies of the astronomers who studied them. Huygens also made another important observation, one that would have great significance for measuring stellar motions and, eventually, distances. In 1868, he detected a small shift in the position of a spectral line in the light of Sirius, a displacement from the wavelength at which that line appeared in laboratory sources. This shift was consistent with the Doppler effect, a phenomenon first described mathematically by the Austrian physicist Christian Doppler in 1842. The Doppler effect predicts that light from a source moving toward an observer will be shifted slightly toward shorter wavelengths, appearing more blue, while light from a source moving away will be shifted toward longer wavelengths, appearing more red. The amount of the shift depends on the velocity of the source relative to the observer. Huygens's measurements suggested that Sirius was moving away from the Earth at a considerable speed, though the exact value was difficult to determine with the instruments available to him. This was the first detection of radial velocity in a star, the component of stellar motion directed along the line of sight, toward or away from us. It was a different kind of motion from the proper motion that Halley had discovered, which described how stars moved across the sky. Radial velocity and proper motion together could, in principle, give a complete picture of a star's movement through space, though combining them required knowing the star's distance, which brought us back to the old problem of parallax. Around the same time that Huygens was working in London, an Italian astronomer named Angelo Secchi was undertaking a different but complementary project at the Vatican Observatory in Rome. Father Secchi, a Jesuit priest and director of the observatory, was interested in classifying the stars based on their spectral characteristics. Between 1863 and 1868, he examined the spectra of some 4,000 stars and found that they could be sorted into a relatively small number of distinct types. Most stars fell into one of four main categories, which Secchi labeled with Roman numerals. Type 1 stars, like Sirius and Vega, showed strong absorption lines of hydrogen and relatively simple spectra overall. They appeared white or bluish-white in color. Type 2 stars, like our own Sun and the bright star Kepler, had more complex spectra with numerous lines corresponding to metals like iron and calcium. They appeared yellow or orange. Type 3 stars, such as Betelgeuse and Antares, showed broad absorption bands rather than sharp lines, features that were later understood to be caused by molecules like titanium oxide in their cooler atmospheres. These stars appeared distinctly red. Type IV stars were relatively rare and showed strong bands of carbon compounds. Secchi later added a fifth type for stars with emission lines rather than absorption lines, though these were uncommon. This classification scheme was a significant step forward because it suggested that the diversity of stellar spectra might arise from physical differences among the stars themselves, perhaps differences in temperature or in the stage of their evolution. A hot star would have a different spectrum from a cool star, even if both were made of the same chemical elements, because temperature affected which absorption lines were most prominent. The idea that stars might form a continuous sequence, related by physical properties rather than being entirely independent objects, would prove to be enormously fruitful in the 20th century. The technique of spectroscopy continued to advance through the 1870s and 1880s, and one of the most important developments came from the work of Hermann Karl Vogel at the Potsdam Astrophysical Observatory in Germany. Vogel was a specialist in precise spectroscopic measurements, and he devoted many years to refining the methods for detecting Doppler shifts in stellar spectra. His instruments and techniques were more accurate than Huygens' had been, and he was able to measure radial velocities for a growing number of stars with reasonable precision. In 1889, Vogel made a particularly interesting discovery while studying the spectrum of a star called Algol, which had long been known to vary in brightness in a regular pattern. The spectrum of Algol showed periodic shifts in its absorption lines, moving first toward shorter wavelengths and then toward longer wavelengths and back again, with a period that matched the cycle of brightness variation. Vogel interpreted this as evidence that Algol was not a single star but a pair of stars orbiting around their common center of mass. When one star was moving toward us in its orbit, its spectral lines were blue-shifted, and when it was moving away, its lines were red-shifted. The brightness variations occurred because one star periodically passed in front of the other as seen from Earth, blocking some of its light. This was the discovery of what we now call a spectroscopic binary, a double star system whose dual nature is revealed not by visual observation but by the periodic shifting of its spectral lines. Vogel went on to identify other spectroscopic binaries, and this became an important tool for studying stellar masses and orbits. If you could measure the radial velocities of both stars in a binary system over a complete orbital period, and if you knew the orbital inclination, you could calculate the masses of the stars themselves. This was valuable information that could not be obtained in any other way for stars too distant to show measurable parallax. The relevance of all this spectroscopic work to the problem of stellar distances may not be immediately obvious, but it was there, implicit in the growing understanding of stellar physics. As astronomers accumulated more spectroscopic data and compared it with other information about stars, patterns began to emerge. Stars of the same spectral type tended to have similar physical properties. A star that looked like Sirius spectrally was probably similar to Sirius in temperature and intrinsic brightness. A star that looked like our Sun was probably genuinely Sun-like. And if two stars had the same intrinsic brightness but different apparent brightness as seen from Earth, the fainter one must be farther away. This reasoning would eventually crystallize into what became known as spectroscopic parallax, though that name is something of a misnomer because the method does not involve parallax at all in the geometric sense. The idea is straightforward in principle. If you can determine a star's spectral type through careful analysis of its light, And if you know from observations of nearby stars with measured trigonometric parallaxes what the intrinsic brightness of stars of that type typically is, then you can estimate the distance to any star of that type simply by measuring how bright it appears. The ratio of intrinsic to apparent brightness gives you the distance. The full development of spectroscopic parallax would not come until the early 20th century, after Ejnar Hertzsprung and Henry Norris Russell discovered the relationship between stellar luminosity and spectral type that we now call the Hertzsprung-Russell diagram. But the foundations were being laid in the 1860s, 70s, and 80s, in the work of Huggins and Setkai and Fogel and many others. They were demonstrating that stars were physical objects that obeyed physical laws, that they could be classified and understood, that they were not infinitely various but fell into recognizable categories. And if stars within a category were genuinely similar, then their apparent differences in brightness must arise primarily from their different distances. This was a profound shift in how astronomers thought about the cosmos. The trigonometric parallax method, for all its elegance and geometric certainty, could only reach the nearest stars. Beyond a few dozen light-years, the parallax angles became too small to measure reliably with the instruments of the 19th century. But spectroscopy offered the hope of reaching much farther, of using the physics of light to estimate distances to stars that were hundreds or thousands of light-years away. The universe was opening up, becoming accessible to measurement by multiple independent methods that could check and support each other. And so we see how the study of starlight, begun by an optician who wanted to test his glass and continued by chemists and physicists and amateur astronomers working with prisms and spectroscopes, contributed to the ancient quest for stellar distances. It was a different path from the geometric one that Tycho and Bessel had followed, but it led toward the same goal: the mapping of the heavens and the understanding of our place within them. The stars were very far away, as the parallax measurements had shown, but they were not beyond understanding. They were made of familiar atoms. They moved through space in ways that could be measured, and they belonged to types and categories that hinted at underlying physical regularities. All of this knowledge, accumulated slowly and patiently through the second half of the 19th century, would prove essential for the great advances in stellar distance measurement that lay ahead in the 20th century, though that is a story for another time, another gentle exploration of how we came to know the scale of the universe. The measurement of stellar parallax, as we have seen, required astronomers to detect angular shifts so remarkably small that they pushed against the very limits of what their instruments could reliably perceive. This challenge was not merely a matter of building better telescopes or more finely divided measuring circles, though those improvements certainly helped. The deeper problem was one of uncertainty itself, of understanding how to distinguish a genuine signal from the random fluctuations that inevitably accompanied any act of measurement. And so, as astronomers pursued the elusive parallax of the stars throughout the 19th century, they found themselves developing new ways of thinking about error, about probability, and about the very nature of reliable knowledge. This interweaving of astronomical practice and statistical reasoning forms a quieter but no less important chapter in our story, and we shall now trace its gentle course through the decades. When Friedrich Wilhelm Bessel sat down to analyze his observations of 61 Cygni in the late 1830s, he brought to that task a lifetime of careful thought about the nature of measurement error. Bessel had begun his scientific career not as an astronomer but as a merchant's apprentice in Bremen, teaching himself mathematics and celestial mechanics in his spare hours. His earliest astronomical work involved reducing the observations of James Bradley, the Astronomer Royal, whose meticulous records from the mid-18th century contained a wealth of stellar positions. In working through Bradley's data, Bessel encountered the fundamental challenge that would occupy much of his intellectual life, namely the question of how to extract the most reliable possible conclusions from observations that were inevitably imperfect. Every measurement, no matter how carefully made, was subject to small errors from countless sources, some known and some unknown, and the astronomer's task was to find methods for handling these errors in a rigorous and honest way. During the 1810s and 1820s, Bessel developed and refined his approach to what we might call the quantification of uncertainty. He was not working in isolation, of course, for mathematicians such as Pierre-Simon Laplace and Carl Friedrich Gauss had already laid important groundwork in the theory of errors and the method of least squares. Gauss, in particular, had shown how to combine multiple observations of the same quantity in a way that minimized the overall error, and he had demonstrated the mathematical properties of the bell-shaped curve that we now call the normal or Gaussian distribution. Bessel absorbed these mathematical insights and transformed them into practical tools for the working astronomer. His great contribution was to take the abstract theory and render it concrete, developing specific procedures that could be applied to real observations in the observatory. Central to Bessel's approach was what he termed the probable error, a concept that allowed astronomers to express the reliability of their results in a standardized and meaningful way. The probable error of a single observation, as Bessel defined it, was the amount of error such that there was an equal chance of the true error being larger or smaller than this value. In other words, if you made a large number of observations of the same quantity and computed the probable error correctly, then roughly half of your individual measurements would fall within one probable error of the mean, and roughly half would fall outside it. This provided a clear and intuitive measure of scatter, a way of saying just how tightly or loosely your observations clustered around their central value. When Bessel announced that the parallax of 61 Cygni was a certain number of arc-seconds with a probable error of a certain smaller number, he was communicating something precise about the confidence that could be placed in his result. The beauty of this approach lay in its honesty and its utility, rather than simply reporting a single number and hoping that readers would trust it. Bessel was acknowledging the inherent uncertainty in his measurements and quantifying that uncertainty in a way that others could evaluate. If the probable error was small compared to the measured quantity, then the result was likely to be reliable. If the probable error was large, approaching or exceeding the measured quantity itself, then skepticism was warranted. This framework proved essential for parallax work, where the angles being sought were often barely distinguishable from the random scatter in the data. When Thomas Henderson's parallax for Alpha Centauri or Wilhelm Struve's value for Vega were published with their associated probable errors, astronomers could judge for themselves whether these results represented genuine detections or merely fluctuations in imperfect data. The calculation of probable error required multiple observations of the same quantity, and the more observations one had, the more reliably one could estimate the error. This created a virtuous cycle in parallax research, encouraging astronomers to make many measurements rather than a few, and to pay careful attention to the scatter in their results. If a star was observed on 10 different nights, and all 10 measurements agreed closely with one another, then the probable error would be small, and one could have confidence in the mean value. If the same 10 measurements were wildly discordant, jumping around with no clear pattern, then the probable error would be large, warning that something was amiss either with the observations themselves or with the assumptions underlying their analysis. This statistical discipline helped to separate genuine parallaxes from spurious ones, though it could not eliminate all sources of systematic error that affected measurements in consistent but undetected ways. The development of statistical thinking in astronomy was advanced considerably by the work of Adolphe Quetelet, the Belgian polymath whose interests ranged from mathematics and physics to sociology and the organization of scientific research. Quetelet is perhaps best known today for his studies of human populations, in which he applied statistical methods to understand the distribution of characteristics such as height, weight, and even criminal behavior. But he was also deeply interested in astronomy, having trained at the Paris Observatory and founded the Royal Observatory of Belgium in Brussels. Quetelet recognized that the methods he was developing for social statistics could be applied with equal profit to celestial observations, and he devoted considerable attention to what he called the theory of probabilities as applied to the physical and social sciences. In his astronomical work, Quetelet emphasized the importance of large numbers of observations and the careful analysis of their distribution. He studied the errors that arose in astronomical measurements and showed how they conformed, at least approximately, to the theoretical distributions predicted by Gauss and Laplace. This confirmation was reassuring, for it suggested that the mathematical theory of errors was not merely an abstract construction but a genuine description of how measurement uncertainties actually behaved in practice. Quetelet also explored more sophisticated questions, such as how to detect the presence of systematic errors that might bias an entire series of observations in one direction, and how to combine measurements made with different instruments or by different observers. His textbook on the theory of probabilities, published in the 1840s, became a standard reference for astronomers grappling with these issues. The influence of Quetelet's statistical approach extended into parallax research in both direct and indirect ways. Directly, his methods helped astronomers to analyze their parallax observations more rigorously, identifying outliers, estimating probable errors, and combining results from multiple sources. Indirectly, his broader vision of a statistically informed science encouraged astronomers to think about the stars not merely as individual objects to be measured one by one, but as populations whose collective properties could be studied through appropriate averaging and analysis. This perspective would prove increasingly important as the 19th century progressed and astronomers began to consider questions about the structure and extent of the stellar system as a whole. By the middle of the 19th century, it had become clear that trigonometric parallax, the direct geometric method based on the Earth's orbital motion, would yield reliable results for only a small number of nearby stars. The angles involved were simply too tiny, the measurements too difficult, and the accumulation of probable error too large to permit the detection of parallaxes much smaller than about 1/10 of an arcsecond. This corresponded to a distance of roughly 30 light-years, which meant that the vast majority of stars visible in the sky remained beyond the reach of direct measurement. Astronomers did not abandon the trigonometric approach, for it remained the gold standard of distance determination, the only method that provided truly direct and model-independent distances. But they began to explore alternative techniques that might extend their reach further into the depths of space, and these alternatives relied heavily on statistical reasoning. One such approach was developed by the English astronomer Richard Anthony Proctor, a prolific writer and popularizer of science who also made significant contributions to stellar astronomy. In 1869, Proctor published a study of the proper motions of stars, those slow drifts across the sky that result from the actual movement of stars through space relative to the Sun. Proctor noticed that when he mapped out the proper motions of a large number of stars, They did not point in random directions but showed a definite pattern. There was a region of the sky, located in the constellation Hercules, toward which the proper motions preferentially converged, and an opposite region from which they seemed to diverge. Proctor interpreted this pattern as evidence that the Sun itself was moving through space, heading in the direction of Hercules at a substantial velocity, and that the apparent motions of the stars were partly a reflection of this solar motion rather than purely intrinsic movements of the stars themselves. This insight, which had been anticipated by William Herschel nearly a century earlier but was now placed on a firmer statistical foundation, had important implications for the measurement of stellar distances. Proctor recognized that the proper motions of stars could be decomposed into two components, one resulting from the Sun's motion through space and one representing the true or peculiar velocity of each star. If one assumed that the peculiar velocities of stars were randomly oriented, pointing in all directions with no preferred pattern, then any systematic trend in the observed proper motions could be attributed to the solar motion. And crucially, the apparent magnitude of this solar motion effect would depend on the distances of the stars, being larger for nearby stars and smaller for distant ones. This opened the possibility of using proper motion statistics to estimate average stellar distances, even when individual parallaxes could not be measured. Proctor's work on star streaming, as this phenomenon came to be called, represented an early example of what we might call statistical astronomy, the use of large samples and averaging techniques to extract information about stellar properties that could not be determined for individual stars. The method was not precise, for it depended on assumptions about the randomness of stellar velocities that might not be strictly true, and it yielded only average distances for groups of stars rather than individual distances for each one. But it extended the astronomer's reach far beyond the 30-light-year horizon of trigonometric parallax, and it pointed the way toward more sophisticated statistical methods that would be developed in the decades to come. The concept of secular parallax, which emerged toward the end of the 19th century, represented a particularly elegant application of the solar motion idea to distance determination. If the Sun is moving through space, then over the course of years and decades, it traces out a path that can serve as a baseline for parallax measurement, much as the Earth's orbit serves as a baseline for annual trigonometric parallax. The crucial difference is that this secular baseline grows longer with time, extending well beyond the diameter of Earth's orbit. After 20 years of solar motion, for example, the baseline might be several times the size of the Earth's orbit, and after a century, it would be many times larger still. This extended baseline means that the parallactic shifts produced by the solar motion are correspondingly larger than the annual parallax shifts, and thus easier to detect. The method of secular parallax was developed most fully by the Dutch astronomer Jacobus Cornelius Kapteyn, whose work we shall encounter again in later portions of our narrative. Kapteyn recognized that by studying the proper motions of stars over long periods, one could detect the slow drift caused by the solar motion through space and use this drift to estimate distances. The technique required knowledge of the direction and speed of the Sun's motion, which could be determined from the convergence pattern that Proctor had studied, and it required careful analysis of proper motion data accumulated over many years. When applied to groups of stars, the method yielded average distances that were reasonably reliable, though individual stellar distances remained uncertain due to the unknown peculiar velocities of each star. It is important to understand the distinction between these different approaches to stellar distance measurement, for they represent fundamentally different kinds of knowledge. Trigonometric parallax, the method that Bessel, Henderson, and Struve employed so successfully, is a direct geometric measurement that makes no assumptions about the physical properties or motions of stars. The parallax angle depends solely on the geometry of the Earth-Sun star system, and the distance follows immediately from simple trigonometry. This directness gives trigonometric parallax a special status, for its results are model-independent and require no auxiliary hypotheses about stellar physics or kinematics. When we say that a star has a parallax of 1 arcsecond and therefore lies at a distance of 1 parsec, we are making a statement that is as certain as any statement in astronomy can be, subject only to the measurement errors that Bessel taught us to quantify. Statistical and secular methods, by contrast, are indirect approaches that rely on additional assumptions. The statistical method assumes that stellar velocities are randomly distributed, with no preferred direction, so that systematic patterns in proper motion can be attributed to the solar motion. The secular parallax method assumes that we know the speed and direction of the Sun's motion accurately enough to compute the expected parallactic drift. Both methods yield only average or typical distances rather than precise values for individual stars. If the underlying assumptions are wrong, if stellar velocities are not random, or if the solar motion is different from what we suppose, then the derived distances will be biased in ways that may not be immediately apparent. These methods are powerful tools for extending our reach into the stellar system, but they must be used with appropriate caution and humility. By the year 1900, after more than 6 decades of intensive effort following Bessel's breakthrough, the ledger of trigonometric parallax results was modest in size but precious in quality. Only about 60 stars had parallaxes that were considered reliable, meaning that the measured values were substantially larger than their probable errors and had been confirmed by multiple independent observers using different instruments. These 60 stars represented the nearest neighbors of our Sun, a tiny sample of the millions of stars visible to the naked eye and the billions that telescopes had revealed. The distances ranged from just over 4 light-years for Alpha Centauri to perhaps 30 or 40 light-years for the most distant stars in the parallax catalogue. Beyond this horizon, the stellar universe remained unmeasured by direct methods, its scale determined only by the less certain statistical approaches. The reasons for this slow progress were manifold. The inherent difficulty of the measurements, requiring the detection of angles as small as a few hundredths of an arcsecond, meant that only the most skilled observers with the finest instruments could hope for success. The Earth's atmosphere, with its constant shimmering and distortion, imposed a practical limit on the precision achievable from ground-based observatories. Systematic errors, those insidious biases that affected all measurements in the same direction and thus did not average out with repeated observation, proved surprisingly difficult to identify and eliminate. And the simple fact that most stars are very far away meant that their parallaxes were smaller than any instrument could reliably detect. Yet within these 60 hard-won parallaxes lay the foundation for all subsequent work on stellar distances and the structure of the galaxy. Each parallax represented a calibration point, a star whose distance was known with reasonable confidence and whose other properties, such as brightness, color, and spectral characteristics, could therefore be studied with the knowledge of how far away the light had traveled. As astronomers began to recognize patterns in the relationship between stellar brightness and spectral type, they could use the parallax stars as anchors, establishing the intrinsic luminosities of different kinds of stars and then applying this knowledge to estimate distances for the countless stars too remote for direct measurement. The statistical methods developed by Proctor and Kapteyn, meanwhile, extended the astronomer's reach into the surrounding stellar system, revealing patterns in the distribution and motion of stars that hinted at structure far larger than the parallax horizon could illuminate. The combination of direct and statistical approaches, each contributing its distinctive strengths while compensating for the other's weaknesses, would prove essential for the 20th century investigations that eventually mapped the Milky Way and established our place within it. But all of this later work rested upon the careful statistical foundations laid by Bessel and his contemporaries, who taught astronomers to quantify their uncertainties, to report their probable errors, and to treat the scatter in their observations not as a nuisance to be ignored but as a source of valuable information about the reliability of their results. As we rest here for a moment, contemplating the patient accumulation of parallax measurements throughout the 19th century, we may appreciate the quiet heroism of this statistical work. It lacked the drama of discovery, the thrill of seeing a new world for the first time or detecting an unsuspected phenomenon in the heavens. But it was essential nonetheless, for without rigorous methods for handling uncertainty, astronomers would have been unable to distinguish real parallaxes from illusory ones, and the distances of the stars would have remained matters of speculation rather than measurement. The probable error, that modest little number appended to each parallax value, represented a hard-won understanding of the limits of knowledge, and its careful calculation was a necessary prelude to any further progress. And so we turn our attention now to the southern hemisphere, to that distant promontory of rock and scrubland at the very tip of the African continent, where the Atlantic and Indian Oceans meet in a perpetual confluence of currents, and where, beginning in the middle of the 18th century, astronomers would journey from the northern latitudes to gaze upon stars that had remained largely unmeasured and uncatalogued since the beginning of recorded history. Stars that wheeled around a different pole and traced unfamiliar arcs across skies that European observers could only imagine from their fog-bound observatories in Greenwich and Paris and Berlin. The story of parallax measurement in the southern skies begins, in a meaningful sense, with a French abbé named Nicolas Louis de Locail, a man of quiet temperament and extraordinary patience, who in the year 1751 set sail from the port of Lorient aboard a vessel of the French East India Company, bound for the Cape of Good Hope with the intention of mapping the heavens that lay beyond the reach of northern telescopes. Locail was not, it should be said, a man given to grand pronouncements or dramatic gestures, but rather possessed that particular form of scholarly dedication that finds its satisfaction in the slow accumulation of precise observations, in the careful recording of numbers that might one day prove useful to those who came after. He arrived at the Cape in April of 1751 and established his modest observatory in the town that the Dutch settlers called Kaapstad, setting up his instruments on a site that afforded clear views of the sky in most directions, and there he remained for nearly 2 years, working with a diligence that borders, when one considers the scope of his achievement, on the almost incomprehensible. During those 22 months at the Cape, Locail observed and recorded the positions of nearly 10,000 stars, an undertaking that required him to spend night after night at his telescope, noting the transit times and zenith distances of each star as it crossed his meridian, converting these raw observations into coordinates that could be compared and verified, all while contending with the practical difficulties of working in a colonial outpost far removed from the libraries and instrument makers of Europe. His catalogue, when it was eventually published, revealed to northern astronomers a wealth of celestial objects that had previously existed only as rumors and vague reports, including many of the stars that we now recognize as among the closest neighbors to our own solar system, though Locail himself could not have known this at the time. He also took the opportunity to measure the positions of Mars and Venus against the background stars, hoping to contribute to the determination of the solar parallax, and he made observations of the Moon that would prove valuable to later investigators attempting to understand the shape and size of the Earth itself. Locale's work at the Cape demonstrated something important, namely that the southern hemisphere contained astronomical riches that warranted permanent and systematic investigation, and that the establishment of a proper observatory at this latitude would benefit not only the science of positional astronomy but also the practical needs of navigation and timekeeping that were becoming ever more pressing as European maritime empires expanded their reach across the globe. Yet it would be nearly 70 years before such an observatory came into being. 70 years during which the Cape passed from Dutch to British control, and the strategic importance of the colony as a waypoint on the route to India became increasingly apparent to the government in London. The Royal Observatory at the Cape of Good Hope was established in the year 1820, following a recommendation from the Board of Longitude and the Commissioners of the Admiralty, who recognized that an observatory in the southern hemisphere would serve both scientific and imperial purposes, providing accurate time signals for ships rounding the Cape and contributing to the great surveys of stellar positions that were then being undertaken at observatories throughout Europe. The observatory was constructed on a slight rise to the southeast of Cape Town, a location chosen for its relatively clear air and its distance from the lights and smoke of the growing settlement, and there it would remain for the next century and a half, gradually expanding its facilities and its staff as the demands of astronomical research grew more complex and more ambitious. The first two directors of the Cape Observatory were capable men who laid the foundations for later work, but it is the third director, Thomas Henderson, who concerns us most directly in this account of parallax measurement, for it was Henderson who first attempted to determine the distance to one of the southern stars using the method of trigonometric parallax, and who thereby contributed, though somewhat reluctantly, to the resolution of that ancient question that had occupied astronomers since the time of Aristarchus. Henderson arrived at the Cape in April of 1831, having previously served as an assistant at the Royal Observatory in Edinburgh, and he brought with him a determination to make good use of the excellent observing conditions that the Cape was reported to offer. He was, by all accounts, a somewhat reserved and cautious man, not given to rushing into print with preliminary results, and this caution would later prove to be both a virtue and a source of some regret. Among the stars that Henderson chose to observe during his tenure at the Cape was Alpha Centauri, the brightest star in the constellation of the Centaur and, as it happens, the third brightest star visible from anywhere on Earth, outshone only by Sirius and Canopus. Alpha Centauri had long been of interest to astronomers because of its large proper motion, the slow drift across the sky that indicates, as we have discussed, a probable proximity to our solar system, and Henderson recognized that this star presented an excellent opportunity for parallax measurement if only one could achieve the necessary precision in determining its position throughout the year. He made a series of careful observations of Alpha Centauri during 1832 and the early months of 1833, using the mural circle that had been installed at the observatory, and when he reduced these observations after his return to Scotland, he found what appeared to be a small but definite parallax, amounting to somewhat more than 1 second of arc, which would imply a distance of roughly 3 light-years, making Alpha Centauri the closest known star beyond our Sun. But Henderson hesitated. He was troubled by certain systematic effects in his observations that he could not entirely explain, and he worried that the apparent parallax might be an artifact of instrumental error or atmospheric refraction rather than a genuine displacement caused by the Earth's orbital motion. And so he delayed publication, working through his calculations again and again, seeking confirmation that proved elusive, and in the meanwhile Friedrich Bessel in Königsberg announced his measurement of the parallax of 61 Cygni, claiming priority for the first successful determination of stellar distance. Henderson did eventually publish his result in January of 1839, just 2 months after Bessel's announcement, but the moment of discovery had passed him by, and he has been remembered ever since as the astronomer who measured a parallax but lacked the confidence to claim it. Henderson's successor at the Cape was Thomas Maskelyne, an Irish-born astronomer who would serve as director for nearly 4 decades, from 1833 until 1870, and who would transform the observatory from a modest colonial outpost into a respected institution capable of contributing to the most demanding programs of astronomical research. Maskelyne was a more robust personality than his predecessor, possessed of considerable administrative ability and a willingness to advocate forcefully for the resources that his observatory required, and he quickly set about improving both the instruments and the procedures that had been established during the observatory's early years. One of his first priorities was to verify Henderson's measurement of the parallax of Alpha Centauri, which remained controversial in the astronomical community, and he devoted considerable effort over several years to obtaining new and more precise observations of this star. Maskelyne's verification of Henderson's parallax was announced in 1840, and it represented an important milestone in the acceptance of stellar distance measurement as a reliable branch of astronomical science. His value for the parallax of Alpha Centauri was slightly smaller than Henderson's, indicating a somewhat greater distance, but it confirmed beyond reasonable doubt that this star did indeed exhibit a measurable displacement when viewed from opposite sides of the Earth's orbit, and that Henderson's caution, while perhaps excessive, had not been entirely misplaced. The confirmation of the Alpha Centauri parallax also established that this star, or more precisely this system of stars, for Alpha Centauri is in fact a binary, was indeed the closest stellar neighbor to our Sun, a distinction that it retains to this day, and that the southern hemisphere contained objects of fundamental importance for understanding the structure and scale of the cosmos. Throughout his long directorship, Maskelyne continued to improve the Cape Observatory's capabilities for positional astronomy, installing new instruments and training new assistants, advocating for funding from the home government and cultivating relationships with the astronomical establishments of Europe. The observatory operated throughout this period under the authority of the Admiralty in London, which provided the salaries of the director and his staff and approved the major expenditures for instruments and buildings, a colonial arrangement that gave the Cape access to resources that would not have been available from local sources, but that also imposed certain constraints on the observatory's independence and its ability to pursue research programs that might not serve immediate practical needs. Maskelyne navigated these constraints with considerable skill, maintaining the observatory's primary mission of providing timekeeping and navigational services while gradually expanding its capacity for fundamental astronomical research. And by the time of his retirement in 1870, the Cape had established itself as a significant contributor to the international enterprise of stellar cartography. The transformation of the Cape Observatory into what might fairly be called a premier institution for parallax measurement, however, did not occur until the arrival of David Gill in 1879. Gill was a Scottish astronomer of remarkable energy and ambition, who had previously made his reputation through observations of the transit of Venus and through an expedition to Ascension Island for the purpose of measuring the solar parallax by observations of Mars at opposition, and he came to the Cape with a clear vision of what the observatory might accomplish if properly equipped and properly directed. He would serve as Her Majesty's astronomer at the Cape for nearly 3 decades, until 1907, and during that time he would oversee a program of research that would fundamentally alter our understanding of stellar distances and stellar distribution in the southern sky. Gill's approach to parallax measurement differed in important ways from that of his predecessors, for he recognized that the future of precise positional astronomy lay not with the traditional transit instruments and mural circles that had served observatories for generations, but rather with newer instruments that offered greater accuracy and greater efficiency. Chief among these was the heliometer, a specialized telescope designed originally for measuring the angular diameter of the Sun, which used a divided objective lens to produce two images of the same field that could be displaced relative to one another by a precisely calibrated mechanism, allowing the angular separation between two stars to be measured with an accuracy that exceeded what was possible with any other instrument then available. Gill had used a heliometer during his earlier observations of Mars and Venus, and he was convinced that this instrument, properly employed, could revolutionize the measurement of stellar parallax. The heliometer that Gill installed at the Cape was a magnificent instrument, with an objective lens of 7 inches aperture, and he devoted it primarily to two complementary programs of research. The first was the refinement of the solar parallax, which is to say the determination of the distance from the Earth to the Sun, a quantity that serves as the baseline for all subsequent measurements of cosmic distance, and that was still, in the 1880s, known with less precision than one might suppose. Gill contributed to this effort through observations of the transits of Venus in 1874 and 1882. Those rare occasions when the planet passes directly between the Earth and the Sun and can be observed as a small dark disk against the brilliant solar surface, and also through observations of certain minor planets, or asteroids, whose close approaches to Earth provided alternative opportunities for triangulation. These asteroid observations proved particularly valuable, as they avoided many of the systematic difficulties that had plagued the Venus transit expeditions, and Gill's results contributed significantly to the improved values for the solar parallax that were adopted by the international astronomical community in the decades that followed. The second major program that Gill undertook with the heliometer was the measurement of stellar parallaxes, and here his contributions were even more substantial. Using the same techniques of precise differential measurement that had proved so effective for the solar parallax, Gill and his assistants observed dozens of southern stars that were suspected, on the basis of their proper motions or other characteristics, of being relatively nearby, and they succeeded in determining reliable parallaxes for many of these objects. The precision that they achieved was remarkable, with probable errors often amounting to only a few hundredths of a second of arc, and their catalogue of southern stellar parallaxes remained the standard reference for many years. Among the stars that they measured was, of course, Alpha Centauri, and their improved determination of its parallax confirmed and refined the earlier values of Henderson and Maskelyne, establishing the distance to our nearest stellar neighbor with a precision that would not be significantly exceeded until the advent of space-based observations in the late 20th century. But perhaps the most ambitious undertaking of Gill's directorship, and one that would have lasting implications for both parallax measurement and stellar astronomy more generally, was the Cape Photographic Durchmusterung, a systematic survey of the southern sky using the new technology of astronomical photography. Gill had become interested in the possibilities of photography after the Great Comet of 1882, when he discovered that relatively simple photographic equipment could record the positions of stars with an accuracy comparable to that achieved by laborious visual observation, and he recognized that a photographic survey of the southern heavens could accomplish in years what would otherwise require decades of painstaking telescope work. The Durchmusterung, which is a German term meaning roughly a searching through or a comprehensive survey, was modeled on similar catalogues that had been produced for the northern sky, particularly the Borner Durchmusterung compiled by Friedrich Argelander and his assistants at the Observatory in Bonn, and it aimed to record the position and brightness of every star down to about the 10th magnitude that was visible from the Cape. The work on the Cape Photographic Durchmusterung began in earnest in 1885 and continued for 15 years, finally reaching completion in 1900. The photographic plates were exposed at the Cape using a specially constructed astrographic telescope, and they were then measured and reduced with the assistance of astronomers in the Netherlands, particularly Jacobus Kapteyn at the University of Groningen, who undertook the immense task of extracting stellar positions from the plates and compiling them into a usable catalogue. The finished work contained the positions of 454,875 stars, a number that dwarfs the earlier catalogues of Locail and Henderson and represents a comprehensive inventory of the stellar population visible from the southern hemisphere. This catalogue served not only as a resource for identifying stars suitable for parallax measurement, but also as the foundation for statistical studies of stellar distribution and stellar motion that would inform the developing understanding of the structure of our galaxy. Throughout this period, the Cape Observatory continued to operate within the colonial administrative framework that had governed it since its establishment, with funding provided by the British government and oversight exercised through the Admiralty and later the Colonial Office. This arrangement had both advantages and disadvantages. On the one hand, it gave the observatory access to resources and expertise that would not have been available from local sources, and it ensured a degree of continuity and stability that allowed long-term research programs to be undertaken with confidence. On the other hand, it meant that the observatory's priorities were necessarily influenced by the needs and preferences of administrators in London, who might not always appreciate the scientific importance of work that had no immediate practical application, and it created a certain dependence on the goodwill of distant authorities that could be uncomfortable for directors who wished to pursue their own research agendas. Gill, like Maskelyne before him, proved adept at managing these relationships, cultivating support in London while maintaining the observatory's reputation among the international astronomical community, and the Cape flourished under his leadership as perhaps the most productive observatory in the Southern Hemisphere. The work of these astronomers at the Cape, from Locail's pioneering survey through Henderson's tentative parallax measurement to Gill's comprehensive programs of observation, represents a sustained effort to extend the reach of human knowledge into regions of the sky that had remained largely unknown to European science. The stars they catalogued, the distances they measured, the techniques they developed all contributed to the gradual assembly of that picture of the stellar universe that would emerge, with increasing clarity, during the early decades of the 20th century, and their observations continue to be cited and consulted by astronomers working today on problems that these Victorian and Georgian pioneers could scarcely have imagined. The southern heavens, once a blank space on the celestial map, had been surveyed and measured and made knowable through the patient work of observers stationed at that remote promontory where the continents of Africa meets the sea. And so we come now to another path that astronomers found toward measuring the distances to the stars, a path that emerged not from the careful tracking of tiny seasonal shifts against the background of more distant suns, but rather from the patient observation of stars that dance together through space, bound to one another by the invisible thread of gravity, wheeling around their common center in stately orbits that may take decades or even centuries to complete. These are the binary stars, and the story of how they came to serve as cosmic measuring tools is a gentle one. unfolding across the 19th century through the work of many careful observers who spent long nights at their telescopes, sketching the positions of faint companion stars and noting, year after year, the slow changes in their arrangements. The recognition that some stars travel through space in gravitationally bound pairs came relatively late in the history of astronomy, for although double stars had been observed for many years before the 19th century began, it was not immediately clear whether these pairings represented true physical associations or merely chance alignments along our line of sight. When one looks up at a clear night sky, stars that happen to lie in nearly the same direction as seen from Earth will appear close together even if they are actually separated by vast distances, one star perhaps nearby and the other immeasurably far beyond it. These optical doubles, as they came to be called, tell us nothing about stellar distances or stellar physics, being merely accidents of perspective. But true binary stars, stars that orbit one another because each feels the gravitational pull of the other, are systems of profound astronomical importance, and it was William Herschel who first demonstrated clearly that such systems exist. William Herschel, the German-born musician who became one of the most prolific observers in the history of astronomy, had initially catalogued double stars for an entirely different purpose. His intention in the late 18th century had been to use close pairs of stars to detect trigonometric parallax, reasoning that if one star of a pair happened to be much closer to us than its apparent companion, then over the course of a year the nearer star would shift its position relative to the more distant one as Earth moved around the Sun. This was a clever approach to the parallax problem, and Herschel devoted considerable effort to measuring the angular separations between the components of double stars, expecting to find seasonal variations that would reveal the parallax of the closer member. What he found instead, after many years of patient observation, was something rather different and in its own way more remarkable. By the year 1802, Herschel had accumulated enough measurements of certain double star systems to notice that the changes he observed were not the back-and-forth seasonal wobbles that parallax would produce, but rather steady, progressive shifts in the position angle and separation of the companion star relative to the primary. The fainter star in these systems was not oscillating but rather moving along a curved path around the brighter star, tracing out what appeared to be an orbital trajectory. Herschel announced his conclusion in a paper presented to the Royal Society in 1802. Declaring that he had found approximately 50 instances in which the relative positions of double stars had changed in ways that strongly suggested genuine orbital motion. These were not optical doubles but physical doubles, true binary stars held together by mutual gravitation and obeying the same laws of celestial mechanics that govern the planets in their courses around the Sun. This was a discovery of considerable significance, for it demonstrated that the law of universal gravitation, which Newton had formulated to explain the motions of bodies within our solar system, operated also among the distant stars. The Sun was no longer unique in possessing gravitational dominion over orbiting bodies. Other stars too exerted gravitational forces capable of binding companions into closed orbits. But for our present purpose, which concerns the measurement of stellar distances, the importance of Herschel's discovery lay in the possibility it opened for calculating those distances through the analysis of binary star orbits, though this possibility would not be fully realized until some years after Herschel's initial announcement. The first person to compute a complete orbit for a binary star system was Félix Savary, a French astronomer working in Paris, who in 1827 published his solution for the orbit of the double star known as Chi Ursae Majoris. This star, located in the constellation of the Great Bear, had been observed carefully enough over the preceding decades that Savary had sufficient data to determine the shape and orientation of the orbit, the period of revolution, and the time at which the companion star reached its closest approach to the primary. The orbital period he derived was approximately 60 years, which meant that the companion had completed a substantial fraction of its orbit during the interval over which observations had accumulated. Savary's work demonstrated that the techniques of orbital mechanics developed for calculating the paths of planets and comets could be applied successfully to binary stars, yielding precise descriptions of their motions through space. The calculation of a binary star orbit from observational data is a matter of considerable mathematical intricacy, requiring the astronomer to determine 7 orbital elements from measurements of angular separation and position angle made at various times. These elements describe the size and shape of the elliptical orbit, the orientation of the orbital plane in 3-dimensional space, and the timing of the companion's motion along its path. When enough observations have been gathered, spanning a sufficient portion of the orbital period, these elements can be extracted through methods that had been refined over the preceding century for use with solar system bodies. Savary's success with Xi Ursae Majoris opened the way for other astronomers to attempt similar calculations for additional binary systems, and gradually a catalogue of known binary orbits began to grow. Now here we approach the matter of distance determination, for the computed orbit of a binary star contains within it information that can, under certain conditions, reveal how far away the system lies. The key relationship is one that follows directly from Newton's laws of motion and gravitation, connecting the orbital period, the size of the orbit, and the combined mass of the two stars. If we know how long it takes the companion star to complete one orbit, and if we know the actual physical size of that orbit measured in kilometers or astronomical units, then we can calculate the total mass of the two stars together, for the period and the orbital size are related to the mass through a formula that astronomers call Kepler's third law in its generalized Newtonian form. But here we encounter a complication, for when we observe a binary star from Earth, we do not measure the actual physical size of the orbit directly. What we measure instead is the angular separation between the two stars, the tiny angle they subtend as seen from our distant vantage point, and this angle depends on two quantities together: the true physical separation between the stars and the distance from us to the system. A binary system with a large physical separation will appear to have a small angular separation if it lies very far away, while a system with a modest physical separation will appear wider if it happens to be nearby. Without knowing the distance, we cannot convert our measured angular separations into true physical separations, and without the true physical separation we cannot determine the mass from the orbital period alone. This difficulty might seem to leave us stranded, unable to use binary stars for distance measurement at all, but there is a way forward if we are willing to make an assumption about the masses of the stars involved. If we suppose that the total mass of the binary system has some particular value, perhaps based on what we know about stars of similar brightness or spectral type, then we can work the calculation in reverse. We begin with the assumed mass and the observed orbital period, which together tell us what the true physical size of the orbit must be. We then compare this physical size to the angular size we observe, and from the ratio we deduce the distance to the system. This technique came to be known as dynamical parallax, because it uses the dynamics of orbital motion to infer a parallax-like distance, even though no actual parallax shift has been measured. The method is elegant in conception but carries with it an inherent uncertainty, for the distance we calculate depends directly on the mass we assume, and the mass assumption may be incorrect. If we suppose the stars to be more massive than they truly are, we will overestimate the physical size of their orbit and consequently overestimate their distance from us. If we assume too little mass, we will underestimate the distance. This circularity was recognized from the beginning as a limitation of the dynamical parallax method, and astronomers understood that the distances derived in this way were provisional, dependent on mass estimates that might require revision as stellar physics became better understood. During the decades following Savary's pioneering work, the observation and cataloguing of double stars proceeded with considerable energy, for astronomers recognized that these systems held clues not only to stellar distances but also to stellar masses and to the processes by which stars form and evolve. John Herschel, the son of William Herschel, carried forward his father's program of observation with a systematic survey of the southern skies undertaken from the Cape of Good Hope between 1833 and 1838. From this location in South Africa, Herschel could observe stars that never rise above the horizon as seen from European observatories, and he took full advantage of this opportunity to sweep the southern heavens for new double stars and other objects of interest. The resulting catalogue, published in 1847 as part of a comprehensive summary of his southern observations, included several hundred previously unknown double star systems, along with careful measurements of many that had been discovered earlier. Herschel's work demonstrated that binary stars are common throughout the sky, in the southern hemisphere as in the northern, suggesting that the formation of gravitationally bound stellar pairs is a widespread phenomenon rather than an astronomical rarity. His measurements also provided valuable new data points for tracking the orbital motions of known systems, extending the baseline of observations and improving the accuracy with which orbits could be calculated. As the 19th century progressed, the systematic measurement of double star positions became increasingly refined, with specialized instruments called filler micrometers allowing observers to determine angular separations and position angles with growing precision. Among the most dedicated practitioners of this art was Otto Wilhelm Struve, a member of the remarkable Struve family of astronomers who directed the Pulkovo Observatory in Russia. Struve devoted himself to the careful measurement of visual binary stars over many years, accumulating thousands of observations that served as raw material for orbit calculations by himself and others. His work, continuing the tradition established by his father Friedrich Georg Wilhelm Struve, helped to transform double-star astronomy from a pursuit of scattered individuals into a sustained international effort. The measurement of double stars requires patience and steady attention to detail, for the angular separations involved are typically very small, often just a few seconds of arc, and the changes from year to year are smaller still. The observer peers through the eyepiece of the telescope at two faint points of light hovering close together, adjusting fine threads or wires in the micrometer until they bracket the stars precisely, then reading off the separation and angle from graduated scales. This work must be repeated on many nights, under varying atmospheric conditions, and the results must be averaged and analyzed to extract reliable values. It is not glamorous work, but it is essential, and the long series of measurements accumulated by observers like the Struves provided the foundation upon which dynamical parallax calculations could be built. By the close of the 19th century, the number of known double stars had grown enormously, thanks in large part to the indefatigable efforts of Shuburn Wesley Burnham, an American astronomer who combined a talent for observation with remarkable persistence. Burnham began his career as a court reporter in Chicago, pursuing astronomy in his spare time with a small telescope set up in his backyard, Yet he went on to discover more than 1,300 new double stars and to compile a monumental catalogue that brought together observations from many sources. His general catalogue of double stars within 121 degrees of the North Pole, published in 1906, listed some 13,665 double star systems, each with measurements of position, separation, and other relevant data. This catalogue represented the accumulated labor of many observers over many decades and served as an invaluable reference for astronomers seeking to study binary stars and to calculate their orbits. Now we must address more directly the logical difficulty that haunts the dynamical parallax method, for as we have noted, the distance calculation requires an assumption about stellar masses. Yet the determination of stellar masses in turn requires knowledge of stellar distances. If we wish to weigh a binary star system, to determine how much matter its component stars contain, we must know both the orbital period and the true physical size of the orbit. The orbital period we can measure directly by watching the stars circle one another over years or decades. The true physical size of the orbit we can determine only if we know how far away the system lies, for only then can we convert the observed angular separation into a linear separation measured in astronomical units or kilometers. This interdependence of mass and distance calculations troubled astronomers, for it meant that neither quantity could be determined independently of the other. One could assume a mass and derive a distance, or assume a distance and derive a mass, but both could not be firmly established without some external source of information. For those few binary stars whose trigonometric parallaxes could be measured directly, the difficulty was resolved, for the parallax gave the distance without any assumption about mass, and from the distance the true orbital dimensions could be calculated, leading to a reliable mass determination. But trigonometric parallax was measurable only for the nearest stars, leaving the masses of more distant binaries uncertain. The resolution of this difficulty came, at least in part, through the discovery and development of spectroscopic binary stars, a distinct class of double star systems detected not by their visible separation in a telescope but by periodic shifts in the wavelengths of their spectral lines. When a star moves toward us, the light it emits is shifted slightly toward the blue end of the spectrum. When it moves away, the light is shifted toward the red. In a binary system whose orbital plane lies nearly edgewise to our line of sight, each star alternately approaches and recedes as it travels around its orbit, producing a rhythmic back-and-forth wobble in the spectral lines that reveals the presence of orbital motion even when the two stars are too close together to be seen as separate points of light. The first spectroscopic binary was identified in 1889, when astronomers at Harvard College Observatory noticed that the spectral lines of the star Mizar, in the handle of the Big Dipper, periodically doubled and then merged again, betraying the presence of two stars in close orbit whose combined light could not be separated visually. Soon afterward, similar discoveries followed for other stars, and it became clear that spectroscopic binaries were quite common, perhaps more common than visual binaries, for they could be detected at great distances where visual resolution was impossible. The spectroscopic method provides information complementary to that obtained from visual observation. From the Doppler shifts of the spectral lines, astronomers can determine the velocities of the stars along the line of sight and the period of their orbital motion. If the system can also be resolved visually, so that the angular separation and orientation of the orbit are known, then combining the spectroscopic and visual data allows the calculation of both the distance and the masses without the circularity that plagued the dynamical parallax method applied in isolation. The spectroscopic observations reveal the absolute scale of the orbital velocities, which, together with the period, give the true physical size of the orbit. Comparing this physical size to the observed angular size yields the distance directly, and from the distance and orbital dimensions the masses follow. This happy combination of spectroscopic and visual techniques could be applied only to certain favorable systems, those in which the stars were far enough apart to be resolved visually yet close enough to produce measurable Doppler shifts in their spectra. Such systems are not abundant, but where they exist they provide precious calibration points, binary stars whose distances and masses are both securely known. These calibration binaries can then serve as guides for interpreting other systems where only one type of observation is available, helping astronomers to refine their assumptions about stellar masses and thereby improving the reliability of dynamical parallax distances derived for systems that cannot be calibrated directly. As we rest here for a moment, considering the progress that had been made by the turn of the 20th century, we can appreciate that the study of binary stars had grown into a rich and productive branch of astronomy, yielding information about stellar masses and stellar distances that complemented and extended what could be learned from trigonometric parallax alone. The dynamical parallax method, despite its limitations and its dependence on mass assumptions, provided a means of estimating distances to binary systems too remote for direct parallax measurement, pushing the boundaries of the known universe outward beyond the nearest stars. The spectroscopic technique, applied to close binary systems, revealed orbital motions invisible to the eye and provided absolute velocity information that could anchor the distance scale when combined with visual observations. The slow accumulation of double star measurements across the 19th century, from William Herschel's early recognition of true physical pairs through the systematic surveys of his son John and the painstaking micrometer work of the Struves and Burnham and many others, built a foundation of observational data that would support stellar astronomy for generations to come. The binary stars, wheeling patiently around one another in orbits that span human lifetimes, became tools for cosmic measurement, their gravitational dances revealing secrets of distance and mass that the stars keep hidden from casual view. And so we find once again that the patient, methodical work of careful observation, carried out night after night and year after year, opens pathways to understanding that no single brilliant insight could provide. The slow accumulation of facts building toward knowledge as surely as the binary stars build their orbits through time, each measurement a small step along a very long road. In the decades following the first successful measurements of stellar parallax, a quiet transformation began to unfold in the workshops and observatories of the world, as astronomers came to understand that their ability to push further into the cosmos would depend not merely upon patience and mathematical skill, but upon the quality and size of the instruments through which they gathered starlight. The telescopes that had served Bessel and Henderson and Struve so faithfully were excellent instruments for their time, but they were also, in a sense, the products of an earlier age of craftsmanship, built by artisans who worked largely by intuition and accumulated experience rather than by systematic scientific principles of lens design. What emerged in the second half of the 19th century was something rather different, a new era in which the construction of astronomical objectives became itself a kind of applied science, pursued with ever greater precision and ambition, and in which the names of certain master opticians became as celebrated, in their own quiet way, as the names of the astronomers who used their creations. Among these figures, none would rise to greater prominence than Alvan Clark, a portrait painter from Massachusetts who discovered, somewhat late in life, that he possessed an extraordinary gift for the grinding and figuring of telescope lenses. Clarke had come to lens-making through a circuitous path, having first become interested in telescopes as a hobby, building small instruments for his own use and gradually refining his techniques until he was producing objectives that rivaled and then surpassed the finest European work. What set Clarke apart from many of his contemporaries was his almost instinctive understanding of the subtle optical aberrations that plagued large lenses, the chromatic errors that caused stars to appear fringed with color, and the spherical aberrations that softened images and robbed them of their sharpness. He learned to test his lenses not against artificial targets in the workshop, but against the stars themselves, spending countless hours at the eyepiece examining double stars and planetary disks, searching for the slightest imperfections in the images his objectives produced. The firm that Clarke established with his sons, George Bassett Clarke and Alvan Graham Clarke, would come to dominate American telescope making for nearly half a century, producing a series of increasingly large refractors that pushed the boundaries of what was technically possible. Their first major instrument for a public observatory was an 18.5-inch refractor completed in 1862 for the Dearborn Observatory, then located in Chicago, and it was with this telescope that the younger Alvan Graham Clarke made a discovery that would ensure the instrument's place in astronomical history. On the evening of the 31st of January, while testing the newly completed objective by observing Sirius, the brightest star in the night sky, he noticed a tiny point of light hovering close beside it, a faint companion that had never been seen before despite Sirius having been observed by countless astronomers over thousands of years. This companion, which came to be known as Sirius B, was of particular interest because the astronomer Friedrich Bessel had predicted its existence nearly 2 decades earlier, based on subtle wobbles he had detected in the motion of Sirius itself. The discovery demonstrated in the most compelling fashion that the Clarke refractor possessed resolving power of the highest order, capable of separating objects so close together and so different in brightness that they had eluded all previous observation. For the work of measuring stellar parallax, such resolving power was of obvious importance, since the angular displacements involved were so exceedingly small, mere fractions of an arc-second, that any improvement in the sharpness and steadiness of stellar images translated directly into improved precision of measurement. The success of the Dearborn refractor led to commissions for ever larger instruments, and in 1873 the Clarkes completed a 26-inch objective for the United States Naval Observatory in Washington, which was at that time the largest refracting telescope in the world. The Naval Observatory had long been engaged in the measurement of stellar positions and motions as part of its mission to provide accurate astronomical data for navigation, and the new refractor was expected to advance this work considerably. Asaph Hall, who served as professor of mathematics at the observatory, used this instrument to discover the 2 moons of Mars in 1877. Demonstrating once again the power of large apertures to reveal objects previously hidden from view. The telescope remained in active use for parallax observations and other precision work for many years, its long focal length and excellent optical quality making it well suited to the patient business of measuring the positions of stars with the utmost care. The final decades of the century saw the construction of still larger refractors, as wealthy benefactors and ambitious observatory directors competed to possess the most powerful telescopes in existence. James Lick, an eccentric California land baron, bequeathed a substantial fortune for the construction of an observatory on Mount Hamilton, east of San Jose, and the centerpiece of this new institution was to be the largest refractor yet built. The Clarkes accepted the commission and set about producing a 36-inch objective, a task that required the procurement of suitable glass blanks from France and many months of painstaking grinding and polishing. The Lick Observatory saw first light in 1888, and its great refractor immediately became the premier instrument for visual observation in America, its massive lens gathering more light than any telescope before it and forming images of remarkable clarity and definition. Yet even as the Lick refractor was being completed, plans were already underway for something larger still. Charles Tyson Yerkes, a Chicago streetcar magnate of somewhat colorful reputation, agreed to finance the construction of a 40-inch refractor for the University of Chicago, and once again the Clarks were called upon to produce the objective. This was to be the final and greatest achievement of the Clark firm, and also the last great refractor of the classical era, for the 40-inch aperture represented something very close to the practical limit of what could be achieved with lens-based telescopes. The glass blanks for such a large objective were extraordinarily difficult to produce without internal flaws and imperfections, and the finished lenses, each weighing several hundred pounds, could be supported only around their edges, which meant that they tended to sag slightly under their own weight, distorting the images they formed in subtle but measurable ways. The Yerkes Observatory was dedicated in 1897, and its great refractor remains to this day the largest refracting telescope ever built for astronomical research. There was talk, from time to time, of constructing still larger instruments, but such projects never came to fruition, and the reasons for this reveal something important about the nature of astronomical observation and the limits that nature itself imposes upon our ability to see clearly into the depths of space. For as the refractors grew larger and more powerful, astronomers began to understand that the primary obstacle to sharper images lay not in the telescopes themselves, but in the ocean of air through which all ground-based observations must be made. The atmosphere of the Earth, that thin shell of gases upon which all terrestrial life depends, is never truly still. Even on the calmest nights, when the air seems perfectly motionless to human senses, there are subtle currents and eddies, slight variations in temperature and density, that cause starlight to bend and waver as it passes through. This phenomenon, which astronomers came to call seeing, was familiar in a general way to anyone who had spent time at the eyepiece, for it manifested as a constant trembling and dancing of stellar images, a restless motion that made precise measurement frustratingly difficult. What became clear in the Great Refractor era was that this atmospheric turbulence imposed a fundamental limit on the sharpness of images that could be achieved from the ground, regardless of how large or how optically perfect the telescope might be. A small telescope, with an aperture of just a few inches, forms images whose apparent size is limited primarily by diffraction, the spreading of light waves as they pass through a finite opening. As the aperture increases, the diffraction limit decreases, and in principle the images should become sharper and more finely detailed. But atmospheric seeing typically limits the effective resolution to something on the order of 1 or 2 arcseconds, equivalent to what might be achieved with a telescope of only a few inches aperture. A telescope of 20 or 30 or 40 inches gathers vastly more light than a small instrument, and can therefore reveal fainter objects and detect finer differences in brightness, but it cannot see more sharply than the atmosphere will permit, at least not under ordinary conditions. This understanding led astronomers to search for observing sites where the seeing might be better than average, high mountains where the air was thin and relatively undisturbed, remote locations far from cities and their attendant heat sources. The Lick Observatory on Mount Hamilton was an early example of this trend, and its mountain location did indeed provide seeing conditions that were often superior to those found at lower elevations. But even at the best sites, the atmospheric limitations remained, and astronomers were forced to accept that their visual observations would always be subject to this fundamental constraint. For the measurement of stellar parallax, the implications were profound. The annual displacement of even the nearest stars amounts to less than 1 arcsecond, and for more distant stars the parallax is proportionally smaller, quickly dropping below 1/10 of an arcsecond for stars only a few tens of light-years away. When the atmosphere itself blurs stellar images by an arcsecond or more, measuring displacements a fraction of this size becomes extraordinarily challenging. Astronomers developed various strategies to work around these difficulties, observing only on nights of exceptional steadiness, waiting patiently for moments when the seeing would briefly improve, and making many independent measurements whose average might approach the true position more closely than any single observation could. The instruments used for visual parallax measurement were themselves refined to the highest possible degree of precision. The standard device for this purpose was the filler micrometer, a measuring apparatus fitted to the eyepiece of the telescope, consisting of fine threads or wires that could be moved by calibrated screws to span the angular separation between objects. One wire might be fixed, while another could be driven across the field of view, and by carefully centering each wire upon a star in turn, the angular distance between them could be determined with considerable accuracy. The best filler micrometers were marvels of mechanical craftsmanship, their screws ground to microscopic tolerances, their threads fashioned from spider silk because no manufactured fiber was fine enough for the purpose. Other devices served similar purposes, including the double-image prism, an optical element that produced 2 images of each star in the field, separated by an amount that could be precisely controlled. By adjusting the prism until the 2 images of one star coincided exactly with the 2 images of another, the observer could measure angular separations with great delicacy, and the method had certain advantages over the filler micrometer in that it was less affected by personal bias in centering the crosshairs. Each technique had its adherents and its particular strengths, and skillful observers often achieved remarkable consistency in their measurements, agreeing with one another to within a few hundredths of an arcsecond despite the ever-present disturbances of the atmosphere. The human demands of visual parallax work were considerable, and perhaps insufficiently appreciated by those who knew astronomy only through published papers and tabulated results. The observer sat for hours at the eyepiece, often in the cold and darkness of an unheated dome, making measurement after measurement with painstaking care and recording each result by the dim light of a shaded lamp. The work required intense concentration sustained over long periods, a steady hand and a trained eye, and a temperament suited to the patient accumulation of data over months and years. Some observers found a certain meditative satisfaction in this routine, a quiet rhythm of observation and recording that could fill the long winter nights, but others found it tedious beyond endurance, and the history of 19th-century astronomy includes more than a few examples of observers whose health or spirits were worn down by the relentless demands of precision measurement. The cold was a particular hardship, for the dome had to remain open to the night sky, and any attempt to warm the observing chamber would create the very air currents that degraded the seeing. Observers bundled themselves in heavy clothing and sometimes sat with their feet upon heated bricks, but still the chill seeped in, numbing fingers and making the manipulation of fine micrometer screws an exercise in stubborn persistence. The strain on the eyes was also considerable, especially when observing faint stars that hovered at the very limit of visibility, and many experienced observers developed techniques for relaxing and refocusing to prevent the fatigue that could compromise their measurements. As the century drew toward its close, it became increasingly clear that photographic methods offered a potential escape from some of these difficulties. The photographic plate, once exposed, provided a permanent record of the stellar field that could be measured at leisure in a warm and well-lit laboratory, and measurements could be repeated and checked without requiring additional nights at the telescope. Early photographic emulsions were slow and insensitive, requiring long exposures that left stellar images blurred by tracking errors and atmospheric motion. But steady improvements in plate technology gradually made photography competitive with visual methods for many purposes. The transition from visual to photographic astrometry did not happen all at once, and through the final years of the 19th century both methods continued in use, often side by side at the same observatories. Some astronomers embraced photography enthusiastically, recognizing its potential for systematic surveys and large-scale mapping of stellar positions, while others remained loyal to visual methods, trusting the trained human eye over the chemical vagaries of the photographic emulsion. The great refractors continued to be used for visual parallax work well into the 20th century, and some of the most precise visual observations were yet to come. But the direction of future development was becoming clear, and the age of the photographic survey was beginning to dawn. What the great refractor era had demonstrated, above all, was that the measurement of stellar parallax required not merely large and powerful telescopes, but a comprehensive approach that addressed every source of error, from the optics of the instrument to the personal characteristics of the observer to the fundamental limitations imposed by the atmosphere itself. The astronomers of this period had pushed visual observation to something approaching its natural limits, developing techniques and instruments of extraordinary refinement, and had laid the groundwork for the photographic methods that would dominate the coming century. The quest to measure the stars would continue, taking new forms and employing new technologies, but always building upon the foundations that these patient observers had established through their thousands of hours at the eyepiece, watching the gentle dance of distant suns through the trembling air of Earth. As the 19th century drew to its close, and as the calendars turned toward the year 1900, the astronomers of the world found themselves in possession of a modest but precious collection of stellar distances, gathered over 6 decades of patient and exacting work. This collection, when assembled and examined in its entirety, represented one of the great triumphs of observational science, and yet it also revealed, with quiet clarity, the profound limitations that still constrained humanity's understanding of the universe. The stars had yielded their secrets reluctantly, fraction of an arcsecond by fraction of an arcsecond, and the catalogue of known parallaxes stood as a testament to both perseverance and humility. By the turn of the century, approximately 60 stellar parallaxes could be considered reliable, which is to say that they had been measured with sufficient care and confirmed with sufficient consistency that astronomers felt confident in accepting them as genuine determinations of distance. This number, 60, may seem small when one considers the countless thousands of stars visible to even a modest telescope, and the millions upon millions that reveal themselves to larger instruments. But each of these 60 measurements represented years of careful observation, painstaking calculation, and the accumulated expertise of the most skilled practitioners of positional astronomy. These were not numbers plucked easily from the heavens, but rather prizes won through dedication and patience, through countless nights of careful measurement and countless days of careful arithmetic. The foundational measurement, the one that had opened the door to all the others, remained Friedrich Wilhelm Bessel's determination of the parallax of 61 Cygni, that modest double star in the constellation of the Swan. Bessel had published his result in 1838, finding a parallax of approximately 0.314 arcseconds, which corresponded to a distance of roughly 10.5 light-years. Subsequent measurements by other observers, using improved instruments and refined techniques, had generally confirmed Bessel's work while suggesting small adjustments, and by 1900 the accepted parallax for 61 Cygni had been refined to approximately 0.29 arcseconds, placing the star at a distance of just over 11 light-years from the Sun. This gentle revision illustrated an important principle, namely that parallax measurements were not fixed and final truths but rather progressively improved approximations, each generation of astronomers contributing incremental refinements to the work of their predecessors. Thomas Henderson's measurement of Alpha Centauri, announced shortly after Bessel's result, had revealed the nearest stellar neighbor to our solar system, with a parallax of approximately 0.75 arcseconds corresponding to a distance of just over 4 light-years. This remained, at century's end, the largest stellar parallax known, and Alpha Centauri held its position as the closest star, a distinction it would retain as measurements grew ever more precise. The closeness of Alpha Centauri made its parallax relatively easy to measure, at least by the demanding standards of such work, and multiple observers had confirmed Henderson's fundamental result while refining the precise value. Friedrich Georg Wilhelm Struve's measurement of Vega, the brilliant blue-white star in the constellation Lyra, had proven more troublesome than the other early determinations. Struve had found a parallax that subsequent work suggested was somewhat too large, and by the end of the century the accepted value for Vega's parallax had been revised downward to approximately 0.12 arcseconds, placing this bright star at a distance of roughly 27 light-years. This revision illustrated the particular challenges posed by bright stars, whose images on the photographic plate or in the eyepiece of the telescope were large and somewhat ill-defined, making precise positional measurements more difficult than for fainter, more point-like stellar images. Among the other well-established parallaxes in the catalogue of 1900, several deserve particular mention for their scientific importance or for the care with which they had been measured. Sirius, the brightest star in the night sky, had been found to possess a parallax of approximately 0.37 arcseconds, corresponding to a distance of roughly 8.5 light-years. This measurement was of particular interest because Sirius was known to be a binary star, accompanied by a faint white companion that had been discovered through its gravitational influence before it was ever seen directly. The distance determination allowed astronomers to calculate the true luminosity of Sirius and its companion, revealing that while Sirius itself was extraordinarily bright, its companion was remarkably dim despite having a mass comparable to that of our Sun, a puzzle that would not be fully resolved until the physics of white dwarf stars was understood in the 20th century. Procyon, another bright star known to possess an unseen companion, had been measured at a parallax of approximately 0.31 arcseconds, placing it at a distance of roughly 10.5 light-years, quite similar to the distance of 61 Cygni. Altair, the brightest star in the constellation Aquila, showed a parallax of roughly 0.2 arcseconds, corresponding to a distance of about 16 light-years. These and similar measurements began to populate the solar neighborhood with known objects at known distances, creating the first tentative three-dimensional map of the stars nearest to the Sun. The catalogue also included a number of fainter stars that had attracted attention precisely because their large proper motions suggested they might be relatively nearby. Lalande 21185, a dim red star in the constellation Ursa Major, had been found to possess one of the largest parallaxes known, approximately 0.4 arcseconds, placing it at a distance of just over 8 light-years. Groombridge 34, another faint star with rapid proper motion, showed a similar parallax. These inconspicuous objects, invisible to the unaided eye, turned out to be among the Sun's closest neighbors, a finding that hinted at the vast population of dim stars that must exist throughout the galaxy, stars too faint to draw attention but numerous beyond counting. The accumulation of these measurements had required astronomers to develop an increasingly sophisticated understanding of the sources of error that could corrupt their results, and the catalogue of 1900 was accompanied by an extensive literature discussing these difficulties in exhaustive detail. Atmospheric refraction remained a persistent concern, the bending of starlight as it passed through the Earth's atmosphere causing apparent displacements that varied with the star's altitude above the horizon, with the temperature and pressure of the air, and with the wavelength of the light being observed. Elaborate tables had been constructed to allow observers to correct for standard atmospheric conditions, but departures from these standard conditions introduced uncertainties that were difficult to eliminate entirely. The aberration of starlight, that apparent displacement caused by the combination of the Earth's orbital motion with the finite speed of light, had been well understood since Bradley's discovery in the 1720s, but the precise correction for this effect required accurate knowledge of the Earth's orbital velocity and of the direction of the star being observed. Small errors in either quantity would propagate into the parallax determination, and achieving the necessary precision demanded careful attention to the details of the Earth's orbit as refined by the best work of celestial mechanicians. Instrumental flexure presented challenges of a different sort, arising not from the atmosphere or from the geometry of the Earth's motion but from the physical behavior of the telescope itself. As a telescope was pointed toward different parts of the sky, the tube and the mounting would bend slightly under their own weight, causing subtle shifts in the relationship between the optical axis and the measuring scales. The finest heliometers and transit circles were constructed with extreme rigidity, using the most stable materials available and employing ingenious mechanical arrangements to minimize flexure. But no instrument could be made perfectly rigid, and the systematic errors introduced by flexure had to be carefully mapped and corrected. Perhaps the most subtle source of error, and one that had only gradually come to be fully appreciated, was what astronomers called the personal equation of the observer. Different individuals, it turned out, possessed slightly different reaction times and perceptual habits, leading to small but systematic differences in how they recorded the transit of a star across the crosshairs of a telescope or estimated the bisection of a stellar image by a measuring wire. These personal differences were not large, typically amounting to only a few hundredths of a second in time measurements or a few hundredths of an arcsecond in position measurements. But when one was attempting to detect parallaxes of a tenth of an arcsecond or less, even such small systematic errors could be troublesome. Observatories developed elaborate protocols to measure and correct for the personal equations of their staff, and the most reliable parallax determinations were typically those made by a single observer working consistently over an extended period, so that personal equation would affect all the measurements equally and cancel out in the final calculation. It was in this context that the early photographic work of Frank Schlesinger at the Yerkes Observatory began to point toward a new and more promising approach to parallax measurement. Schlesinger, a young American astronomer, had begun in 1899 to experiment systematically with photographic methods for determining stellar positions, and his work would continue through the early years of the new century with increasingly impressive results. The photographic plate, unlike the human eye, did not possess a personal equation, and it recorded all the stars in a field simultaneously rather than requiring each to be measured in sequence. Moreover, the plate provided a permanent record that could be measured repeatedly by different observers using different measuring engines, allowing systematic errors to be identified and reduced in ways that were impossible with direct visual observation. Schlesinger's work at Yerkes, using the 40-inch refractor that was then the largest refracting telescope in the world, demonstrated that photographic methods could achieve precisions comparable to or exceeding the best visual measurements, and he began to develop standardized procedures that would eventually transform parallax work from an art practiced by a few gifted observers into a systematic program that could be pursued on an industrial scale. This transformation would take decades to complete, but by 1899 the outlines of the future were already becoming visible to those who paid attention to Schlesinger's careful experiments with glass plates and measuring microscopes. Despite all the progress that had been made, the Parallax catalogue of 1900 revealed a fundamental limitation that no existing technique seemed capable of overcoming. There appeared to exist a practical barrier at parallaxes of roughly 0.05 arcseconds, below which measurements became unreliable and inconsistent. This barrier corresponded to a distance of approximately 60 light-years, and it meant that the vast majority of stars visible in even modest telescopes lay beyond the reach of direct parallax measurement. The stars that could be measured directly constituted only the tiniest fraction of the stellar population, a small sphere of known space surrounded by an immense and unmeasured beyond. This limitation shaped profoundly the astronomical understanding of the cosmos at the turn of the century. The Dutch astronomer Jacobus Kapteyn, drawing on the available parallax measurements, proper motion studies, and star counts in different directions, had constructed a model of the stellar system that became known as the Kapteyn universe. In this model, the stars were arranged in a flattened, lens-shaped system roughly 30,000 light-years in diameter, with the Sun located somewhere near the center. This model represented the best synthesis of available data, but it rested on foundations that the astronomers of the time knew to be uncertain. The Kapteyn universe was derived primarily from statistical arguments rather than direct distance measurements, since direct measurements could probe only the nearest few percent of the system's supposed extent. Kapteyn and his colleagues had to assume that the stars in the nearby measurable volume were representative of stars throughout the system, an assumption that might or might not be correct. They had to assume that the apparent distribution of stars on the sky reflected their true spatial distribution, neglecting or attempting to correct for the absorption of starlight by intervening matter, a phenomenon whose existence and extent were still matters of active debate. The resulting model was elegant and self-consistent, but it carried uncertainties that were difficult to quantify and perhaps larger than anyone fully appreciated. The nature of the nebulae remained one of the great unresolved questions at the turn of the century, and the parallax measurements available had done little to settle the matter definitively. Some nebulae appeared to be associated with stars and could be assumed to lie at roughly stellar distances, but others, particularly the spiral nebulae that had been revealed in such striking detail by Lord Ross's Great Telescope and by the new photographic surveys, remained enigmatic. Were these spiral forms enormous systems of stars lying far beyond the boundaries of the Kapteyn universe, true island universes comparable to or even larger than the stellar system containing the Sun, or were they relatively nearby structures of gas and dust, perhaps solar systems in the process of formation, as some had suggested? The parallax method offered no help in answering this question, for no spiral nebula showed any measurable parallax at all, indicating only that they lay beyond the 60 light-year horizon of current techniques. which was consistent with either interpretation. The absolute scale of the universe thus remained deeply uncertain. The parallax measurements had established the distances to a handful of nearby stars with reasonable confidence, but extrapolating from these local measurements to the scale of the stellar system as a whole, and from the stellar system to whatever larger structures might exist beyond, required chains of inference that grew ever more tenuous with each link. The period luminosity relationship of Cepheid variable stars, which would eventually provide a means of measuring distances far beyond the reach of parallax, had not yet been discovered, and the cosmic distance ladder that 20th-century astronomers would construct rested in 1900 on a single firm rung: the parallax determinations of the nearest stars. There were also troubling inconsistencies among the parallax measurements made at different observatories. The same star, measured by careful observers using excellent instruments at different locations, would sometimes yield parallax values that differed by more than the claimed uncertainties would suggest. These discrepancies might arise from any of the error sources already discussed, from atmospheric refraction or instrumental flexure or personal equation, but they might also indicate systematic errors that were not yet understood or accounted for. The comparison of results from different observatories became an important tool for identifying such problems, and the astronomical literature of the period contains many careful analyses attempting to reconcile discordant measurements or to identify the sources of disagreement. Such was the state of stellar parallax as the 19th century ended and the 20th began. 60 reliable distances, a well-characterized but apparently insurmountable barrier at 0.05 arcseconds, a promising but still developmental photographic technique, and a model of the stellar system that was acknowledged to be provisional and uncertain. The astronomers who gathered at observatories around the world to welcome the new century could look back with satisfaction on 6 decades of progress since Bessel's breakthrough, but they also understood clearly how much remained to be done. The universe had revealed a small part of itself to their patient inquiries, but it held far more in reserve, waiting for new instruments and new techniques that would push the boundaries of the known ever further into the uncharted depths of space. The work continued, as scientific work always does, each generation building on the achievements of those who came before while preparing the ground for those who would come after. The parallax catalogue would grow, the precision of measurements would improve, and eventually the photographic methods that Schlesinger was pioneering would transform the entire enterprise. But all of that lay in the future, and the astronomers of 1900 could not know in detail what form those advances would take. What they did know was that the stars were very far away, that measuring their distances was extraordinarily difficult, and that the effort was worth making nonetheless, for in those measurements lay the key to understanding the true scale and structure of the cosmos that surrounded the small blue planet where all these patient observers made their homes and did their work and recorded their careful measurements in the great ledgers of astronomical science.